Okay, good morning everybody. Glad you could make it. We were hoping for more people live, but I guess we have the option of having these hybrid meetings. I guess it's made it easier for people to attend, but at the same time less willing to come and be present in person. So I really appreciate those of you who have come here on, live. A couple of things before we get started. Keep in mind that unless you are eating, you should be wearing your masks. This is a university requirement, okay? So we have to follow the university rules, which I guess will keep masks until we are told otherwise. Thank you for being here. If you don't have a name tag, please contact Sana at the registration desk. She will counter. She will give you one. Okay, so I guess we'll get started. Thank you for being here. The intention of this workshop is to discuss a series of issues regarding hydrogen, the hydrogen economy in particular, which have come to a fore, as I'll discuss in a second, in the interest of net zero, right? What the Canadian government is trying to accomplish by 2050, and even earlier by 2030, right? The reduction of emissions. My name is Claudio Canizares. I'm the executive director for the Waterloo Institute for Sustainable Energy, WISE. I'm somewhat recent. I started in August. And this is our second workshop that we have organized around these hot topics that are basically driving our sustainable energy discussion and debate and research, because that's our main interest. We are as you'll see in a second, an institute that is committed to establishing research relationships between faculty members, industry, government, NGOs. And the interest in this particular topic, on this particular session, this particular event, is hydrogen. Now, before I get into the discussions about hydrogen, get things moving off in the direction of our presentations and discussions and debates, let me introduce briefly WISE. So WISE is basically, as you can see here, is committed to sustainable energy research, debate, discussions, policy, etc. Technology, certainly, we are closely associated with the Faculty of Engineering and the Faculty of Environment, who our sort of main membership comes from these two faculties. However, we do have interactions with the Faculty of Arts, Faculty of Health Studies as well, in terms of discussions around anything that has to be sustainable energy. We're part now of a sustainable futures cluster that we are collaborating, or we are closely closing our links with the Institute for or IC3, Institute for Climate Change, and the Water Institute as well. So this is, our intention is to collaborate, obviously, as I just mentioned, reach out, which is what we're trying to do through these events. So establish these links between our university, our faculty, our members, and industry, NGOs, government as well. And influence. Our intention is also to develop policy. In fact, we are in the process of hiring new faculty members at Faculty of Environment, Faculty of Engineering, in which we are trying to get new people involved, and we're looking for Ontario. We're trying to hopefully in the near future have an Ontario research chair in all these issues of policy, okay? Sustainable energy policy, which is another of the main drivers or the main focus of our institute. And we hope that this will basically enhance our expertise in that particular area. I'm personally from the technical area. I work in power engineering, power systems, different aspects of sustainable energy systems from the perspective of the power grid. And I'll do a bit of work on policy, but we are actually very interested in influencing the debate, okay? And this is part of the intention, that's one of the intentions of this event. Now, as I was mentioning, WISE basically focus on all different aspects of sustainable energy. So we can look at the technical aspects, the grid, hydrogen, for example, the generation, utilization, etc., of hydrogen, all the issues of carbon capture and sequestration of CO2, which is going to be, we have a previous workshop. Some of you, I guess, were here before in that event, in which we were trying to establish the relationship between these and the need for CCS in the context of a net zero future, okay? And this is in the transition, right? By 2030, we have to basically reduce our emissions by what, 40, 50%? So to accomplish that, we're gonna need something like carbon capture and sequestration. We also looked at different aspects of energy, not only electrical grid, although it's gonna be part of the main, if you will, the core of electrification, right? The core of net zero. We're going to have, I like to refer to this as the electrification of everything, in which basically the power grid is going to play a major role. But there are also other aspects of energy in which we are quite interested in, and hydrogen is one of them. And certainly the policy debate, we want to be part of that as well. We're participating in different committees at the government level and trying to influence the discussion, as I mentioned before. Now, with respect to this event, we have following leads. We have Professor Mike Fowler, who is going to be here hopefully in person soon. We have Shanggu Li, who is going to be joining us in person, I hope, soon. We also have from Mike is from chemical engineering. Shanggu Li is from mechanical and mechatronics engineering. Jeff Jostek, chemical engineering, is he here? Okay. Is he going to be joining us as well? Okay. Shangyu Wu, I saw him sitting on the back. Oh, okay, he was there. Okay. He is from mechanical electrical engineering. All of these colleagues are working in different aspects of hydrogen. Maurice Dussault, which is in Calgary, he's going to be joining us live from Earth and Environmental Sciences, Faculty of Science. We have Professor Samesh Shagari, which is an associate professor, a young professor of mechanical electronics engineering. She's a professor at Windsor. And then we have Richard Jackson, which is our go-to guy when we have this type of discussions. He is associated with their environmental science as well. He also has a consulting company. And Eric Rosset, chemical engineering, is he going to be joining us in person soon? Hopefully he'll joining us soon. And then myself, which together with Armugan here, thank you very much, Armugan, who is the second in command at WISE and basically is been the main organizer of this event. And also we have Sana, who you have met at the beginning. As I mentioned, if you don't have a name tag, please contact Sana. She'll provide one to you, so we can have some interactions and know who we all are. Now, in the aspect of all this discussion we were having about our net zero discussion, we are quite interested in all different directions of trying to influence or interact with government in terms of the emissions reductions in Canada. So there's a specific, I see Shanggu Li here, he just joined us, which is the intention of basically reduce carbon emissions by 50% about by 2030, right? And in that sense is the intention of tax. One of the main policy aspects is taxing emissions, right? And also all these issues of carbon reduction. Now, in the context of this, hydrogen is going to play a major role, okay? Green hydrogen in particular. I think that there are certain aspects, as we will have the discussion today, there are certain aspects that will require basically the need for hydrogen and ammonia as well in the context of this net zero future that we are all shooting for by 2050. I gotta remind you that 2030 is just in, 8 years? So it's just around the corner. So if we are gonna be successful in accomplishing these targets, we are going to have to need all the possible tools, technological tools, etc., that allows us to reach those targets. And hydrogen is part of it. And the intention of the Canadian government is basically to support this hydrogen economy that has been around or has been kicked around. I've been involved in this for many years, but at least for the last decade or so, hydrogen has been under discussion. Then it took a little bit of a slowdown, but in the last few years, with the interest in Canada and in particular in Europe, there's a big commitment to a hydrogen economy in terms of hydrogen production, generation, utilization, and different aspects of the type of discussions we're going to have here. And we are certainly, for example, in my case, I have collaborations with colleagues in Germany who are quite interested in. Germany is putting a lot of interest, a lot of money into this particular issue. So we are also interested in establishing international collaborations. We're happy to help our faculty members, our partners, industry partners, to establish these links in any way or form that we are able to or capable to do so. So those are the different aspects. Now, we are also a very important part in the Waterloo, at University of Waterloo and WISE in particular, is our involvement with Sustainable Development Goals, SDGs. And we believe that we can certainly influence some of these aspects. We have highlighted in here, in this case, the 7 SDGs in which we are directly involved in. And one of them is certainly access to energy. And we also have a big interest in remote communities. We have actually one of our initiatives within WISE is access for energy to humanity, A4H. And we are interested in basically all the aspects of hydrogen applications also in remote communities, because we believe that it's also going to be part of the solution in all this discussion. So with that said, I just want to highlight the intention of this event, which is basically establish these multiple collaborations, multiple level discussions among faculty, researchers, industry, and as well government. So that's the intention of this event. And we are certainly very much, we have all the tools and the different interests, and we have a history of establishing these links, and we welcome these opportunities, especially our industry partners who are present here to establish these links and are going to be present also online here. Okay, so I think we're going to start with the keynote speaker. If I can have Armugan here to get the proceedings started. Hopefully Robert is already online. Okay, excellent. Okay, so we have Robert here. He's Executive Director for and CEO of Hydrogen Business Council. I've had a long relationship collaboration with Robert. Good to see you, Robert, here in the area of electric vehicles. Now he's working, committed to the different aspects of hydrogen. Certainly, zero-emission vehicles is a big aspect of hydrogen. And thank you very much, Robert, for being here. I guess the floor is yours.
Thank you very much, Claudio. And you're right, we go back a ways. Can everybody hear me okay?
Yes.
Excellent.
Yes,
so I'll go right into it and just give you a little bit of background. So what is the Hydrogen Business Council? We basically started about 5 years ago as an entity which would try to represent the hydrogen sector here in Ontario. And I should give you a caveat. The way things are developing in terms of hydrogen, I guess you could say associations across Canada, is each jurisdiction with its own uniqueness in terms of energy supply is developing their own policy framework and their own advocacy framework. And we in Ontario are somewhat unique in that we have a large proportion of nuclear in our electricity generation, unlike, for instance, Alberta, which is still burning coal in some instances and which is dependent heavily on natural gas for producing blue hydrogen. So Quebec, on the other hand, has a lot of electricity. They're already a very green grid. Each province has its own specifics. And so what I'm going to be talking about today is mostly about Ontario because that's the area that I'm familiar with. We'll talk a little bit about the federal programs, but I'm hoping that one of your other speakers can speak more to the issue of the federal government. But we are affiliated with the national organization, the Canadian Hydrogen and Fuel Cell Association, which is presently based in Vancouver, but their new CEO is based here in Ontario. So anyway, you can see our last conference was very successful last November. These are all the sponsors that you see their logos on our main screen. We're having another one this November as well. Very successful. The last one had 350 participants virtually, and the next one will be virtually as well. We gambled that it would probably continue to be virtual. We'll see how that goes. So, but in terms of what we've been doing is we basically raise awareness about hydrogen, and that continues to be the biggest barrier towards hydrogen adoption, is just people are unaware. They know about batteries, they understand how they are part of electrification, but they don't understand that hydrogen is basically another electric option when you're looking at transportation. Instead of batteries, it's fuel cells. We also advocate on behalf of the hydrogen sector with the Ontario government and with the feds to some extent. And we've had limited success, frankly. I can talk about that if there's time at the end as to why we are getting some of what we were asking for, but not all. On that basis, maybe I'll just roll into some general background about hydrogen production and hub creation here in Ontario. Could I have the next slide, please? So, as I mentioned earlier, our grid is getting greener constantly. And we see these various sources of electricity here in Ontario that are emission free. And I'm just depicting them here. That's the Darlington plant, that's Niagara Falls, that's the 400 megawatt solar farm. I believe it's 400 megawatts in Nanticoke, and of course wind all along the eastern shore of Lake Huron. And we expect that our grid will be totally green by 2030. However, there will be a blip after Pickering shuts down in 2025 when we use a lot of combustion turbines to peak our electricity demand. But that will slowly over time shift over to more renewables, and also the blending of hydrogen into natural gas in those very same turbines. And we can talk about that a little later too, hopefully. So this is just a depiction. If I could have the next slide, please. I'm sorry that I'm depending on someone local to switch slides for me, because whenever I try to share screen, weird things happen here. So I'm counting on someone to be able to switch to the next slide. I don't think it's up yet. Am I correct? Well, anyway.
Hi, Robert. Yeah, the slides are changing here.
Oh, they are. Okay, I'm sorry. So so we're on the slide that shows the sector, the sources of electricity generation on a pie chart.
Yes. Can you
Well,
see it
thank
now?
you. I don't see it yet, but that's okay, as long as someone can tell me that the new one is up.
We can see it here. Yes.
Okay, good. So you can see that nuclear continues to be the largest proportion of electricity supply in Ontario, followed by hydro, followed by gas, wind, which is growing constantly, and gas and oil 7%, which is basically methane combustion turbines. Biofuel, small percentage, solar, small percentage. That solar indication of a little more than 1% is rather misleading. If I could have the next slide, please. If I'm correct, the next slide will show you a bar chart, a big yellow bar showing the amount of solar supply in Ontario that's not connected directly to the grid. That solar is coming from embedded solar supply on rooftops of large buildings such as warehouses, and like Canadian Tire and Walmart, for instance, have a lot of solar on their roofs in the area around the airport. This is not shown typically when they show sources of supply in Ontario as being solar. It's not captured by the ISO because they just see it as load reduction. But you can see from that bar chart, what we have is almost 2,500, and actually this is out of date, I have to confess. It's probably closer to 4,000 megawatts of electricity from solar, which is significant, but not properly identified in our grid. Now, GHG emissions, this is a little out of date, but really the trend is the same. you can see that from this next slide, the pie chart and bar chart shows that the majority of our emissions are coming from transportation and space heating for buildings. The orange bar, transportation, is the single largest emitter here in Ontario. And so it's low-hanging fruit if we can start converting transportation to hydrogen. And I should mention that if you subdivide sector by subsector by subsector in the transportation sector, the one that's growing fast is trucks, heavy vehicles. Automobiles are becoming more efficient with each passing year because of fuel standards, but trucks are not. And in fact, if you ever go along the 401 lately, you'll know that 2 lanes are almost all trucks. It's pretty dramatic. And so if you look at trucks as a subset, it's probably the single biggest emitter within transportation. And that's why we look at trucks as being the next big issue in terms of decarbonization. Now, because of our grid, next slide, please. Because of our grid, we do, in fact, have this potential to electrify, not just with electricity and batteries, but also with production of hydrogen through electrolyzers, a fleet, hopefully, of electrolyzers across Ontario that would be using electricity not necessarily during peak times, but during shoulder and off-peak times, or even with surplus electricity. In the past, we've had surplus electricity here on our grid sufficient number of times that we've had to curtail it or sell it at less than cost to our US partners through the interties. That will probably stop, and it will stop sooner than you think, because the existing government realizes this is a huge loss of revenue for Ontario. Could I have the next slide, please? So just so that I know that I'm marking the slides, this should be a slide showing several different vehicles, trucks, trains, buses, what have you, and a couple of politicians standing in front of a hydrogen car. Is that what you see? It's the same as my backdrop behind me.
Yes, yeah, we can see it.
Thank you. Thank you, Claudio. And yeah, I'm just showing you this because it's a multi-moded issue here of what do we convert. And yes, you can drive cars that do have hydrogen fuel cell, capability. And that particular car, I'll talk to you a little later, is the Toyota Mirai. But there's also the Hyundai Nexo that's also a hydrogen car. Now, these cars are available. You can buy them now, but of course you need to know where you're going to be refueling them. Could I have the next slide, please? So this is an interesting slide. You're seeing 4 modes of transport. What's interesting here is 3 of these are things that you can buy off the shelf. I wonder if you could figure out which ones, but I'll save you the trouble. That locomotive is being built by CP Rail, and there are 3 of them presently on rails in Calgary. And they were developed with a combination of money from CP, the Alberta government, and the federal government, a $30 million project. I'm actually very jealous. I wish we had that kind of money here in Ontario for a project like that. But it won't be long before locomotives like that will be pulling freight and pulling commuter rail as they would here in Ontario with bi-level cars. That bus is made by New Flyer, which is based here in Canada, but their production facility is global. That particular bus was probably built in the US, but it's an articulated bus, totally fuel cell operated, and you can fuel it in 10 minutes, which is one of the big advantages of hydrogen versus batteries. You don't have to park your vehicle overnight for charging. You can fuel it just like you would with diesel, except it's a gas. Those trucks are high zone. High zone trucks are now available. They're being sold in the hundreds to California, to Europe, and into China. And we're looking to bring a fleet of them here to Ontario. Now, that Airbus aircraft, which is a propeller aircraft, is one of several different propeller-driven aircraft that are being converted to hydrogen, but these are only prototypes. They are not ready for commercial service, unlike the other 3 elements. Could I have the next slide, please? So just a little bit about safety. We can talk about safety another day, but unfortunately, when I talk about awareness being the biggest barrier on hydrogen adoption, this is part of the problem. When you talk to people in the general public who vote, And this hydrogen is not a voter issue. If we could make it a voter issue, perhaps we'd get more traction. You talk about it and they think of the Hindenburg, or they think of cars. They'll say, well, where's the car? Can I buy it? Nothing in between. They don't talk about industrial applications. They don't talk about buses or trains or trucks. They talk about the Hindenburg. They talk about cars. So part of our job is to make people realize that there's a huge spectrum of applications, and that most of the ones that we're looking at have the higher carbon intensities if we can switch them over. As you can see there, that gentleman in the yellow tie is actually Vic Fideli, and he's the Minister of Economic Development here in Ontario. Another one of those cars, as you can see, went 1,360 kilometers on one tank of hydrogen. It took 5 minutes to refuel in California. We're hoping that we can get some fueling stations here in Ontario pretty quickly for people who choose to buy a car with a longer range. It's not a battery car. Could I have a next slide, please? Now, you should be looking at a picture of a fire engine. I like this slide because when people talk about safety, I always put this up and say, do you think that if hydrogen wasn't safe as a transportation fuel, that firemen would be driving it to a fire? And so here we have a classic case of basically a municipal vehicle, but we can also look at garbage trucks and snow plows and all kinds of things, which are heavy transportation, end users, and which we hope to convert to hydrogen. And this is just a copy of the next. So this is a Tucson. I'm sorry, this is a Hyundai Tucson. That's a hydrogen variant, and I have to stress whenever I'm raising awareness that it's the other electric car. You know, if you've got batteries or you have fuel cells, you can either recharge it or you can put in hydrogen. But it is the other electric vehicle, and once you step back from whether it's a fuel cell or a battery, the electric framework basically is the same. It's motors on the wheels. Everything else is the same. So I'm going to talk a little bit now about the government of Ontario's decarbonization strategy, which we've been pressing them to put into play for many, many years now. And they finally released it about 3 weeks ago. And we're still frankly poring over the significance of what the Ontario government has put forward. Unlike the federal government is putting forward, frankly, billions of dollars over several years to incentivize the uptake of hydrogen, either through fueling station incentives or incentives for rolling stock like buses and trucks. But the provincial government is not putting any money forward for capital investments. We hope to change that maybe after the election, but prior to this election, that's the only thing they're promising is policy changes and basically implementation through their various agencies. So the biggest affiliate of OPG right now is a company called Atura Power. And Atura Power was given two things: a fleet of assets, which are combustion turbines, the ones we were talking about earlier that are gas-fired, and a mission to decarbonize the Ontario grid using electricity and hydrogen. And so that's one of the things that they tell us, and I find this a rather interesting business model. They intend to create hydrogen hubs by producing electrolytic hydrogen and then using it to blend with methane into their combustion turbines over time. So they will be a producer of hydrogen and a user of hydrogen. And they will try to produce the electrolyzer capacity to the point where they can then use it for other end users or identify it for retailing. They're looking at other locations, but the key location that was announced 3 weeks ago is a 20 megawatt facility at Niagara Falls. They're still looking for end users for that one. Now, the Ontario government will undertake its own third-party feasibility study to look at other hubs. We can talk about that very briefly, and we, the Hydrogen Business Council, hope to be part of that initiative. Now, one of the very bottom of that slide, talking about government strategy, we're talking about interruptible power rates for production of hydrogen. And this was actually probably the most important thing we asked for. And it looks like we're going to get it, but not quite yet. because the government is still in consultations. But the bottom line is that if you're going to produce hydrogen in Ontario, for whether transportation or whether it's for other industrial applications that you're decarbonizing, you will get a very inexpensive electricity rate for that, to the point where your hydrogen could compete with diesel fuel. And that's an important marker. If you can produce hydrogen that will compete with diesel fuel, you can start converting major fleets over. So the next slide, please, which the header should be proposed provincial support for projects in Ontario. So one of the other things that the government is doing is that they're directing the grid operator to look at using a fleet of electrolyzers as a grid balancing tool. Now, there was a prototype of this built in partnership with Cummins and Enbridge in Markham, and they actually built a 2.5 megawatt electrolyzer with the intent of putting that fuel into the methane distribution grid. And they got last year permission to do so. So that would be what you've called power to gas, where they would actually take electrolytic hydrogen produced off peak and put it into the gas mains. So but what the ISO will do is see what the feasibility is of upscaling that by a factor of 10 or 20 or even more, so that we have something they can toggle on and off to help balance the grid. Bruce Power actually, from time to time, has bottled up power up the Bruce Peninsula, and they're repowering their reactors, their turbo gensets, to produce even more electricity than the nameplate, to the point where they will have 800 megawatts of uncontracted supply very shortly. And to some extent, they might not be able to get that to market through the transmission corridor. So they're looking to produce hydrogen locally as a product, a higher value product that they can market. We're still trying to figure out what we're going to do with that, and I'm working on a panel with them to do that. It may mean that they make green ammonia, because that's something that can be transshipped more easily than compressed hydrogen. The government of Ontario is looking at hydrogen technology and services to be a major export opportunity. And as an example, we have 3 major producers of electrolyzers here in Ontario: Cummins, which used to be Hydrogenics, Next Hydrogen, and Hydrogen Optimized. So we, unlike what people may realize, the center of gravity for hydrogen products and services is moving eastward, away from BC, or at least a significant component of it is. And finally, there will be a role for blue hydrogen here in Ontario. And the reason for that is that some industrial applications will require huge amounts of hydrogen. For instance, the DeFasco steel plant in Hamilton will be converting, and they've gotten $1 billion from the government to convert their steel operation to decarbonize it so that they don't use coal anymore. And in 2028, they will require about 500 tons of hydrogen per day. That just puts them in a whole different class. Now, we know other industrials that, if they're approved, will be also requiring hundreds of tons of hydrogen per day to produce green ammonia or to produce green methanol or other industrial chemicals. So we do not see the grid growing fast enough to electrolyze hydrogen and supply it at those rates. So there will be a role, I think, for blue hydrogen production locally, probably in the Sarnia-Lambton area. So this next slide, and please confirm that you see it, is hydrogen hub activities across Canada. This is a very brief snippet, and I can't pretend to know what every other province is doing, because, as I mentioned earlier, we're basically cutting and pasting each different province into its own particular energy strategy. But BC has always been a major hub for hydrogen. The federal government have supported it through regional development funds, and the BC government has supported it. So they are going to soon see a chain of hydrogen fueling stations down the coast, and connecting with the ones in the US, so that they basically will have a hydrogen corridor all the way from San Diego to Vancouver and points north. But there's a lot of other things happening. And for instance, the Port of Vancouver will be converting some of their operations to hydrogen. They will be looking also at export opportunities for hydrogen production and exporting compressed hydrogen outside the country. Alberta is probably doing more about hydrogen now than any of the other provinces. And my take of that is because the oil and gas sector have seen the writing on the wall, and they know that they're not going to be able to utilize all of what's in the ground if they don't decarbonize it. And so they're looking at decarbonizing by producing hydrogen with steam methane reforming, sequestering the CO2 in depleted gas wells, and then using locally or exporting that hydrogen. Now, there are many projects that are underway, and right now Edmonton is a poster child for how to develop a hub with 6 municipalities, several large companies, and with federal and provincial money behind it. They're going to be producing, again, hundreds of tons of hydrogen per day in the near term and probably thousands over time. They also have several projects for utilization of that, buses, trucks, and the locomotive that I mentioned. The CP Rail has formed a consortium with ATCO, the energy company, to produce fueling stations along their rail corridor from Edmonton to Calgary. And so I wish that we could do the same thing here, and I'm hoping we can do something like that in Ontario. And finally, Quebec has built a 20 megawatt electrolyzer just outside of Montreal, and that is basically for purposes of industrial applications, but they're also looking, I believe, to put between 10 and 20 fueling stations in the Montreal area for hydrogen powered cars. So a little more about hub development here in Ontario, and I'm almost done. I think I just have 1 or 2 more slides. So what you should be looking at right now is progress on hydrogen hub development. As I mentioned, Niagara Falls is probably the first of our hubs, but we're also looking at least Atura, which has been tasked with producing some of these hubs for the Ontario government, is looking for hubs in Brighton Beach, Nanticoke, and the Toronto Portlands, which is all co-located with their combustion turbines. I should mention that the Brighton Beach location, they're looking to actually store hydrogen in a salt cavern, and they've signed an MOU with a company that does geological research to look at the feasibility of this. But if it proceeds, it'll probably be the first hydrogen storage facility here in Ontario. There have been others elsewhere using salt caverns, but never here in Canada. The other major hubs that are already well on their way is Sarnia-Lambton, because it's the Chemical Valley, and they produce hundreds of tons of hydrogen right now, but in what we would call gray hydrogen, where that is where the CO2 is released. And they're hoping to convert a lot of that operation to sequestered hydrogen, CO2, I should say. And finally, because of the DeFasco project in Hamilton, we see that becoming a hub. We at the Hydrogen Business Council are also helping several other regions develop hubs. Durham region, the city of Mississauga, and Bruce County are all very, they have unique capabilities and attributes which would be good for producing a hub. And we're co-funding a study to decarbonize the 401 corridor. You'll hear more about that in the future. So, maybe I'm just going to go to, you should be seeing the next slide, which is what's a hub? It should be self-exclamatory of what a hub is, but it's basically a self-sustaining network of suppliers and end users of hydrogen that make economic sense in one particular locale. And so the Canadian government hopes to see 30 of these across Canada by the end of 2030. And that would be, and ultimately what we hope to see is that interconnection between those hubs would create a hydrogen economy coast to coast. But the feeling is that it's these hubs that are early adopters, if you will, of hydrogen technology, or early producers of hydrogen, and that are clustered together in an economically sustainable way, are the way that we move forward on the hydrogen front. So that's all I have to say for today. My very last slide shows a little bit about the federal program and the amount of money that they're committing. Our big complaint with the federal government, frankly, is that although several of their programs will encourage hydrogen, they encourage batteries as well. And our experience has been that there's a battery bias in the political frameworks, and in the Republic at large. They know what batteries are. They don't understand hydrogen. And so even when hydrogen would have been the optimal solution, they would use a suboptimal battery solution. So we're hoping that the federal government carves out a specific arena for hydrogen development and adoption that would make life easier for us. So that's all, and I don't know if there's time for questions, but if not, we'll talk about that later when we have the networking sessions. Thank you.
Thank you, Bob. Can you hear me?
I can hear you.
Thanks for your presentation, very interesting. There's a few minutes for questions. Then we'll have a short break to get the panel organized. And I'm going to get this started, taking the advantage of chairing this particular session. I have a couple of questions for you, and the first one is regarding the last comment you made, the issues of battery versus hydrogen. I see many applications for hydrogen, certainly many advantages, especially in the transportation, industrial type of applications. My concern has always been, having worked in this area for many years, is the issue of efficiencies in terms of, for example, light vehicles, right? The issue of weight is not as significant as it would be in a heavy transportation. Producing hydrogen to then have electricity produced again is not very efficient, although it's comparable to thermal cycles, but still not as efficient as electricity. So how do you, in that context, how do you place hydrogen? I think it has its applications. And in fact, we ourselves, we have an initiative in introducing hydrogen into a facility, a microgrid facility, in which we also will look at transportation issues, fueling issues.
Yes.
We're getting a vehicle, a light, I guess a light truck, I believe it is, or a transportation vehicle to look at these issues. However, comparable to that, in that particular arena, how do you justify the issue of using hydrogen versus batteries?
Well, thank you, Claudia, for the question. But as an engineer, I'm not a purist. I'm not going to say, well, batteries are the silver bullet, or hydrogen is a silver bullet. It's neither. It's a combination of both. And the transition to where, like for instance, in a battery electric vehicle is ideal in an urban setting. I would not even pretend that would be an arena where a hydrogen vehicle would have any benefits other than the fast fueling. But if you can charge at home, a battery electric vehicle is optimal, I would think. And in fact, I have very good friends in the battery space, like Kara Clareman, who runs Plug and Drive. She and I have been friends for many, many years. But as soon as you start, as you said, Claudio, as soon as you start getting into heavy transportation, you find out that hauling those batteries around takes, the weight of them, the space it takes up, interferes with the economics of heavy transport. And so we see the sweet spot for efficient use of hydrogen in heavy transportation, whether it's buses, trucks, or trains, and maybe even ships, but only where it's efficient. And it goes without saying that there'll still be batteries as part of the system, the traction system. You have to have batteries for the high torque you need for starting, for instance, from a stop. So it inevitably, I keep saying, this is another electric option, but it's one that allows, for instance, a long haul truck that goes from thousands of kilometers and maybe in a single day. They can't afford to stop and charge that battery for that truck for 3 or 4 hours, even on a fast charge, when they could refill it with hydrogen in 10 minutes. So we see that in that particular sector, the one I identified earlier is low-hanging fruit. We see conversion as being an efficient way of using hydrogen.
Thank you, Bob. And my next question, before I open the floor, it was the issue of industrial applications of hydrogen. You did mention there's going to be a significant need of this green hydrogen. However, there might not be enough for servicing some of these industrial applications. And then you talk about blue hydrogen. However, in the context of a net zero future, how are we going to be accomplish this? I guess we'll need a bigger grid to be able to supply all the hydrogen that we require. Because blue hydrogen was going to have its role, but I guess it won't be forever, right?
Let me be very blunt with you. My bias, we all have biases, right? My bias was that the electricity grid in Ontario would be our ace card to produce hydrogen. And we wouldn't necessarily do it for export. It would be mostly for our own consumption, for our own utilization. But when I'm realistic and I look at the industrial needs that are coming fast because a lot of companies want to decarbonize, and they don't announce their plan because there's commercial elements to it that they don't want to share early on because of competition. And bang, suddenly you find out that there's a new company and they're going to want 200 tons of hydrogen. So if you actually look forward at the industrial conversions here in Ontario, I don't see the grid being growing fast enough to meet them. I could be wrong, but I don't see it. The investment would be huge on the grid side. But eventually, I think the grid will grow to meet our needs. But there's going to be a period of time when I think we're going to be depending on blue hydrogen for at least part of our supply. And it would probably be produced in Sarnia-Lambton and sequestered. And we have depleted gas and oil wells here in Ontario. A lot of people don't know that. A lot of them on the north shore of Lake Erie. And the government basically has allowed them, decertified them actually, so they could be used for that purpose if there was an economic benefit to do so.
Thank you, Bob. I guess you make a good point. I guess it's the same debate we had when we were talking about carbon capture sequestration. I guess it will be part of the transition.
Yes.
Blue hydrogen.
Yes.
Thank you very much. So I'm going to open the floor for any questions, comments. Yeah, there is one. Please go ahead. A couple of questions more.
Yeah, good morning. Thanks, Robert. So Chris Penny from Atura Power. So appreciate the rundown on what we're doing. I think you probably walked through what our prospective projects are better than I could myself. So I'm the manager of hydrogen projects at Atura Power, so amongst others responsible for the Niagara project. I wanted to make a comment and then just a quick question to you, Robert. So firstly, I think the kind of key opportunity for Atura is, and I guess it's kind of a unique opportunity, is that because we can be sort of vertically integrated, we have opportunity to consume the hydrogen that we would then produce. And it's kind of that ongoing proverbial chicken and egg scenario, right? Who's going to produce the hydrogen if there's nowhere for it to go? So I think the opportunity that we have, and so that's a message I think that when I'm sharing about a project, I kind of want to put that front and center, because I think that's kind of been one of the missing links is someone to kind of take that opportunity and run with that. So yeah, we're excited about the Niagara project, subject to our federal funding application later this summer. Yeah, really exciting opportunity there. But yeah, Robert, you mentioned, and it's quite relevant, but with respect to provincial support, so the rate with respect to electricity, super helpful. And I think for those that don't know, electrolyzers have the ability to basically dynamically adjust their output and kind of on off relatively quickly. So there's a good case for being able to pay a cheaper rate for electricity as a result. So I think that is definitely a good opportunity for additional development. But beyond that, what do you see as being the hurdle to get the provincial government to sort of be participating more in earnest? Is it an education thing? You mentioned it's not really a voter issue, so is it getting the public a little bit more informed and educated? And then sort of what's your take on that front?
Well, thank you for that question. And yeah, no, I'm very pleased that an agency like Atura is going to take the lead here, because someone had to. As you said, it's a chicken and egg thing. But to the point, you're going to be wanting customers for your hydrogen, and until at least two levels of government provide some risk avoidance, capital risk avoidance, by helping to for capital project procurements, that we're not going to have those off takers. And my assessment is it is awareness, and because it's not a voter issue. And I know that the Ontario government, as it presently exists, and pre-election, I'm not going to make any speculation as to who will win or who won't, but I get the sense that the existing government will probably put more effort into this after the election. But prior to the election, they basically have been paring back capital money on every front, including this one. And so they know that they're going to have to step up, or else jurisdictions like Alberta and BC and Quebec are going to race ahead of us in terms of their adoptions and in terms of their industrial development. So I guess part of what we see ourselves doing is raising awareness at the grassroots level, so that it becomes a voter issue, so that people see that hydrogen has a big role in decarbonization. That's a bit of a challenge, because it's as unfortunately, as you guys all know, because you're all engineers and scientists here, the minute you start talking to people in the general public and you start getting technical, they zone out. They don't want to hear about it. So I personally think we're going to have to get some buses, trucks, and trains viable here so people can see them operating, and that's when things take off. And so that's the big hurdle to me, is to get demonstration projects that are commercially viable here in Ontario.
Okay, thank you. Yeah. Go ahead. Then, okay, one more question after that.
Hey Robert, thanks for the presentation. I just have one question about the Sarnia region. Do you think that's one of the top spots?
Please identify yourself.
My name is Jay Duhan. I work for Respec. I'm a geomechanical engineer. Do you think the Sarnia region is a top spot for becoming a hydrogen hub because of the presence of industry, presence of salt caverns which can be used for storage, and also presence of porous reservoirs which can potentially be used for carbon capture?
Absolutely, you've hit it bang on. It's that as a hub. It's just an obvious place where you're going to put a hub and produce hydrogen, blue hydrogen, sequester it locally, store hydrogen locally. But it's because there's so many industries there that are using hydrogen right now, and they need to green their operation. So it becomes a natural hub. And in fact, there's a non-government agency representing the Sarnia Lambton economic community. They've just put out an RFP just about a week ago. They're looking for a third party to come in and do a monumental foundation document describing how their hub will work, where you actually see each industry, each producer, how they all fit together, how the pipelines fit together. Some of those pipelines already exist, apparently. I have to confess, I didn't know that. So it is a natural hub. There's no question.
This is Saeed Begheri. I serve as Technology Transfer Manager for University of Waterloo. In one of your slides, you had shown a Toyota that had a range of over 1,300 kilometers, and it took 5 minutes to refuel. Can you provide a cost analysis on state-of-the-art hydrogen production, comparing it to diesel?
Well,
at the end of the day,
yep. I can jump in very quickly with an answer, and it depends on your jurisdiction. Some jurisdictions, like in California, are making it easy for producers to supply hydrogen that will compete with gasoline and diesel. We're not there yet here in Ontario. I'm not even sure we're there in Quebec either, even though their electricity is much cheaper than ours per kilowatt. So, but if you project forward, when you start building electrolyzers at scale, then the cost will come down. And so again, unfortunately, it's this chicken and egg thing we keep talking about. If you're going to build a large
rebates,
it could be a rebate. It could just be a capital cost allowance of some sort that the government puts in place, so that if you build an electrolyzer, you get some help from the government for that initial investment, and that way you can sell the hydrogen at prices that will compete. But it's a mosaic right across North America. Now in Europe, it's a different story, right? Because they pay much more for their electricity. They pay much more for their natural gas.
Isn't
I'm
that
sorry?
a bottleneck? So if a fleet owner cannot predict or know for sure the cost of refueling, isn't that seen as a bottleneck?
Well, have you seen gasoline prices? They've kind of doubled in a year. So I hate to be mischievous, but if you're looking at something like fueling costs and saying, well, I want to project forward and know what my price will be in 10 years, you can't do that. It's a market. When you create a market, it's self-sustaining. What we can do in the early days is make sure that there is an economically viable market, and that it is an option that people can use. And I think, but in terms of being able to give people a price guarantee over time, there might be a big supplier, like for instance, let's Atura represented here. I'm sure that Atura, in order to attract a customer, will probably give them a rate going forward, for whether it's 2 or 5 years. But once you produce a thriving hydrogen economy, the price will vary. from place to place and from time to time.
Thank you, Bob. I appreciate your presentation. I appreciate your time and effort. I guess we'll be seeing you in a few minutes.
A few hours, I hope.
Panel.
A few hours.
Okay. Okay, the last
Thank
panel.
you.
But anyway, thank you very much, Bob.
Thank you.
Thanks for your introduction and presentation of these hydrogen economy issues. Okay, so we're gonna we have our next panel, which is going to be moderated by Richard Jackson, which is here. And it's going to be focusing on the issues of fuel cells and sustainable mobility. So if the panelists can please come up to the table. Excellent. Thank you. Okay, Richard, the floor is yours.
It's even there, so you could see the comfort monitors.
Good morning. I'm Dick Jackson, and I'm associated here with Earth and Environmental Sciences, and I'm a fellow with Geothermal Engineering in Ottawa. I want to introduce you to our four panelists. Antimo Graziano will speak first, followed by Jeff Gostick, followed by Samane Shalgaldi, and finally Professor Shangong Li will be giving his presentation. So the presentations will be roughly about 15 minutes, and will please hold your questions and answers for the session afterwards, when we're going to get into a few things in greater detail. So I'd like to invite Antimo Graziano to lead off.
Thank you. Thank you very much.
Oh, I should say that Antimo, just in case, is with Cummins here in Mississauga, and is Cummins Hydrogenics, and is a specialist in bipolar plate composites and gasket seals engineering. Sorry.
Thank you. Thank you for the introduction. Okay. I guess everybody can hear me? Okay. Okay. Thank you. Okay, good morning, everybody. It's a pleasure for me here, and I'm very happy to meet you all and learn about what you do, what's your interest. My talk today is focused on practical application of fuel cells in the transportation sector specifically. So as we are all aware of the greenhouse gas emissions problem, and if you have a look at the table up there, there are two interesting things to notice, that the amount of CO2 emitted in the atmosphere in 1950 was 5 billion metric tons, and then 7 times that in today. So imagine how much more we have compared to the past. One big reason is because the world population is increasing a lot, and as you can see from 2050 to now, we've increased the world population from 2.5 billion to 8. And also that's another reason is that, of course, many sectors, many industrial sectors are growing, and as you can see among transportation, residential, so all that contribute to CO2 emissions. If we look specifically at the transportation to see which part contributes the most to CO2 emissions, you can see very well that the passenger car is the one that makes up the most, because we have 41% of CO2 emitted in the atmosphere by passenger car. And then you can see all the other transportation that also include marine and aviation. So what could be one of the ways of mitigating this problem and solving it eventually? One could be the hydrogen fuel cell. So we can use hydrogen fuel cells in all those transportation sectors that you saw earlier. And one example here is that what happens if we use it in the passenger car? So imagine replacing your internal combustion engine with an hydrogen fuel cell. now the fuel cell serves you as the motor, as the engine. What you have as your inlet, as your gas, is not your regular gasoline, but it's hydrogen. And you also need air, that I will explain later. So imagine now, if you're using hydrogen and you're just producing electricity to get your car going, you will have 0 CO2 emissions eventually. And that's a great way of solving the CO2 emissions problem. Just very briefly to show you how a hydrogen fuel cell works, and then my colleagues will talk more specifically about that. So just roughly, in order for you to create electricity, you need an anode and a cathode, and you need a flow of electrons going from one side to another. As I said, your gas, your inputs are hydrogen and air, but specifically we're needing oxygen from the air. So you inject hydrogen from one side, from the cathode side, as you can see from up there. And then the hydrogen goes at the center, which is called proton exchange membrane. It splits into hydrogen ions and the electrons. The electrons go up and flow to the other side, which is called cathode, while the hydrogen protons, the ions, flow through the membrane. So now at the other side, you have electrons that emit the hydrogen ions. But there is also oxygen coming in, and therefore you have the second reaction that gives you water. Water is one of your byproducts that you have to eliminate together with heat. So that's how you produce electricity with hydrogen and oxygen, a very green way. Now, let's look at more specifically at the market. We were talking about transportation and how the fuel cell can mitigate the problem of CO2 emissions in transportation. So this slide is showing you what's happening to the passenger cars with the fuel cell. So it's interesting to see here. I've divided it, in countries, or also the continent Europe, to see how they're doing. So in 2014, there was the very first hydrogen fuel cell car in the market, which is a Toyota Mirai. It was sold in Japan. Here at the bottom, you see for each country how well they're doing in terms of application availability. So one circle means few cars sold in that country. Multiple circles means many cars. So as you can see, Japan and US are doing very well. Specifically, the US reported 1,700 Toyota Mirai sold in 2017 and 2018. So the market, especially for the passenger cars, is growing. It's very exciting to see that one day we'll be able to decarbonize the world, and that's a great thing. If we look at the truck market, so as you well know, the trucks are divided in 3 main categories: the light duty, medium duty, and heavy duty. So in terms of status of the application, so the hydrogen fuel cell trucks, we can see that the light duty and the medium duty are more on the demonstration stage, at the demonstration stage. That means that at a small scale, companies were able to test and provide evidence that these type of fuel cell in that type of truck is working well. So we could actually have products available in the market. Whereas regarding the heavy-duty trucks, we're still at the prototype stage, which means that we're still trying to get to product development. So in terms of bus market, here we're growing there too. As you can see, China and Europe are doing very well. They had some, also US had some, like a few projects that sponsored the growth of hydrogen fuel cell buses. And here I'm also showing the brands that are releasing hydrogen fuel cell buses. And in China, we have now many. As of 2018, we see that there were 200 operating fuel cell buses in the country. You can imagine how it's growing now, 4 years later. Lastly, in terms of like fuel cell applications in the transportation, I want to show you what's happening in the airplanes, for the airplanes. So for the airplanes, it's very interesting to know that late 2020, there was the very first plane, hydrogen fuel cell plane, that was tested in UK. So this company, Zero Avia, which is a leader in decarbonization in the aviation, launched or tested, I would say, their first hydrogen fuel cell plane in late 2020 at their R&D facility in the UK. And it worked very well. They had a successful 8-minute flight. So it's pretty exciting to know that soon we'll have also airplanes that work on fuel cells, and therefore 0 CO2 emissions. Specifically, we're expecting that by 2023, we see some 10 to 20 seats, 500-mile range planes available in the market. And then we go through 2027, all the way to 2040, when we expect to see 200 seats plus planes available in the market. So it's pretty encouraging to see how the hydrogen fuel cell technology is growing, it's evolving in the market. Here we're looking at some pros and cons, because when you have a hydrogen fuel cell vehicle, for example, so a vehicle works on hydrogen fuel cell, it comes with pros and cons. So we have to be aware of those. And for pros, you can imagine already, we have a green power source for the hydrogen, long range. Also, the fueling time is short. So compared to a battery car, it takes a very little time for you to get your hydrogen in the car compared to a battery car. So it's a good advantage. And also, of course, there is no greenhouse gas emissions, among others. For cons, we have that high costs. Of course, the new cars cost a lot of money compared to conventional cars. And also we have lack of infrastructure, not only because, as you can imagine, there are very few hydrogen stations around, so you won't be able to get your hydrogen in the car so often as you do with your regular car. And also producing the hydrogen is also a challenge, not just because we don't have much infrastructure, but also because it might be costly, and not necessarily the ways of producing hydrogen are always green. And we can talk about that later. But let me dig more into the specific of the challenges for deploying hydrogen fuel cells, especially divided by main areas, I would say. So if we look at the environmental challenge, we can see that, of course, the environmental challenge is that, as I said before, not always you produce hydrogen in a green way. As you know, only green hydrogen is produced in a green way because you have electricity coming to the electrolyzer that is coming from renewable resources like wind energy. So somehow, when you produce hydrogen, you still emit CO2, so that's a concern. Also, hydrogen can be highly flammable. And you can imagine, the person that goes and buys the car also feels a little bit concerned about having hydrogen in the tank instead of your regular gasoline. And that brings me to social awareness, so social challenges. And of course, the driver is also more concerned about accident risk having hydrogen in your tank. Economic challenge. The hydrogen storage is costly. As you know, there are many costs involved in the storage of hydrogen. Infrastructure, as I said before, but also the fact that in the fuel cell, we use a precious metal in one of the components of the fuel cell, and that also is expensive. Legal challenge is related to unclear regulatory frameworks, so it's not very clear as of now. That's why there's also a challenge related to legal. And we have, of course, we have a technical challenge related to performance and durability. So let me talk about that more specifically. As many of you, I'm sure, know that hydrogen fuel cell is, of course, is a cell. Therefore, there are many. Once you have a cell that is made of these components, so the single cell over here, then you have to put multiple cells together, one on top of the other, to have a stack. Now, if we look at what one single cell is made of, you have the membrane, which is the proton exchange membrane that I mentioned before at the center. Then you have two gas diffusion layers. Then you have a seal. And then you have a bipolar plate. Now, when you look at these components in terms of cost, like what contributes the most to the cost of the fuel cell and the weight, you know that the two important components are bipolar plate and MEA. That's why let's talk about the challenges that we're facing in that. And since I come from an industry, I would like you to see what are the requirements that the industry is putting out there. So we're expecting some technical properties, I would say, in order for us to be happy, and therefore the hydrogen fuel cell can be deployed. So if we look at the bipolar plate, which at the top I put the main functions of the bipolar plate in the fuel cell, which is distributing the gas uniformly in your cell, dissipate the reaction heat also uniformly, and also bipolar plate is responsible for supporting the MEA, and because you have to sustain the clamping pressure when your fuel cell is in operation mode. Here on this column, I put on the left the main properties that we're interested in to see in a bipolar plate. At the center, you see the 2025 DOE target. That means the Department of Energy is telling us by 2025, for each of those properties, we have to reach those values, at least those values. And on the right, you see what is that properties, what is the function that property is related to. So as you can see, electrical conductivity is pretty important, as well as thermal conductivity. And we also have flexural strength is important because, as I said, bipolar plate needs to support the MEA as well. And here you can have an understanding of the hours, like for how many hours we want the bipolar plate to work so that the fuel cell works well, it doesn't die, for at least 8,000 hours, the weight and the cost of a bipolar plate. These I should mention is all related to passenger car application as an example. These are the properties we expect for a passenger car application for bipolar plate. And lastly, we want to see what do we expect from a MEA point of view. So the MEA is responsible for providing the reaction site for generating the electricity. As you saw before, the hydrogen, the oxygen react, and they react at the MEA site. So there is an active site where the reaction occurs. Also, MEA is responsible for optimizing the transfer of your products and the reactants. And let's see what properties are important. Properties are important in the MEA for the passenger car. So we have once again, I'm showing what the DOE expects by the 2025. So I'm showing the electrical resistance, which is directly correlated to electrical current conduction. The performance in terms of power supply, your platinum catalyst loading, as I was talking before, there's a precious metal in the MEA, and also your lifespan and the cost of the MEA US dollar per kilowatt of power produced. So with that, I'd like to thank you, everybody, and of course we'll leave questions at the end. Thank you.
Thank you, Timo. As Timo mentioned, we'll defer questions to the end, and then we'll open it up then. Our next speaker is Jeff Kostic from Department of Chemical Engineering here at the University of Waterloo. Jeff was previously worked with as a research engineer at Tech Resources, and is going to speak to us now on fuel cells and the future of sustainable mobility.
Okay, thanks. So good morning, everybody. My name is Jeff Kostic. I'm a professor in chemical engineering, and my lab is called the Porous Materials Engineering and Analysis Lab, and we look at porous materials in general, but we tend to look at fuel cell and battery electrodes a lot because they're porous and they're very interesting. So today I'm going to talk about a project that we did. I had one PhD student working on this, and I thought it would be an interesting thing to give you an overview of what he worked on since it was relevant, and it ties in nicely with Timo's talk. So the project was making catalysts that had no platinum or no platinum group metals or no precious metals in them so that they were much, much cheaper. Replacing platinum with nothing. So I always like to start these general talks with these two graphics. This is the annual temperature. So each time you go around the loop, it's January, February, March. This is the average temperature of that month over the last 150 years. And when you're at the center, that's the average temperature. And then as the circle gets wider, the average temperature is getting hotter. I'll run it again, actually, if I'm able to. So what you see here is that the spiral is it's wider and wider. The average temperature is increasing, and it's a really great visualization of this climate spiraling out of control, perhaps. You can download this graphic from this website here, climate-lab-book.ac.uk, and they probably get an updated one that says more than just 2017 on it. And there's another version of this where it looks, instead of at the temperature, it looks like the Arctic sea ice volume per year, dating back to 1990 when they started to collect data. And you can see that the amount of sea ice, it's a little bit off-center because in the summer there's less ice than in the winter and so on. But look what happens in the last 10 or 15 years to the volume of sea ice. And it really gives you the idea of something circling the drain. Very, very visual. It makes it pretty obvious that we have to, do something. Things are changing, okay, in our environment. Okay, so with that in mind, let's talk about fuel cells. All right, so, and Timo talked about fuel cells, and I have another graphic here for us. This is a fuel cell stack, a cartoon of a fuel cell stack. And it's many, many cells in a row. Each one produces about 1 volt, and then all those voltages add up to give you the power that you need. And inside, the black component is the gas diffusion layer that has the catalyst on it. And I'm going to zoom in on that. That's I guess, the heart of the fuel cell. So here's a cross-section of that thing. The green is the polymer electrolyte membrane, and then you can see the little green and yellow circle, little particles that I've drawn there. That's the catalyst layer, and it's sprayed onto the membrane like a paint, and that's where all the platinum is. So when you're talking about porous materials, that layer is porous, and looking in at the properties and the structures of that layer is what we're interested in this project. This picture on the bottom is an SEM, a scanning electron microscope picture of a catalyst layer. You can see all these little globules and the pores as well. So the transport phenomena occurs in the void space of the gases. Electrons and ions travel through the solid phase. And I'm going to zoom in on that picture in the next slide. So here we have that SEM, and here's a cartoon of what it looks like. So we have in this layer, there are carbon particles that are decorated with platinum dots, and the platinum dots are where the chemical reaction happens, that catalyzes the reaction. Those particles agglomerate together, electrostatic attraction or whatever, and they're glued together by a polymer called Nafion or ionomer. Nafion's a brand name. It's called an ionomer, which is an ion-conducting polymer to let the ions get out to the catalyst site. And then those things kind of aggregate into 1 to 3 micron size aggregates. So you can see this picture on the right. Hopefully that makes sense, and you can see how the correlation. So you can see the aggregates, and you can even see the little spherical particles, and inside those things is where this platinum is. Okay, so that's the cartoon I'm going to go with. Now here is a small progression of the last, 20 or 30 years of fuel cell research. So when they were first doing these things in the 90s, they were like, well, let's just use big platinum, pure platinum particles, platinum black. And 40 milligrams of platinum per centimeter squared was basically how much platinum they were putting in there. And it was obviously very expensive. It would be something on the order of $100,000 per car if you were to actually go ahead and do that. So they had to bring that cost down. So it doesn't take Einstein-level genius to think, well, maybe we don't need the inside of that particle to be platinum, since only the outside is where the reaction happens. So they took carbon particles and they decorated the outside with platinum dots, and that brings the platinum down by an order of magnitude or more. So now you're at $10,000 a car. Now, moving forward, we're looking at ways to use even less platinum, like ultra-low loading platinum. Maybe you could be at $1,000 a car. And the cartoon I've drawn there is using less platinum dots. Maybe you replace the platinum with something else, like cobalt or alloys or whatever. Or also, you can make your catalyst layer thinner, but more effective. It's also a way of reducing the platinum per meter squared. And ultimately, moving forward in the 2020s and onwards, what if we could just do it with no platinum? And then it would be $0 per car, essentially. Or maybe $100 if for whatever you got to process these things. But essentially a negligible cost. So how do you do that? You take all the platinum off these spheres. Basically, there was, I guess you would say, a discovery that if you were to take a graphene sheet and take out one of the carbons and replace it with iron, that has electrocatalytic activity towards oxygen reduction. So that was very exciting because iron's super cheap. So all you have to do is make your graphene lattice and then find a way to insert these irons into the lattice like this. And if you can make these carbon particles out of this material, then you would have electrocatalytically active particles. So that's the idea. Okay, so people are of course chasing after this idea, and we thought, well, we like to look at structure. of porous catalyst layers, less so at catalysts. So we worked with a collaborator who made these catalysts for us. And we made a catalyst layer and did some testing of these. One thing I'll say is that because this site is not as active as platinum, it's okay, but it's not even close. So basically, you have to make up for it by using a lot more sites. So what ends up happening is that the catalyst layer has to be quite thick because you got to put a lot of active sites per square meter, so that you have to make it pretty thick for it to work. So that you end up having a lot of transport phenomena problems, getting the gases in, getting the electrons and the protons in and out. So that's where our expertise in porous materials comes in. Yeah, so the active sites are far less active, right. So we thought, let's try making a custom catalyst layer with this technique called electrospraying. So it's basically you take your catalyst particles and they're dispersed in a solvent, and you shoot them out of a syringe, but you apply a 10,000 volt difference between the syringe and the collector plate, and it causes the droplets to blow apart into a really fine mist. Here's a cartoon. So as the droplet emerges, it's highly positively charged because of this power supply. As the solvent evaporates, you get the charges become condensed, and then they burst apart into tiny little droplets. They disintegrate, called Coulombic explosion, which is kind of a cool term. And that happens repeatedly during the travel of those droplets from the needle to the collector, so you end up with really fine and interesting particles. And you can really vary this process by changing the solvent composition and the flow rates and the voltages, so you can get a lot of interesting structures. I'll just say one thing that this offers that the traditional method doesn't is the solvent evaporates in the air before it even hits the collector, as opposed to the traditional technique. So we get this thicker and more porous layer landing on the collector, as opposed to the normal technique where it's wet on the membrane and then the solvent evaporates and you get kind of like a consolidated mud. So we thought, well, maybe this technique could make it a more fluffy and higher transport rates for us. So here's a snapshot of varying the flow rate of the stuff being ejected from the needle and the distance the needle was to the collector, just to see. I think there's a very wide difference between the morphologies that you're able to create, which was nice. That was the point. It's highly tunable. And so the effective diffusion coefficient, that is the ability of gas to diffuse through this layer to get to the reaction sites. Higher is better. So you can see that it does vary with the flow rate, and it does vary with the distance that the needle is to the collector, so that we were able to not only have different structures, but ultimately the transport properties were better or different. So the top row there, each one of these pictures corresponds to one of the dots on that graph. So another thing we did is we plotted our data. This is the porosity, which is just kind of how, the openness of the pore space on the x-axis, and tortuosity. So higher is bad for tortuosity. It's just like a metric that we use to describe the effective gas diffusion. So low is good. So ours are the orange dots. The blue, the solid dots, pardon me. The open dots are the ones from literature. You can see we were able to get our tortuosity way lower, and we could have our porosity much higher, and we're down in the bottom right corner of this curve. So it looked very promising. So when we did some performance tests with our different materials, different amounts of naphthalene, we also varied. We varied the composition as well as the production parameters, and it worked. So you can see what's interesting here, I guess, is that there was an optimum. So if there was too much naphthalene, too much of that ionomeric binder, it didn't perform well. And if there was not enough, it didn't perform well. But there was a sweet spot right in the middle, which was that red line, where we were able to get a good cohesion of the particles without overcoating them with this polymer. But the target for the near term, not even the long term, but the near term performance targets for fuel cells is way up there, that green dot. And so we were not even close with this catalyst layer. So even though it had good transport properties for gas diffusion, we must have hindered other properties. So we did some modeling. I'll just quickly show you. We modeled here's the model domain. We modeled the ion transport, electron transport, all the various multiphysics processes that are occurring in the cell. And with this model, we're like, okay, well, maybe we can start playing with the different parameters to see if there's some combination that we can get to give us the right performance. So I'll say that the dots are the experimental data and the lines is the model. So we calibrated it into the model and validated that to the data that the model worked well. And then once you had this model running, then you can play with all your parameters, like the amount of naphthalene and the thickness and the porosity and so on. And we did see we could get a whole wide range of performances. And in the end, we had to play some imaginary games, like what happens if we So if we improve the structure so that we have more surface area. So that's the, the baseline is the one I showed you. It says base. So we could improve the structure. We can get a little bit closer to that interim target. What if we could somehow improve the electrical conductivity of the layer? So it looks like maybe the layer is so thick and the agglomerates are not contacting very well. So if we could somehow improve that, we could get even closer. And lastly, if we could improve the intrinsic catalytic activity of those iron sites, we could match the interim target there. And I'm almost done. So ultimately, it looks like if we wanted to get to the DOE long-term target, which you'll notice is at a much higher current density than the interim target, it's at 1.5 amps per centimeter squared instead of 0.5. So really pushing out, out to the right and high is good here. So we want to get up to the top right corner of this graph for best performance. So basically, it's going to require a combination of optimized structure, improved electrical conductivity, and boosted catalyst activity. So lots of work left to do in this area. And in conclusion, so improving the structure helps, but it's not enough. And basically, we need to make the catalysts more active or make more sites for these non-platinum base metal catalysts to work. And I'd like to thank the group as well. Young, on the very, very far end there, Young Kim was the one who did most of this work. So thank you very much.
Thank you, Jeff. Our third speaker is Samane Chalgaldi from the University de Quebec à Trois-Rivières, who is also an adjunct professor here at University of Waterloo. And she has also worked as a research scientist with Cummins Hydrogenics.
Thank you so much. I'm super happy to be here with you guys today. And a little bit about myself. I was working here at the University of Waterloo for 4 years with Dr. Lee at Green Energy Lab. After that, I joined Hydrogenics, working on different PEM electrolyzer and fuel cell project, focusing on membrane electrode assembly. And after that, January 2021, I joined University of Quebec at Trois-Rivières, and I got Canada Research Chair Tier 2 on fuel cell and electrolyzer. So today I'm going to talk about membrane electrode assembly for proton exchange membrane fuel cell, but I'm going to talk about a little bit about electrolyzer as well. So I want to use this opportunity and introduce our school as well. We are located in Trois-Rivières, beautiful city between Montreal and Quebec City. We are 1 hour, we are in the distance of 1 hour drive from Montreal. In our school, we are in a medium-sized university. We have almost more than 40,000 students in our school, and we have 55 research units, including Hydrogen Research Institute. So Hydrogen Research Institute is founded actually in 1994, and it's the first institute in whole North America focusing on hydrogen. And today we are working on different hydrogen projects: storage, production, fuel cell, safety, and management. Besides Hydrogen Research Institute, we have another institute, Institute of Innovation in Eco-Material, Eco-Products, and Eco-Energy-based Biomass. So if you look at this image here, you see that if you guys are familiar with fuel cell or battery, you see the roll-to-roll machine. So we previously in this institute, we was focusing on pulp and paper industry. But now we are switching to more bringing those material in the energy sector, because there are a lot of knowledge that we can leverage from pulp and paper to the energy that I'm going to talk about it today as well. So this is my research group. Thanks to different partners, we have different projects. We have a project with Cummins Hydrogenics, and we are focusing on different catalysts, precious metal catalysts, developing of MEA, basically for PEM electrolyzer, PEM fuel cell, and a little bit battery. So Antimo and Jeff talk about global warming, and I'm saving a little bit time. We all know about energy consumption is increasing and global warming is here, and we need to address. If you look at this graph, we see that CO2 emission for 2019, it was around 60 gigaton, that it has 7% increase from 2018. And transportation has almost 40% role in this graph. If I want to talk about the advantages of fuel cell, PEM fuel cell, we can say it's environmental friendly, it's direct energy conversion, high efficiency, and we can operate it at low temperature. But think about it, even if we have a perfect fuel cell today, we need still to address three main things: production, infrastructure, and safety, that my colleagues are going to talk about it in the next panel. Back to the fuel cell, as my colleague talked about it, if you look at it like that, it's like all electrochemical cell, we have a electrolyte, catalyst layer, fuel, and oxidant, and simple electrochemical reaction. So it's very simple. We have hydrogen from one side, oxygen from the other side. Overall reaction, we have electricity, water, and heat. It means that from exhaust of our car, train, truck, we have a clean water. But what are the challenges? Why we are still dealing with that, and we need to address a couple of things. So if we want to talk about challenges, we need to deal with cost, performance, and durability. In this stage today, we can talk about two at the same time. We can address two at the same time, but not three together. For example, we can make a stack that is very good performance, very durable, but it's so expensive because we need to put a lot of high precious metal inside. And if we want to get rid of the cost, then we can use non-precious metal, so we can have high performance, cheap, but it's not durable. So we need to think about it in a way that we address all these three together. So here we see that the stack, one of the hydrogenic stack, fuel cell stack, if we look at it as a black box, but inside of that we have hundreds of these cells inside of one stack. So we have, in the middle, we have membrane electrode assembly, that is a heart or core component of fuel cell, that is a place that the reaction happens. So we have membrane and two catalyst layer, anode side and cathode side. So, and then we have gas diffusion layer. So some people, if you go back to the literature, some people call it 3-layer. It means that electrolyte and catalyst layer, and if we call it 5-layer, and then we bring the gas diffusion layer together as a MEA. And then we have bipolar plate. So if this image shows a half of our MEA. So we have our membrane, then we have our catalyst layer, gas diffusion layer. Okay, so if we consider this as anode, then we have the same structure on the cathode side or anode side, but with different loading, because we need to have more catalyst in the cathode, because cathode is the sluggish reaction happen over there. If you see, we have a carbon, platinum, ionomer, and specifically pore. It means that we need to construct our catalyst layer in a way that we have electrical conductivity, proton conductivity, and right proper porosity, because our reactor needs to reach three-phase boundary for the reaction happen. So if we talk about our membrane, so basically the state of the art of our membrane is perfluorosulfonic acid. But today we have different kind of this material in the market. We have short side chain, long side chain. They are responsible for proton conductivity, and they need to insulate the electron and also separate the gases, separate the whole cell between hydrogen and oxygen. So basically they need to have high proton conductivity, good insulating properties, and mechanically and chemically stable. However, when we have those membrane inside our cell, there are three main degradation modes that may happen in our cell. That is mechanical, thermal, and chemical, that we need to address this in order to prevent the degradation inside our fuel cell. So I put one of the postdoc here working on the degradation of membrane in my group, especially on electrolyzer side. And also we did, with Dr. Lee, we did also a lot of work on comparing the long side chain and short side chain of membrane under different operational conditions. For example, we need to know if we want to run our stack in high temperature, what kind of membrane we need to select. We cannot select one membrane for all operational conditions that we have. So we need to clarify the operational condition that we have and then select the component of our stack for both fuel cell and electrolyzer. Then we have our catalyst layer. So basically, our catalyst layer accelerates the reaction, provide a flow path for fuel and oxidant, and also provide a path for proton and electron transport. So it means that we need to have enough amount of carbon with good connection because we need electrical conductivity. We need to have right amount of ionomer because we need to have proton conductivity, and then right porosity because our fuel needs to reach the three-phase boundary from these pores. So if you have a very dense catalyst layer, then we have problem. So we are still working to address this, to find the right amount of ionomer, right amount of support, and right amount of porosity for our catalyst layer. On the other hand, catalyst layer also goes to degrade inside our stack. So it may happen, platinum dissolution may happen inside our stack, or platinum detachment, carbon corrosion, or ionomer decomposition. So there are a lot of things that we can do in order to address. For example, we can use, instead of carbon, we can use metal oxide in order to have a better bond with platinum, and also bring down the degradation mode. However, then we need to think about the electrical conductivity of our support, because if we change carbon to metal oxide, then we have a problem. So what we did, we produce our platinum, we produce shaped platinum, like cubic shaped platinum, or we change the support to graphene or mix of graphene with different material in order to address this problem. And also we produce the fiber-shaped platinum in order to have a better connection between the, have higher surface area from the tube to the support in order to prevent degradation. Also, we work a lot on the ionomer because ionomer also play a very important role, and people are not talking about that much. So if we have high amount of ionomer inside our stack, it closes the pores, and we have good proton conductivity, but electrical conductivity is, we need to sacrifice electrical conductivity. So we need to select right ionomer for our stack. We have different kind of ionomer inside our, we have different kind of ionomer in the market nowadays. Again, the state of the art is perfluorosulfonic acid, that we have short side chain, long side chain. When I'm talking about short side chain, it means that we have more sulfonic acid in terms of, in compared to carbon fluorine base, and it means that we have more water retention inside our stack. So it means that, so this is one of the work that we did, and compare long side chain and short side chain inside the stack, and we find out that, okay, it seems that when we use shorter side chain ionomer, the cell performance is not that much sensitive to the amount of ionomer that we are applying in compared to the long side chain. And also we think about it, okay, what is the role of ionomer in durability of our catalyst layer? Because we all the time talk about the role of catalyst, but not ionomer. So we did this research and compare, you know, we put our stack on accelerating stress test, and we find out the ionomer also has an important role on the durability of our stack. So this work also, it clearly shows that if we change the operational condition, for example, if we imagine if you have a stack and we want to run it with a low humidity and low flow of reactant, okay? So we cannot select one ionomer, the ionomer that we want to run it for the stack for high humidity. Because if we have high humidity inside our stack, and if we select short side chain ionomer, then our cell is going to the flooding. So we have flooding inside our stack. So we need to get rid of the water that we have and water that we generate, you know? So we need to use longer side chain ionomer. So again, the component that we are selecting for our stack, it really needs to match the operational condition. And also we did a work on gradient type of ionomer in order to bring down the amount of ionomer that we have inside fuel cells, and we prepare different MEA, and we find out that if we have more ionomer near three-phase boundary, near membrane, we can get better performance, and we save good amount of ionomer in terms of cost. But in terms of mass production, we need to make two kind of ink, and we add one step in the production line in terms of the mass production for industry. Then we have gas diffusion layers. So if we are bringing now those gas diffusion layer inside our MEA, and we call it 5 layers, so we have macroporous and microporous, that is basically carbon nanofiber and a carbon nanoparticle on top. And the gas diffusion layer, it provides a flow path for reactant supply, and also for a flow path for our electron and heat. Also, we did a lot of work. We applied graphene instead of particle in order to have a better water retention inside our porous transport layer in order to develop a stack specifically for dry condition and very low humidity. And we got an excellent result on that. So, okay, now we talk about catalyst layer, membrane, and ionomer. We talk about the component, but it's really, really important that we know how we make our MEA, okay? So when we are mixing our catalyst layer with ionomer and solvent, how we need to deposit that catalyst layer inside our membrane or GDL in order to have right porosity. Normally, we have 3 main methods for making MEA. When we are putting the catalyst on our substrate, that's called GDE, or a catalyst-coated substrate, or when we deposit directly on the membrane and also on the inert substrate and then transfer it to the membrane. We have also new method that names DMD, that we coat membrane on the catalyst layer on the GDL. So these are also play an important role, that we can increase the platinum utilization on the on our stack. Sorry, we don't have time, so I'm not gonna. So this work was really interesting, published in Electrochemical Acta. If you guys are interested, we developed a fuel cell that it was not sensible to the flow of reactant. It means that we reached to the stage that if you have high flow, medium flow, or low flow, we got the same performance for our fuel cell. And now, I did talk about a lot of components that you see, that we have carbon-based catalyst, we have a carbon-based gas diffusion layer, and we have our bipolar plate that is graphite. So all of this carbon material comes from petroleum-based material, and we have also hydrofluoric carbon from our membrane and ionomer, that at the end of the day, in order to produce the green technology, we need to get rid of that. So part of my group also, we are focusing on bringing this biomass and biomaterial to fuel cell and electrolyzer technology. It means that we want to produce a bio-based carbon material with superior properties and apply it in the fuel cell and electrolyzer. So these are some of the results that we got: different shape of carbon from biomass. And thank you so much for listening.
Thank you, Samani. Just one quick question. Several of you have referred to DOE. I presume that's U.S. Department of Energy. Okay. Our final speaker this morning, before we take a short break, and then we'll come back for questions and answers, including folks out there in the Zoom sphere. Our final speaker is Dr. Shangro Li, who's professor of mechanical and mechatronics engineering here at the University of Waterloo.
Okay, wait. Thank you very much. And I know I'm the one standing between you and the break, so I try to be a bit quick. So that our colleague talked about the catalyst MEAs. These are the very important key component in fuel cells. So I'm looking on a little more practical application side that I'm looking at a stack, basically. Now, just in general, that for transportation application, fuel cell technology is kind of getting the stage, early stage of commercialization. Its performance considered to be good enough, and the cost and durability are reasonably acceptable, but need further improvement. So think in this way. And if you're looking on the market potential that our colleague from Kami talked about earlier, I'm just going to look more specific. That if you're looking at the US, really you could think about North America, that by end of 2019, less than 10,000 fuel cell vehicles in the market or so. But if you're looking on their roadmap, that I like to look at 2030, less than 10 years away, they want to reach about over 5 million fuel cell vehicles in the market. Since Canada, US combined together, North America has annual new vehicle sale about 15 million. So which really means about 1/3 of new vehicles will be fuel cell vehicles. And so that gives you the scale of market and potential profit margin for our industrial colleagues here. So if we look at the fuel cell power systems, basically oh, I see this, okay. That's one of the problems with Microsoft PowerPoint, that you made on one computer, but when you present in another computer, the color scheme seems to be all changes. But anyway, so this was supposed to be the fuel cell stack, and it needs a hydrogen air supply, and it produces electrical power as well as the waste heat and water, so that you have, for waste heat management, you have a cooling system, and for water management, then you go through kind of exhaust system, the water being removed, so that you need to manage the electricity collection, the management of the waste heat and the water for the stack level. So if you look at a typical stack, the cross-section, could be square or could be rectangle, depends on the design and depends on the application you have in mind. And so that if you look at the key components, membrane electrode assembly or MEAs, then there's this so-called bipolar plate, which has flow channel on the surface that distributes the reactant gas over the fuel cell surface, at the same time remove the product water as well as the heat from the fuel cell reaction. So that if you're looking on a little bit older statistics, that for the cost breaking down, assuming you make 500,000 units per year, and we're talking about 15 million per year in North America alone, and for vehicles, so that if you're looking at this whole thing is for MEAs, so they are over 50% of the cost, and bipolar plate is about 30%, the second most costly component in fuel cell stack. But if you're looking on the volume, the size, and weight, the bipolar plate, it's over 50%. Actually, could be as high as 80% of the size and weight for a stack, depends on how you design it. So that for mobile transport application, whether it's for vehicles, ground vehicles, or ocean ship, marine application, or aviations, you want to make a lightweight. So the place you can reduce the cost or increase the power density is the bipolar plate. And now if you look on the stack design, basically that you think MEAs is sandwiched in between a two flow plate, or we call bipolar plate. The MEA is very thin, typically less than 1 millimeter thick, while the flow channel is in the order of 1 millimeter by 1 millimeter cross section. The bipolar plate traditionally using graphite plates, like 5-6 millimeter thick. So you see the MEA less than 1 millimeter, and each plate is like a 5 to 6 millimeter thick. So the volume, size, and weight coming in from the bipolar plate. And we also mentioned that the fuel cell generate waste heat, so that this is the cooling plate. So the coolant flow in these flow channels to take the heat away. So that this forms one kind of repeating unit in a stack, and in order to drive a vehicle, you need like a 300-400 of these repeating units putting together in a stack. Now, if you have one person, it's great. You can work day and night and at your pleasure. But if you have a group of people, you're trying to organize, make them work in the same direction, not as Brownian motion, right? So in a stack, when you have 300-400 cells together, some cells work really hard. Of course, they get fatigued and breaking down first, while the others who take an easy, easy flight, then they will be having a longer, lifetime. But the trouble is, they're all in serious connection. So if one cell breaking down, the whole stack breaking down. So how you can make the entire stack, everyone working at the same hardness level, but no one working harder than others. So everybody had the same, lifetime. So that's the kind of tricky thing. Now, if you're looking on these flow channels, you could think in two fundamental design. One is the flow coming in, these flow channels parallel to each other over the fuel cell surface. Or alternatively, you could think of these channels being collected in series. So the most of flow channels in practice are kind of combination of the two. It's a combination or hybrid of parallel and series connection. Say some region in parallel, some region in series. And that will depend on how large the cell area is, particular application, workload, and basic load profiles. So there are many things to consider. Then, of course, there are others trying to using like a biomimetic kind of design. Those look very nice, but practically, to be honest, no one really using. It's academic research. Okay? And then now, if you look on the stack, there are other things to consider, because we have hydrogen coming in, air coming in, and that need to exit the stack. So they could exit in one end and leaving at the other end. They're entering and leaving the same end, or they could come in by the end but leaving the middle. So you can look at a variety of things. You can look at about 27 different combinations of it. And some is better than others. But for example, one of the things that ideally you want to make this parameter equal to 0, meaning cell-to-cell variation is 0. And the best one we're finding that you have a 2 inlet, 1 exit. But the issue is that now traditionally you have 1 inlet, 1 exit to control, but now you have become 3. Then there's actual control, actual materials, actual labor. So that you get something, you lose something. In engineering, we call optimization. Really, in a different angle, we're really compromising it. Because you have to pay for every gain you get, and you're trying to equalize it, basically. Then if you look in historical development in early days, for example, Ballard Power Systems in Vancouver, then when people say, hey, instead of using graphite, they could use metallic bipolar plate and make very, very thin plate, because metallic have strong mechanical strength and almost 0 permeability for gas to leak through between hydrogen and oxygen channels. So that you see that the power density from about 1,000 jump to over 3,000. So that you have to think about materials, manufacturing, design altogether in order to achieve what you need for the performance. So that's where we want to say that material is important, design important, and another thing often not being talked about in research circle, but to industry, that really important to make it in high volume. Whenever you can scale up to volume production, the cost per part manufactured coming down substantially. So these things need to be all considered. Now let's further looking on the details, how everything in the stack coming together. This is the flow plate or bipolar plates, and these are flow channel, these are land portion, and this is the gas diffusion layer, this catalyst layer. Mind you, they are not drawn in scale, because catalyst layer is the thickness less than 5 micron nowadays, and the gas diffusion layer is in the order of 100 micron. And these plates are typically in the millimeter range, okay? So they are not drawn in scale. But what you are seeing here, these are the pass line for electron. Electron go through the conducting part. And in the catalyst layer, you see this region have a high electron, but this region facing the flow channel have less electron. Now, inversely, if you look at the reacting gas, like hydrogen and air, facing the channel, you get a high concentration. Facing the land portion, they get a low concentration. Such that, now if you look at this membrane side, this is the gas diffusion layer side, and look at inside the catalyst layer, you see new membrane, you get a higher current density, and towards the gas diffusion layer, you get a low current density being produced. And then you see also look at this sinusoidal change because of this periodic flow channel. So therefore, you're trying to make your MEA everything the best and uniform distribution of catalyst, which is the most expensive component that you want to make uniform. But once you get the flow channel into the place, everything non-uniform. So how you're going to design the flow field or the bipolar plate depends on how you design the MEAs. For example, that if you make the GDL to be thin, then this non-uniformity going to be increased. But if you make the gas diffusion layer thicker, then they tend to be more uniform distribution of electron reacting in the catalyst layer. But if you increase the gas diffusion layer thickness, the resistance to the heat transfer, mass transfer, everything increases. So again, you see that now that in the stack design, you cannot really design a stack by itself. You have to look on how the MEA performs, the MEA components, characteristics integrate with your bipolar plate design. And then, since I'm from mechanical engineering, I'm going to focus a bit more on mechanical aspect. Suppose, say, we have a MEA in the middle. These are flow channels, and we're taking, okay, I'm running out of time quickly, so I'm only a few more slides. So now if you compress it, what happens that you see that this land portion compress and this region bulge, and in actual operation with cyclic loadings, you're going to see the failure, cracks going to form and the deformation going to coming in. So that if you're looking on the entire cell with flow channel design, and if you look at different pass line, you see the stress and the deformation on the MEA is quite different. And if you're looking at the entire thing, and this color represents how much stress is exerting on the MEA surface, and you see, take this line, you see they are not uniform. So there's two possibilities. Under the assembly force, the plate bulges, or alternatively, the plate may not be having a strict flatness. So that even though nominally everything the same, you actually have a different stress and deformation on the MEAs. So with this thing set, so some people trying to do it that, hey, instead of that, okay, instead flow channel open, we put a porous medium, like a metal foam over there, so that now provide little mechanical support over here, and also that increase the electron and heat pathways. So that being said, this kind of summarizes different fuel cell vehicles. Their stack power density in the order of about 3 kilowatts per liter or 3,000 watts per liter. But if you, this is, a citation from a publication year 2020. And if you look at the last June, that Toyota presented in a conference in Shanghai that 3,000 watts per liter power density of stack is for their first generation Mirai vehicle. For their second generation, they already increased to 5.4 or 5,400 watts per liter. And then if you look on Japanese government's ambitious plan, they want to reach power density over 10 kilowatts per liter. So there's a lot of room to improve and a lot of work to be done. It's good for researchers that we never run out of topic for research. So we're trying to say zero carbon transportation dawning, and there's a lot of work line ahead. And welcome people joining or step into hydrogen fuel cells. So thank you very much.
And we have 60 or so people out there watching via Zoom. So what we'll do is we'll take one question from the audience present here in Fed Hall, and then we'll go to the Zoom questions and switch back between the two. So I will start with asking you for questions that have come up on fuel cells and the future of sustainable mobility. Is there a question here? There is a question from Claudio.
Yeah, I have a question for the panelists in general, which is a follow-up or similar to what I asked Bob, in terms of the reference to the applications in transportation and efficiency. And how do you see all of this working out with respect to, especially in the small vehicle type of applications, with competition with respect to batteries, right? Which are certainly dominating, and sort of makes sense from the efficiency point of view. And how do you see that changing in the near future? I presume that fuel cells, since I got involved in this, have become a lot more efficient. I don't know what the levels of efficiency are right now, but in terms of cost efficiency and the availability of which was already mentioned, the fuel itself, okay? So if you can comment on that, thank you. This is an open question for the panelists.
Antimo? Yeah.
Okay. Thank you. Thank you. Thank you very much for the question. Thank you for the question. Yes, I'm completely in agreement that for the passenger car, like a small car, with the lithium-ion batteries are very well ahead compared to hydrogen fuel cells. One way that I see hydrogen fuel cells catching up, I would say, or maybe even taking over in the future, on the cost side, as we all know, lithium price is increasing a lot. So the hope that as the fuel cell technology develops, we will get to the point where the way you produce or you supply hydrogen will become cheaper, or at least as competitive with the cost of lithium. And that's how I see the fuel cell catching up and then taking over on the passenger car. But at the same time, I agree that especially at the company where I work at, we're focusing mostly on heavy-duty trucks. So that's because we see potential there to be better than battery. But that's how I see one of the ways of catching up with the batteries for passenger car. I see it that way, the cost of lithium.
But if I may follow up on that, I don't think it's only an issue of cost, but efficiencies.
Yes.
Can you comment on that?
Yeah, thank you. Thank you. Yes. Yeah, efficiency is also one of the other struggles we're going through. That's a very fair point. We're seeing that in our hydrogen fuel cells, efficiency and durability, we're actually struggling there. So that's true. And I think one way we can kind of like be at the same level as the lithium-ion batteries in terms of efficiency is if we keep working on our main components that some of my colleagues were talking about, like MEAs or bipolar plates. There are those requirements that you saw that the Department of Energy is putting out there. So the hard work we're doing for the bipolar plate, for example, you can switch between graphite composite and metal. Like there is a lot of research, a lot of work being done there, and we're already proving that the efficiency is growing. So if we keep going there in that direction with the MEA and bipolar plate, I think we can catch up in terms of efficiency as well.
Thank you, Timo.
Okay.
Oh, sorry, Professor Lee.
Yeah, since this is for panel, so I guess anybody could jump in. To be honest, I have a different presentation that could go on at least for an hour, compare hydrogen and battery electrical vehicles. Just from the application side, not only the cost efficiency, but also the convenience, the driving range, and all those coming in important to the customers. Let's first address your question on the efficiency side. Battery electrical vehicle charging, recharging, and electrical motors, they're all coming together. The efficiency will be way over 90%. In close to like a 92, 93% typically for a standard battery electrical vehicle. For hydrogen electrical fuel cell electrical vehicle, because hydrogen generation or electrolysis, the largest scale, you get about 80% efficiency. And from hydrogen to electricity in fuel cell, that's about 50%. So you look at about 40% overall life cycle efficiency. So this is the significant drawback for hydrogen electric fuel cell vehicle that if you look in the literature, there are people talking about. One of my good friends, he retired, he used to be the American Society of Mechanical Engineering. He has a very famous article that pinpoint on this efficiency alone. And he's the strong opponent to hydrogen, energy system, basically. Then if you're looking at the cost, taking Toyota Mirai vehicle as an example, their vehicle compared to battery electrical vehicle, the costs are very similar. Actually, the Mirai vehicle is slightly cheaper than the battery electrical vehicle from the Tesla, if you're looking that way. So that just a quick response to that. But let me look a little more further. For vehicle application, what vehicle need to operate under all environmental conditions, really hot summer to really cold Canadian winter. And if anybody pay attention to the news coming out of China from last winter, you may understand China pushing so hard for battery electrical vehicles. There's a lot of battery electrical vehicles because of government subsidy, so that a lot of people purchase it. And last winter was so cold, a lot of people couldn't drive vehicle back home at the end of the day because batteries perform a capacity drop substantially when the ambient temperature drops, especially in the cold winter. If in Southern California, no problem. The battery perform the best is about 25 Celsius degree. So the temperature going higher or lower, the capacity change, a lifetime reduce substantially. This is the one angle. And another angle is that I want to, since we are academic here, so I want to look on fundamental. Let's look on traditional combustion engine first. What you have in a combustion engine vehicle, you have a fuel tank, you have an engine. Engine is the energy conversion device or power producing device with a fuel tank. Then another reactant, air or oxygen coming from air, you don't carry on the vehicle. The combustion product exhaust you dump into environment, causing our environmental degradation or global climate change. You don't carry. So exhaust you don't carry. The oxygen stream, which is the air, you don't carry. You only carry fuel tank, energy conversion device. Now, if you look at the battery, you carry 2 reactants and the reaction product and the energy conversion device. You carry 4 on board the vehicle. So when you discharge, the reactant react to form product, electricity coming out. The product being stored. When you recharge, put electricity in, product decompose into 2 reactants. So you carry 4. So that's why batteries' power density is very, very low, or energy density is very low. Energy density in the order of like over 200. They're trying to reach 300 watts per liter. They never really got there. Yeah. They claim close, but never. It's about 265, the best one. But for fuel cell, the power density can reach like a Toyota 2nd generation Mirai, 5.4 kilowatts per liter. So it's not the same thing. First, now another issue is related with safety. That when you have all reactants stored inside along with the energy conversion system in the battery. So even though your vehicle is not driving, electrochemical reactivity is still going on. Instead of putting power output, they're going through the electrolyte. And that causing many electrical vehicles from Tesla to almost every maker of battery electric vehicle parked by the roadside burst into fire, or during driving burst into fire. And in China, there's a stalking video coming out, was that people using lithium-ion battery for moped. But battery is so expensive, so often get stolen if parked outside overnight. So the manufacturer make battery packs small enough and removable, so you can carry into your home. And that the video shows that the person carried this much smaller units of lithium-ion battery into the elevator. When the elevator door closed, suddenly fire came out. And so that now they ban in many parts of China that the battery electrical vehicle cannot be parked indoor, cannot be parked underground. Parking space have to be, outside in an open parking lot because of safety concern. So all these things being said, there's one more related to it that the battery electrical vehicle has limited driving range just because the amount of energy that can store being limited. If too much store, they can just add more battery. When they add more battery, there's another issue coming out is that if you look on Tesla battery electrical vehicle, they have over 10,000 cylindrical battery being connected together. So now think about in engineering, we talk about reliability of system is reliability of component multiply. So if you multiply 10,000 times, the total system reliability is less than 0.5% when I estimate. So that's why no matter what they do, the lithium-ion battery power system, when they're small, it's okay. But when getting large, the total system reliability is not there. And that's getting a bit long, but I just want to thank you very much.
Yeah, I think we all understand we need to get into the tow truck business. Okay, can we take a call from the Zoom sphere?
Yeah, should I go ahead? I guess you allowed me to unmute myself.
I turned it off.
Can you?
I can hear you. Can you hear me?
Yes. Say yes.
Yes.
Yes, yes.
Okay, perfect. Yeah. So my name is Mohammed Kadragi, from Germany, and I'm a battery person by definition. So this is my field. I work as a technical manager for battery and storage systems at a German company called SMA, and I'm always happy to be as well a research fellow for WISE since a while as well. So thanks a lot for the panel. I have mainly 3 points to raise up based on the presentations, and basically they are like for sure for comment for the whole panel, but basically I guess Professor Xiong Li already mentioned some of the points which I already take as a note. The first point is about the lifetime of the stack, the fuel cell stack. I compare things to lithium-ion batteries always. So I think always about the lifetime, the state of the art now, and the projection of the lifetime. This is the first question I have in mind. How does the outlook of the lifetime looks like? And the maintenance level which can be done. I have seen in the presentation that you presented the fuel cell stacks. Is it possible to exchange commercially? We know that scientifically and theoretically we can change even lithium-ion batteries single cells, but this is like economically insane and technically very hard to be done. In batteries, we're always in favor of changing a whole module, interconnect module together with its electronics. So in fuel cells, do we talk about changing a whole stack or a whole module as well, or which level of maintenance we have nowadays as a state of the art? This is the first point of comparison I have in mind. The second is related to the operation part of the fuel cells compared to batteries. I have seen kilowatt per liters as a volumetric energy density. What about the kilowatt hours per kilogram, which is as well an interesting figure for using batteries in electromobility specifically. This is the second point I didn't see in the presentations. And the last point is related to how do you see future hybrid systems, including fuel cells and lithium-ion batteries together? Because from my own perspective, I see this hybrid systems always a good solution for many applications, including electromobility, and especially including as well, not large-scale storage systems, but residential applications. So those are the 3 points I have for the panel.
Thank you.
Thanks a lot.
Who would like to start? Professor Lee, would you like the first point?
Now, if I remember the first point, anybody could repeat that?
Could you just briefly repeat the first question?
The first point was about the lifetime and maintenance level which we can have in fuel cells.
Since I'm an academic researcher, I haven't really gone into application, but I'm going to tell you a story that I learned from the actual user, which in Vancouver, because the 2020, the Winter Olympic Game, that they have 5 years, 2010 Winter Olympic Game, they have 20 fuel cell bus running for 5 years. And I had the fortune to talk to the fleet manager. And they say the fuel cell vehicle maintenance, it's about the same as the traditional diesel engine bus. The only difference is the unknown parts that need service. In BC, they don't have local industry. So anything for fuel cell component, they don't know what need to be changed. So when the bus comes to a point need to be changed, they know which one they have to order from Ontario, mostly from Kitchener, Cambridge area. Then shipping over, that takes at least a week. While for traditional diesel buses, they know maintenance schedule, what parts to order. So everything on stock, on shelf. So this takes a couple of hours to change. So that this maintenance schedule have to come in from the user community. Once they know for sure, then will be the fine. And in terms of the cost, because the downtime and also the less parts involved, they say that the first maintenance about 18,000 kilometers, that for the bus operation, the first one is about 50% higher cost than the diesel buses. Then the second maintenance coming down. After 5 maintenance schedule, the cost about the same, because now they know what to do with it. So I hope this gives you some reference point.
Yeah, it sounds
Yeah,
like
thanks a lot.
learning by doing. Yeah. Can you just repeat the second question now?
The second question was about the what we call it gravimetric energy density, or kilowatt hours per kilogram for a fuel cell compared to batteries.
That's about the same. Per liter or per kilogram, almost the same.
Okay.
So that's why I only mentioned one.
And the third?
The third was about the future of hybrid systems, including fuel cells and lithium-ion batteries. So how we see it in electromobility and residential application. Because just a quick comment about this, I have seen products in Australia for home storage systems using fuel cells plus batteries together, like a fridge-size device, which you can put in your house and then use solar energy for producing green hydrogen and getting the luxury of using the batteries together.
Well, that does sound expensive, but anybody care to comment on that?
I can comment a little bit. I used to work with the Automotive Fuel Cell Cooperation. They were a partnership by Daimler and Ford, and putting batteries was out of the question because the cost would have been too high in vehicles.
Mm-hmm.
It was a no-go. As great as it sounded theoretically, it would have solved cold start issues, it would have solved all kinds of regenerative braking, whatever, but the cost was too much. Even supercapacitors or whatever, they weren't going to do that. They were just trying to make the cells work well enough on their own.
Isn't that the same finding in Germany?
It depends, because the lithium-ion batteries costs are getting dramatically down. So I don't know in which year was this cost assessment done.
Ago. Yeah, that would have been 5 or 6 years ago.
Yes, because now we are reaching very, very low euros or dollars per kilowatt hours. And of course, if we do it 5-7 years ago, it will be crazy to do this. But nowadays, it's very, very cost competitive. And even we are reaching $100 per kilowatt hour for lithium-ion batteries. So that's why I see the future, the techno-economic assessment of a future hybrid lithium-ion and hydrogen could be very feasible for some applications.
Okay, thank you very kindly for your comment.
Thanks, Matt.
And your questions. Any other questions from the audience here? Oh, Claudio has another question.
Thanks. Having worked in this area for a while, including hydrogen, fuel cell applications and vehicle applications and batteries, one of the problems what we were facing when we were working with fuel cells is the issue that they couldn't do very well follow a load in the electrical applications, because the ramp up was too slow, right? They need to warm up or whatever, the chemical procedures didn't allow it to follow load. So in that application, we actually, when we were looking at implementing a system for a remote community, we were actually looking at mixing up the fuel cell with the battery. So the battery could follow up fast changes, for example, wind, solar changes, that the variability can be fast in seconds, and that would would address this issue. So, which is a follow-up of the question that was just asked, right? I wonder how the state of the art is now with fuel cells. I mean, can they quickly follow up this type of quick changes in power?
Samana, your
turn.
Well, I can make a quick response. Even though I say fuel cell vehicles, but typically it's a fuel cell battery hybrid power system. If you notice in one of my third slides, when I show up the vehicle, it has a battery clearly shown there. So that even though I say fuel cell vehicle, but really fuel cell battery hybrid power system, the only difference between the manufacturer is that the relative size of the battery and fuel cell system. Some batteries are larger, some fuel cells are larger, basically. It's always hybrid. Fuel cell cannot work alone with automotive application just because fuel cell cannot withstand these variable loads, basically. Yeah.
Thank you. No more questions on Zoom? Are there other questions? There's another question here from the audience. Could you identify yourself?
Yeah, name is Pascal. I'm a master's student here at Waterloo. I just had a question, I guess, for the whole panel. But one of the issues with fuel cells and batteries, fundamental problems in optimizing them is you're looking at optimizing cost, performance, and durability. And I've heard it said that you can pick two, essentially. I was wondering, so that's you know, with what Jeff was presenting with the catalyst layer, you know, one of the issues there was performance in terms of catalytic activity, but also in the case of the bipolar plates, you know, you're looking at the different stress and cracking mechanisms and stuff and degradation. I'm just wondering how do we go about deciding which of the two, or how do we optimize how to optimize the three of those things: durability, cost, and performance, in designing the fuel cells and battery systems.
Maybe I can take that. So, you know, the science is going very fast in fuel cell and battery in both sides, and I think that all these sciences and technology comes up together. So, like a couple of years ago, when Jeff talked about the FCC, we had an MEA that we had almost 4 milligram per centimeter square platinum in our MEA, and we got the exactly same performance and durability that we have today with just 0.2 milligram per centimeter square platinum. So there are a lot of suppliers that are working on different components. We are also, a lot of researchers are focusing on different type of catalysts, non-precious metal, or how we increase the utilization of the precious metal, or how we can recycle, you know, the platinum that we are applying in fuel cell, that over time we come up with a technology that we can bring down substantially the cost.
Okay. Other questions? Yes? Yeah, please identify yourself.
Yeah, hi, my name is Prasad. I'm a fuel cell engineer from Tervis Energy. My quick question is regarding the cost analysis. We have been hearing the sweet number, like $25 per kilowatt. Now we're hearing the DOE's target is $14 per kilowatt. Talking with different manufacturers, the current price of fuel cell stack is somewhere varying from $4,000 to $5,000 per kilowatt. So when is this number going to come down? My second question is something interesting.
Wait a moment, let's just answer the first one.
Oh, yeah, sure.
First. Who would like to try the first one? When is the price going to come down?
I didn't understand the final part of the question. Like you said,
the actual manufacturing price from the manufacturers on the fuel cell stack is between $4,000 to $5,000 per kilowatt, but the target is like $14 per kilowatt by 2025. When is this big number going to change?
The specific number I showed in the last table, that was specifically for MEA, for passenger car application. So that was not referring to the whole stack. That was the price of one MEA, like of MEA, like per kilowatt you produce, like power produced. So I'm not sure, like you're trying to understand the comparison between the price of the stack and the price of the MEA?
Yes. So is the price of the stack going to come down some $100 or like $500 per kilowatt? Then that makes the feasible for fuel cell market.
Yes. That's the goal that one of the ways, as Dr. Shagaldi said, that if you try to, especially on the MEA side, if you try to reduce the cost by reduce the amount of precious metal you're using, like Dr. Gostick was saying, like ideally we would use no platinum, then you're reducing the cost of the MEA, and then because the MEA is the piece, I would say, that contributes the most for the cost of the stack, as Dr. Lee said, then you're automatically reducing the cost of your stack. So that would be one way we want to go to reduce the cost of the stack.
Okay, the cost directly proportional to the platinum.
Yes.
And the second thing is, I really appreciate the work done by Professor Gostick, on graphene and iron. I would like to see those research for the long-term stability as well. And my other question is, when you mentioned about the Nafion coating on the catalyst layers, so that gives the better performance for the fuel cell high power density. Can you just explain how this Nafion coating is done on the catalyst layer when you embed on the membranes?
So the electro spraying process, the one that I showed specifically, we had a alcohol solvent with polymer, the naphthalene or the ionomer dissolved in there, and the particles dispersed. And as you sprayed it, the solvent disappears, and you're left with particles coated by the polymer. So we didn't have a lot of control over that, but and I guess that's why we weren't getting good electrical conductivity between the particles. So it was a better way to lay down the catalyst layer, I guess, would help.
Okay. Yeah, the final one is the bipolar plate. Professor Lee, can you explain about the future trend on the metal bipolar plates and their advantages in improving the fuel cell performance?
Well, the typical material used for bipolar plate are graphite plates and carbon composite and metallic. And each one of them has pros and cons. So there's no one better than others. It depends on the application. If you're looking for like a marine ship application for a high chain, for the chain application, they have enough space and can hold the weight so that you could use graphite plate, which have the long lifetime. And if for metallic bipolar plate can reduce the volume and size and increase the power density, which is good for passenger vehicle application, where the lifetime is only 5,000 to 8,000 versus to a chain and ship, you're talking about, 40, 50,000 hours at least going up. So it's like there's no one design fits all applications. It depends on specific application. Just like the diesel engine, we're talking about diesel engine for trucks, diesel engine for marine application, diesel engine for stationary power generation in remote community. They're all called diesel engine, but design are completely different. Some are more heavy, durable, and some are lightweight and have with shorter lifetime. So that coming back to your very first question, how we're going to look at the cost coming down, typically looking at 3 ways. One is to have novel materials, typically catalyst membrane and the bipolar plate, the materials. The second, design to get a better performance. As I mentioned, that Toyota get already over 5 kilowatts per liter of power density. Japanese government ambition want to reach 10 kilowatts per liter. So therefore, there's further performance to be improved. Another part of it, normally academic never got into, the company working on is the volume fabrication, manufacturing, how they can manufacture these in a cheap, faster way. And this is what the industry is changing. We have a lot of companies in Kitchener and Cambridge area that used to work on auto parts, make millions of parts, per month. But now they jump in trying to make fuel cell components. So the costs were coming down. And to give you a reference point, Toyota reference with these 3 approaches, better materials, the better design, and the better manufacturing, they plan to reduce their Mirai fuel cell vehicle cost by 95%. So that's the way you may be looking at it for future R&D activities.
Thank you very much, Professor Lee. Sorry, did I see any more questions?
Good afternoon. My name is Enrique. I'm a PhD candidate at University of Waterloo. Dr. Graziano mentioned something about security concerns people have about, inflammability, things like that. So I'd like to know what the industry is doing to mainly educate people, and what can we do as academia to help people understand this technology. Because I think, or I feel that same with normal vehicles, we have the same concerns, right? It's fuel. We could potentially cause a fire, and with hydrogen, we have the same concerns. What can we do to work together to educate people to understand, and especially because if we think that this is the future, what can we do together to educate people and help accept this as the future?
Thank you. Thank you for the question, for the comment. That's a very good point. Yes, hydrogen is an element that maybe, especially when it's used in applications, people might not be fully aware of it as opposed to your gasoline in your car. So that's a very fair point, and I totally agree. So in the fuel cell application, we incur flammability risk. As you know, hydrogen, depending on how it's stored or like the temperature is stored in, it can also lead to explosion. But for fuel cell cars or transportation, that's not much of a risk. The risk is more like fire. So I think, first of all, when the application is being like installed, I would say in a truck or in a car, there is all those there are all those tricks, I would say, that are applied so that your car is safe and you are safe as a driver. But at the same time, I believe and I really agree that there has to be some way of like instructing the driver or also people interested in buying a hydrogen car, fuel cell car. So there has to be some sort of like training or like some material that a person can go through and feel more comfortable. Even myself, I joined the company only 1 year ago, and I was more new to the fuel cell application. I come from a polymer composite background, so I helped more on the production of the bipolar plate. But even for me, it took me some time to get some awareness of hydrogen use in the fuel cell. And I believe that with putting that information available out there will help people feel more comfortable.
I just want to say one thing. Gasoline is extremely flammable, and it's sloshing around in our cars all the time, and it is literally on fire in our engines. So I don't understand where this is coming from. It's like some kind of smear campaign that someone started against fuel cells or whatever, but that's the thing we have to fight against, is how is this even a question? Anyway.
Because it's a new thing, so you raise a question mark automatically.
You can say, well, we do not have fire inside our car, unlike an actual car.
Yeah.
Yeah.
Okay, on that, there's just one last question here.
Yeah, I have a question to Professor Lee. This is regarding the flow field pathway. Yeah, my name is Dinesh, and I'm a PhD student from Quebec. You said in order to have like a pressure distribution within the flow field, you have kind of introduced a porous medium within the path. So is there any influence or like differentiation in the flow of the gas itself, or like is there any disruption in the behavior of the flow?
Yes, you are right. When you introduce porous medium in the flow channel, the resistance increases, so the pressure drop increases. Yeah. But that increase also is good for liquid water removal. So you get something, you lose something. In engineering, that's typical. So also it's better for heat distribution and for the electron distribution or transport. So you have to optimize. But if you look on practical application in the Mirai second-gen fuel cell, they're using this porous medium. I think titanium-coated, carbon-coated metal fell into that flow channels. Yeah.
Okay. Thanks very much indeed, Dinesh. Thank you, Professor Lee. And I just wanted to thank Professor Lee and Dr. Shargaldi and Dr. Graziano and Dr. Gostick for their contributions today. We're going to take. Okay, this afternoon's session is on hydrogen and ammonia production. We have 4 guests. Seated in front of me is Professor Michael Fowler, Professor of Chemical Engineering and the Canada Research Chair in Net Zero emissions and hydrogen research. To my left is Nelson Leite, who is the Chief Operating Officer of Fuel Positive Corporation. Also, remotely, Dr. Ophelia Gianu at the University of Windsor will be joining us, and John Koch, who is Executive Director of the Thorium Energy Alliance. We're going to start with Professor Fowler, speaking on giving a general introduction to the issues of hydrogen production, particularly with reference to where we are here in central Canada. Michael, over to you.
Okay, can you guys hear me just fine? We'll get started. Okay, so since Dr. Gostick, he had his chance to talk about climate change, I will put in a little bit just for people to, you could look at this slide and you can make your own opinion of whatever you feel about it. But Albert Einstein said the definition of insanity is to have the same outcome again and again and again without doing something different. So you could take up this slide and make your own equations with that one. Okay, so the first thing is a little bit busy, but what I want to talk a little bit about is I want to talk about the colorful of hydrogen, because there is an easier one for people to understand it. The first thing we have black or coal. Nobody wants coal. Nobody wants coal to come on all there. But coal comes from a lot of hydrogen still. But eventually, we have too much CO2 coming up with coal, and there's other emissions that are coming from coal, so you don't want to have that at all. Yes, we have gray hydrogen. Yes, we're going to have hydrogen. My opinion, I probably see you're going to natural gas probably a couple hundred years. They're comfortable. We can convert gray hydrogen from natural gas, and we can use that, as natural gas and in the infrastructure that's there at the same time. I should have put my glasses on here, right here, if I'm going to look at it myself. Hold on just a second. Okay, the second thing that we're looking at is green hydrogen. Green hydrogen is what we're really looking for. So we're looking for green hydrogen. Green hydrogen coming from renewable. So when I say that, it's coming from wind and solar really there. And yes, you're going to coming from hydro. That's going to come from water. That's what people are saying the future, they say it's going to be green. They leave one thing out, and I'll put it at the little bit at the end, right? Yellow that you have when you're looking at that. Okay, so we're also having doing research, and this is not one. It's in research still, but it might happen. It directly from solar. We can convert into yellow hydrogen, right? Blue hydrogen, we'll let some of the other people talk about blue hydrogen. Is it going to work? Yes, but we have to capture the CO2, and we have to sequestration, and we have to have enough room to do that forever. So I don't know if blue hydrogen is going to work everywhere and where we need, right? Then we get into kind hydrogen and in white hydrogen. These are things that are in research that we are looking for, but we're not really working on research right now, but we'll have in the future. Now, the one thing that I left out before, the colors of hydrogen is very colorful, and what we really need, we're coming from nuclear. We should have been making that over years ago. We have pink hydrogen. It's fully commercial. We can convert electrolyzers into work. We have production hydrogen from nuclear, and it's near zero emissions hydrogen, well to wheels, right? So we'll have that on there. But there are other ways of making hydrogen, and we're going to have some of the speakers that are going to be talking about it. If we convert the hydrogen, then we can handle it into certain applications like airfields or marine. You could handle it a little bit easier into ammonia from the hydrogen, right? Or if you go into reed hydrogen, you actually will go into there where you'll have thermal chemical process. This is what you really want. This is 60% the efficiency that we can have directly from the heat of hydrogen, well, directly from the nuclear energy into hydrogen, and that's where you'll get your efficiency, and it will be the best way that we can work on that. So what I'm talking about, I'm really talking about hydrogen. When we're looking at that, it is the commercial driver is really not driving the vehicles, it's driving the energy storage, right? Energy when we want it, where we want it, the amount we want it, and in the space and when we want it. Well, the energy when we want it. Yeah, wind's nice, but it doesn't have where the wind doesn't work in the summertime. So how do we need that? We need some way to move the energy from one season to the next one. So we need energy storage when we need it, right? Where we need it, when we need it. When I'm driving my vehicle, I want to pull into 401. I don't want to plug it into electrical. And yes, some light vehicles are going to be working there very efficiently, but how are we going to get them to refueling it very, very quickly? Where I'm going to get that moving? And we can move the hydrogen very easily around that. The amount that we have that. How much hydrogen we can store it long-term or temporal from one season to the next season, and the amount we need the hydrogen. We can go underground, we can go into storage. That's another one. Or space or form. So I want a Class 8 vehicle, so I want a big truck. I want a space and the energy there. If you put all your batteries in it, then you're going to carry all that weight and you're going to take your space away from your freight. So you need your space and your form. Hydrogen provides that energy that we're looking at. That's what we're looking at. This is really what the people really want to look at. They want the wind, the hydrogen, the solar. They want to convert into electrolyzers and then ultimately put it into refueling the applications, right? But this is the thing that is going to happen is, yes, it'd be nice to have a renewable energy system. And I think that, yes, this is what people want, is this the objective that people want to have over 20 years, right? They want to have that. But this is a very old slide, I haven't updated the numbers on this, but if we look at it, if we look at the light vehicles, and we have the electricity that's coming out of there. If I look at the electricity that we have now, right, well, we're going to have to double the amount of electricity to start charging up those vehicles, right? We're going to need the hydrogen to refuel the vehicles. So we're going to have to double how much electricity we have out there. So where are we going to get that energy from them? We've proven what's happened out of Germany that built the wind and the solar and enough building all of Germany. What happened? The CO2 went up, right? And the price went way up. In France, they built new nuclear. They got about 85% nuclear. The energy is about half the price of what it is in Germany. And they have a lot less CO2. So there's other things to think about there. So if we look at the energy system, and this is all of them, but what we really want to do, we need energy storage. We need it when we need it, meaning we need it off peak that we're using that. We need the energy storage that we're going to be putting that, and then we're going to put it into our homes. We're either going to be charging up our light vehicles or we're going to be using that. Some people think that they're going to have their homes. Our homes are all heated. Right now, probably 6 months with natural gas. We're going to need other types of electricity is going to come into those homes, and all those homes. Think of all the condos. Think of all the things that we're going to have with those. We're going to need energy storage that when the sun doesn't come, when the wind doesn't come, where do we get our energy from? We're going to need that both each week and over the time, right, that we're looking at them. One way to looking at it, we look at the different ideas for power to gas and with the energy system. So we really need the energy on the one side, the supply. Then we have to convert that into it. And that's where electrolysis comes into it. Electrolysis is the enabler. It will enable all the electricity that's coming. It goes into the electrolyzer, and then we convert it into other things. We can put it right into the natural gas pipeline right away. So we can put that, we don't have to worry about it right now. So the question that people about electrolysis, how much electrolysis do we need in Ontario? Well, we've done the analysis. What I'm telling you is start building electrolysis. When you build enough of them, then I'll tell you when to say stop. So stop building it because we need it right now. And we need a lot more than that, thousands of them, electrolysis coming into the systems. Then we can take it and you say, well, what if I have that electricity? You know, and now you don't have the hydrogen because the vehicles aren't ready yet, because you can only buy them from California or for Washington or someplace. Well, what can you do? Well, while we're waiting that, you can just dump it into the infrastructure of the natural gas. You can mix the hydrogen, enriched natural gas, and you can put it directly into the natural gas system, and we can use it for versatile types of applications. So right now, it's been approved for at least 2%. We're never going to get to 2% of hydrogen. It'd be nice to get there, but it's never there. Other people might get more hydrogen, but we'll eventually have it there. We're going to have the distribution, and we're going to need other places that we're moving it along into the actual applications. So power to gas is a good transition that we're going to have the natural gas coming out of there. So how many years are you going to have natural gas for? 7 years, or are you going to have it 30 years, or are you going to have it 100 years? It depends that we're going to get there, right? So when you look at it, we can enable hydrogen because we meet the grid, and then we took it on into electrolysis. Then we can take that hydrogen, we can store it underground, we can put it into tanks, we can store it until our seasonal time. Then we can turn our applications into vehicles, into our homes, into our different applications. Or I can put it back into the grid again and put the electricity when I need it at night, right? Or that we can look at it, aluminum could be a good application. I think that aluminum is going to have a renaissance in the future. Why? Because we made making hydrogen, we have been making CO2 from coal into aluminum for 150 years. But they have a brand new process where they can make like electrolysis for making aluminum CO2 free. So in 10 years, having aluminum free CO2, that'd be another application that would be very useful for people. So there are different variety of hydrogen. There's versatile, different applications, different ways to have a storage. This is everything that we can get there. Now, the one thing that we say is, well, it's a little handle to come with, let's say, Class 8 vehicles. A little bit handle on marines or airfield. Well, maybe one next step puts it into ammonia, and then it's a little easier to handle like the hydrogen there. But it all starts with the hydrogen turning into electrolysis. So start building those hydrogens, build them as much as you want. I'll tell you when to say stop, right? And I'll never get there, right? So the advantages of power to gas is that in Ontario especially, mostly of Canada also, we have natural gas infrastructure available. It's been built now. We use it today. It goes right into our home. Why can we just start bleeding the hydrogen into there? Yes, it's a waste of the hydrogen. It would be better to be putting in the vehicle, but while we're waiting for the electrolysis to come there, and for the vehicles, well, we can put it into homes. We can put this into other applications. We can put it into blended with natural gas. So there are advantages there in the energy density, the infrastructure's there. We can just put there, and then when we're ready to start putting up the vehicles and our other applications, just change the valve over, and then you can refill your trucks right there, because your electrolysis will be there. There's no real question about the chicken or the egg. We just need hydrogen. Fast electrolysis, built them last of them there, and we can build it along with power to gas in the transition. And we are still having natural gas plants which are providing us with electrolysis. It's still, we can have hydrogen blended into those turbines, and those turbines I've already approved up to 5% by some of the builders, and other people can be building on that, right? So this slide is really take off the Netherlands, but you can have electricity coming from wind, solar, or hydro, or the grid, right? But you're going to need hydrogen. You're going to need lots of hydrogen that's going to come from the nuclear electricity. Then you put it into the pipelines, or you can move it easily to different products, into shipping. You can put it into power. You can put it into aviation, heavy duty, fuel cells, right? Rail. All those applications are right there, right? Or if you really want to, you can take the hydrogen and convert it back into methanation down at the bottom. You can convert it into enriched natural gas is blended, or I can convert back into natural gas if it's a better application that you need that. So there's different ways that we can use it in industry and problems in the products in the future, right? Now, I'm not going to get into the next presentations, but if you're interested, I've done the applications that look for applications for refining, homes, for forklifts in distribution centers. I've done modeling for those. So I've got over about 50 journal papers, every different applications that we can have, we've tried on. My numbers are all wrong, but my numbers are all wrong because I thought it was going to be about 30 or 40 kilometers, or $30 or $40 for climate change, right? But now they're telling us that it's going to be $170 for in 7 years. So I don't know where it's going to come from. My research is I'm shifting that, is I'm saying I'm giving up. As I showed the first slide, the first idea, I've given up on CO2, right? Nobody's doing anything about that. We have less than 1.6% of the climate change is coming from Canada. It doesn't make a difference in the world, right? It doesn't. Over a part of the world, more than probably a third or a half of the world is still burning coal. India, United States, China, India, Russia, Germany are building coal. They continue having to do there. So what I'm saying is that, so what I'm now looking at is that, hey, if we can improve the emissions from the health cost, yes, if we improve the health cost, it will be good for people than having the environmental costs. It will still be good for CO2 if we'll have that, but improving that on the other one. Okay, so that's the other ones. We have lots of microgrids. If you have questions about what type of microgrids, I can go through different applications. You tell me what your application is. I put all the slides into these, the different applications that you can have. Manufacturing, refining, whatever applications that you're looking for, I'm looking at all those applications now.
Thanks, Michael.
That's about 10 minutes? Okay.
Okay.
Together.
Thank you, Michael. As we practiced before, we will return for questions and answers after the four speakers have made their presentations. Our second speaker is Professor Ophelia Gianu, who's part of the Department of Mechanical and Automotive and Materials Engineering at the University of Windsor. She herself is Assistant Professor of Mechanical Engineering. Ophelia?
Oh, there we are. There we are. All right. So thanks for having me, first of all. And I'm sorry I couldn't be there in person. I was teaching in the morning at the University of Windsor. So today I'm not going to focus on the big title that's there. Try not to focus on the whole thing. Focus on the thermochemical CU cycle for hydrogen production. In my research lab, what we do is we focus on hydrogen production and the thermochemical CU cycle. So we will go through some reactor designs. I will give the credit to my student, Ehsan Armoudli, who just graduated last week with his MASC. So if you can go to the next slide. So we're going to talk a little bit about the objectives, the heat exchanger design, some results and discussion, conclusion, and future work. I will try to keep it as quick as possible. Next. All right, next. It's a blank slide. You can populate all the information on this slide if you don't mind. So this is just, I guess, a little bit of a summary of what Michael was also saying. We are quite dependent on fossil fuels. So I know I don't need to convince you that hydrogen is the way to go. That's why you're here, because you know that hydrogen is the way to go. But when we look at the trends, we do see that fossil fuels are still quite used quite extensively, and even the hydrogen production methods, instead of having cleaner hydrogen production methods, we're using the hydrogen production from fossil fuels. So I have a saying where hydrogen is only going to be as clean as the method to produce it. So that's why in my research group, we focus on the thermochemical cycles. So the thermochemical cycles, we will go through it, the reasons why I think they're better. If we can go to the next slide. So why the CuCl cycle? There are many different thermochemical cycles, but the copper chlorine cycle, the operation temperature, so the reactions take place at a temperature that allows the integration with the nuclear power plants. So right now we have, this is for the World Nuclear Association, we have 19 operable reactors in Canada, 0 are under construction, and 6 reactors have been shut down. So in total, this the amount of energy that we get from nuclear power plants is over 13,600 megawatts electricity. And you can see that as we progress through the years, it's been steady since 2009. There is no new reactors that are being planned. However, the ones that are already there can be integrated with this copper chlorine cycle. If you can go to the next slide. So in this slide, again, from the World Nuclear Association, we have the small reactor designs, and these are new small reactor designs. And the reason I thought this this information is useful is because if we look at the outlet temperature of these small reactor designs, we see that many of them have a temperature of above 500 degrees. And we'll see when we look at the copper chlorine cycle that the required temperature to run the reactors is about around that temperature. So not only can we integrate this thermochemical cycle with the nuclear power plants, but even with the small reactors, we could integrate it. If you can go to the next slide. All right, so the copper chlorine cycle, there are different configurations of this copper chlorine cycle, and there is a lot of research going on. There is a lab scale thermochemical copper chlorine cycle that's built at Ontario Tech University. That's where I was before coming to University of Windsor. And at University of Windsor, what we do is we focus more on ways to provide the heat to the reactors and also ways to move these chemicals and integrate the reactor. So we look at the transport phenomena. So there are 3-step, 4-step, and 5-step copper chlorine cycles. And the one that we focus on is a 4-step cycle. So you see, if you look in figure 5, the 4-step CuCl cycle, you start with water that is input into the hydrolysis. And then if you follow the arrows, the water is going to react with cupric chloride, so CuCl2. The water is in the form of steam, and it's going to form this double salt. It's called copper oxychloride. This salt doesn't exist in environment, so we have to create it in that reactor. Then that salt goes next to the thermolysis reactor, where the oxygen is being removed from the salt, and the output is going to be molten CuCl. The molten CuCl, if you follow the arrow towards the electrolysis, gets mixed with the hydrochloric acid that comes out of the hydrolysis, so the top box in the first reactor. So they get mixed and input into the electrolysis. So and in the electrolysis, we split the hydrogen, but in this cycle, we split the hydrogen from hydrochloric acid rather than from water. So hydrochloric acid has a weaker bond. The hydrogen chlorine gas is hydrogen chlorine bond is much weaker than the water bond. So it takes less energy to split. So hydrogen is being removed, and then the chlorine that's left is going to attach to the CuCl that's already in the solution, and it's going to form an aqueous cupric chloride, so CuCl2 mixture, which is then going to be again circulated back to hydrolysis, back to thermolysis and electrolysis. So you can see that there's no emissions. These salts are recycled internally. And the lowest temperature that we need in the cycle is 25 degrees, and that's for the electrolysis can work at that temperature, or it can work up to 90 degrees. And then the highest temperature is 500 degrees, which is the focus of the study that we did. So if we can go to the next slide. So here what we, a little bit to tell you why this cycle is good. The energy efficiency is about 43%. It requires that the maximum temperature is 500, it's between 530 and 550, depending on what other pressures you have and how you want to control the reaction. It has the ability to use waste heat from nuclear power plants. it has very low global warming potential. So it's less than 1 kilogram CO2 equivalent per kilogram of hydrogen produced. Low cost, although we don't focus on the cost, so this I'm not sure how accurate this is, and it's a reasonable level of technology. So what we focused on is how do we take this, how do we provide the heat in the thermolysis reactor to be able to decompose that oxygen, so remove the oxygen. Next slide. So I already told you what the objectives are, so we're going to go to the next slide. All right, so we had some thermal constraints in this reactor, and we needed to have good handling of these materials. We wanted the interior surface of the heat exchanger to the temperature to be lower than 550 degrees Celsius, and that's to avoid crystalline formation. And we had to figure out what kind of material could give us this temperature. So I'm going to go quickly through this. So if you can go to the next slide to look at the reactor design. Next slide. And if you can click again, the reactor design is on that missing page. Next slide. Ah, there it is. Okay, so here what we have is the design that we came up with, and I don't have access to kind of like point, but if you can follow kind of like what I'm, hopefully my explanation is going to be good enough. So where you see at the very bottom of figure 9, you see the direction of flow, and you see the the arrows, the yellow arrows that point up. That's the copper oxychloride that comes from the previous reactor, from the hydrolysis reactor, and that's a solid. And it enters this heat exchanger that we designed. It enters in the blue region at the bottom. So where you see that blue gap, that's where the copper oxychloride is going to enter and move up. Now, the coils that you see, those that's heat that's provided from the nuclear power plant. And we have the highest temperature, so the inlets are at the top, and then the outlets are at the bottom. The idea is that we want the reaction to take place at the surface of that, call it box. And then the oxygen is not going to have to be mixed with different phases. So it's oxygen can detach at the surface and be removed from the reactor. Meanwhile, the CuCl is going to, due to gravity, is just going to flow to the out of this reactor into the next step. So I don't think I have too much time to go through all the slides, but I will mention we can go through them, and I will stop you if there's anything that I want to focus on. So let's go to the next slide. One thing that we have to be careful when we select when we work with the copper chlorine cycle is that the materials are highly corrosive. And one challenge that we have with the nuclear power plant is that the waste heat that they provide, the material is highly radioactive. So there has to be a series of heat exchangers that will capture that heat. So for this study, we went with solar salt. It is stable up until 590 degrees Celsius. So we could provide the heat to our reactor using the solar salt. Next slide. And next slide. So just a closer up of what the reactor looks like. It was modeled as a heat exchanger with the CuCl. It's the rectangular like number 6 and number 5. You see it in the figure 13, and then you have the heat exchanger, the solar salt flowing from 1 to 3 and then to 2. And these are some of the boundary conditions that we had to apply for the analysis. And next slide. So in this study, we simulated about 16 cases. We selected 3 that are best, and the analysis was done for 1 kilogram of hydrogen production, and the mass flow rate of the reactant was calculated to be 0.0196 kilograms per second. Now this can be scaled up. So we designed it so that it can be scaled up. We can go to the next slide. I'm not going to go through the results and discussions, but we did achieve the required temperature that we wanted to achieve. We had to implement fins to increase the surface area. I believe I am out of time, so I will leave it here and I will take questions after. Thank you very much.
Thank you, Olafina. Our next speaker is Nelson Leet, who is Chief Operating Officer of Fuel Positive Corporation. Okay, Nelson, you.
Great.
You want to speak from here?
Forward, backward, pointer. Okay, great. Thank you. This is going to be hard for me to. Can you hear me? Hard for me to see the. Because I'm so tall, these don't normally get in the way. What a picture. Looks like I'm angry at somebody. My name's Nelson Leet. Thank you so much for having me. I'm the COO of Fuel Positive Corporation. We are somewhat of a startup with a reboot that took place earlier in 2021. I'm very honored to be here to help give back to my community. I was born and raised here in Kitchener-Waterloo, and my son just graduated last week from mechatronics from Waterloo, so I'm very pleased to be part of the University of Waterloo events and welcome them in the future. So who are we? So just in case there's anyone out there who isn't familiar with Fuel Positive, we're a company dedicated to acquiring and bringing clean, sustainable, economically viable environmental solutions that can be deployed immediately, not decades from now. My CEO put together that paragraph, and I would just say it's clean energy solutions that can be performed right now and not decades from now. As Dr. Fowler mentioned, we need things done now. We are local to the Waterloo area with offices in the Catalyst building in Kitchener and our first assembly site on Northland Drive in Waterloo. We are currently on an aggressive path and working on securing 2 more facilities, one in Elmira, actually, one for R&D, and a large factory that we're going to be hiring over 150 people over the next year. Our lead technology invented and entirely developed in Canada is now in the demonstration phase and is designed to produce green ammonia on site for a wide variety of uses, especially carbon-free fertilizers and fuel. We also continue to work on our legacy e-store supercapacitor technology. This solid-state energy storage allows for increases in power and energy density, scalability, charging speed, longevity, and a lower cost per kilowatt hour stored. We continue to work on improvements to this technology with a group of scientists associated with NASA in our Texas location, the ultimate goal being the commercialization of this energy. So that was the first technology, well actually the second technology. We were building electric cars about 9 years ago, and then we evolved to supercapacitor storage, and then took on a spin-off reboot when we found this technology at Ontario Tech University pertaining to ammonia. There's a huge paradox associated with ammonia. The world needs fertilizer to meet the growing demand for food and food security, but the problem is that the traditional production method where ammonia is made in massive fossil fuel-powered refineries is one of the most emissions-intensive manufacturing processes in the world. For every metric ton of traditional or gray ammonia produced globally, almost 3 metric tons of greenhouse gases are emitted. Also, these refineries are centralized, with a small number of them providing all the ammonia used around the planet. The resulting ammonia needs to be transported vast distances from the point of production to the point of use, as you can see in the slide. That supply chain is wildly unreliable. Farmers, for example, never know exactly when they will get their delivery, how much they will get, and how much they'll have to pay. Ammonia is becoming unaffordable for the farmer, and it's about to get a lot worse. Just to give you an example, a couple of years ago, ammonia was costing approximately $400 per ton of ammonia. Now it's well over $2,000 a ton, if you can even get it. So the farmers need the ammonia, they can't really afford to pay for it, so if they put it on, they don't have it to put on their crops, then their yields will go down, then their revenue goes down, now they can't afford to pay for ammonia again. So we have to solve the problem. There's a very big problem here. If you've been following it in the news, you'll be aware that the war in Ukraine is resulting in global fertilizer shortages, which will translate into significantly smaller crop yields for farmers as prices skyrocket and supply plummets. And that translates into food insecurities. Moreover, Canada is the largest importer from Russia is nitrogen-based fertilizer in the form of urea, and that supply has now stopped, or at least has stopped direct shipments from Russia. So to sum up what we call the ammonia paradox, we need ammonia for food security, but producing it is contributing negatively to climate change, which in turn is threatening food security. Farmers can't afford ammonia, so their crop yields will be reduced. Well, before the terrible events in Ukraine, which have brought a spotlight on the issues, our amazing team was thinking, what if we could produce ammonia without polluting, and what if we could solve the supply chain and price problems as it relates to agriculture? And that's exactly what we've done. And this slide shows how we do it. We have to be careful, we can't get into specifics because we are a public company and we're patent pending. So we don't have NDAs signed with everyone, but welcome anyone to come to me at the end of the meeting or email me and we can get some NDAs signed and we can share a lot of the technology and some more proprietary information. In comparison to the traditional gray ammonia refinery and supply chain model, this shows you what our green ammonia production system looks like and shows you how we completely disrupt the traditional production model. Our technology was first invented by Dr. Ibrahim Dinser and his team from Ontario Tech University. Decarbonizes and decentralizes the ammonia production. We acquired the technology last year and have applied for a patent with Dr. Dinser and a few others, including our lead project engineer, Dr. Ghassan Shihadi. He's named on the patent as well as some others. You can see here that the actual production system has 3 basic sections. A hydrogen extractor that uses electrolysis to extract the hydrogen from the water, a nitrogen extractor that extracts the nitrogen from the air, and an ammonia synthesis converter. Our patent is for the unique technology used in the ammonia synthesis converter. Oh, I'm just going to go back one. There are 3 main benefits to our approach. First, our patent-pending technology uses only air, water, and sustainable electricity such as solar, wind, or hydro energy to produce clean, carbon-free, green anhydrous ammonia that can be used by any of the industries and sectors that currently use ammonia. The key point is that for the ammonia to be green, the electricity source must be sustainable. And that's been mentioned previously in some of our other talks. Second, beyond the carbon emissions, it negates our system is decentralized and as such completely eliminates the supply chain because the ammonia is produced on site where the user needs it. We call it a containerized plant in a box because it's modular and scalable. Our systems are built to fit within standard 20-foot and 40-foot shipping containers, and they can be scaled up or down depending on the end user's requirements. Each of our initial systems produce a minimum of 300 kilograms of pure anhydrous ammonia per day. If more production is required, additional systems and components can be stacked. Burden on the water system is localized, which distributes the effect to a manageable state. That's very important. We have to be thinking about how much water we use. If we're thinking about these huge, huge production facilities, there's a lot of water that's going to be used. Fortunately for our system, because it's decentralized, a farmer in Manitoba can have a system out back. It uses really less water than an average Toronto household does per day to produce the hydrogen. That's because it's only making a small amount of hydrogen that that particular farmer requires. So you're not putting the water burden on a town such as Guelph for Nestle Waters, for example, producing water bottles for all of North America, but all that water is coming from the town of Guelph. So that becomes a problem. You have to be able to manage that. In our case, because it's decentralized, we've got a pretty good plan for that. It's only using just under 500 liters per day. The third benefit, that because our ammonia is made without emitting carbon dioxide, it is now being considered for uses that were never thought to be reasonable before for gray ammonia, such as fossil fuel replacement for engines and grain drying instead of using gas, propane, or diesel. Green ammonia is also being considered for fuel cells, grid storage, and is an ideal carrier for hydrogen for the hydrogen economy. We plan to manufacture these systems first in small batches and later into large quantities using an assembly line approach to meet the domestic and global demand that's growing every day. Manufacturing in quantity will allow us to reach a price point that will accelerate demand and increase profit margins for the company. In this morning's event, there's a question about how do we bring the cost down. Cost is actually the #1 driver. Whenever we talk to our customers, it's not climate change. It's nothing but cost. They say, well, can it make my ammonia cheaper than what I pay right now? So right now they're paying over $2,000 a ton. It's costing them with our system under $560 a ton. CapEx becomes an issue. How can we make the system cost less? Well, we have to make more systems. So it's a bit of a chicken and the egg, or the egg scenario. So somebody's got to do some planning, and we need to use leading indicators to develop those quantities that we're going to be able to build. And we just have to start getting systems out there. Dr. Fowler mentioned we need to start building them, getting them out there. It's the same thing for ammonia systems, which we use electrolyzers in. So if we need electrolyzers, other people you need electrolyzers, we better start building electrolyzers. This slide shows what a farm could look like using our system. You can see that the water and air go into the fuel-positive containerized production unit that is powered by sustainable electricity sources, in this case, some windmills and a solar array. Some farmers live in an area where the grid is clean, so their power can come from the grid. Some farmers already have renewables powering their farms. Others will need to invest, but we'll help them determine what they need. Each system requires approximately 500 liters of water per day to produce 300 kilograms of green anhydrous ammonia. That 300 kilograms translates to over 100 tons a year, and an average farm in Ontario would use probably about 75 tons, but the average farm in Ontario is very small compared to an average farm in Manitoba. So if an average farm in Manitoba is roughly 6,000 acres, in Ontario it's under 1,000 acres, probably closer to 500 acres. So in Manitoba, the farms are quite large. So when Manitoba looks at our systems and sees the problems that they're having, Manitoba is screaming for these systems. So is Iowa and all the way down the Corn Belt and also in Europe. The green ammonia produced in our system will then be stored on the farm to be used as needed. You can see some of the storage tanks behind the fuel positive unit here. The farmer will use our green ammonia as fertilizer for their crops. It can also be used in an aqueous form as fertilizers in the farmer's greenhouses or sprayed on the fields. And our green ammonia can be used as fuel for the tractors, grain drying, or other farm systems. The hydrogen system also works independently. So on the farm, that farmer has got access to the hydrogen electrolyzer as well. So I'm running out of time, but we'll move on to the next speaker and welcome any questions at the Q&A, and I'll be around after to speak to anyone if you wish.
Thanks, Nelson. Thank you, Nelson. Our final speaker in this panel is John Koch, who is Executive Director of the Thorium Energy Alliance. John, see if I can.
So I'm John Koch. I have an engineering consultancy called Whole World, and I and some other folks also started a nonprofit research organization called Thorium Energy Alliance. And thorium is called the third nuclear fuel. And by doing that, we became very involved in the nuclear renaissance. And then in 2012, I helped start a Canadian company called Terrestrial Energy, which was on one of the slides earlier. And Terrestrial Energy is developing a molten salt reactor system. And if you guys are taking notes at home, you can say that you could go look at the Oak Ridge National Lab, fairly famous experiment for the molten salt reactor experiment. And you'll quickly get the idea of why this is so attractive. It's a Gen 4 reactor, and it's inherently safe, meaning that it's walk-away safe. It has none of the safety issues that any systems we're currently using today might have. Even though our systems today are incredibly safe, these ones are even more better, and much more attractive to me is the high temperature aspect, as was brought up, because electricity is a terrible business to be in these days. So if you can do process heat, that is what you really want to get into, to using your nuclear reactor to directly replace burning stuff like coal or gas or oil. So next slide, please. So this is just a little thing that I tell people, that we're talking about how do we make 100% pure ammonia without any greenhouse gas inputs at all. And so the same question could be asked about any big thing. How do you get to the moon? And Buckminster Fuller, one of my favorite folks, he had this whole thing, 9 changes to the moon. It was basically a logic thing, like what technology do you have in place? How do you build that pyramid? What's at the bottom of the pyramid? What's at the top? And what we know today is that literally just within the last 18 months to 2 years, just within the last 24 months, we finally have the major systems in place. So next slide. Next slide, please. Thank you. So one of the main features is thermal storage. So we've had thermal storage since the 70s. Thermocline systems, you may know about Avampa, which was a bit of a failure, but it had a very big thermal storage system. So a lot of learning got, taken place with that failure. You might know that Bill Gates is trying to develop the Natrium system in Wyoming, which is also going to have a very large molten salt thermal storage system. It's very simple. It's just a giant bucket of very hot salt, and you heat it up with your excess energy, curtailed energy from wind and solar. Wherever you want to get your energy from, you can use it. You can store it for weeks, days, months, and extract that thermal energy back out at different temperatures, right? So we have a patent called thermophase, and the thermophase system uses a phase change and for instant heats. So it's a very interesting approach to storing energy. Next slide, please. So that's technology 1. Technology 2 is we finally are stopping making these electrolyzers one at a time, little tiny bespoke, custom tailor suit type operation. We're finally getting to the point where we're manufacturing them, getting them built at scale. Nel Hydrogen has different electrolyzers available. 200 megawatt electrolyzer is a catalog item. The system that I'm going to talk about here in a little bit could be up to 600 megawatts. So next slide, please. So third key to the huge energy transition that we're talking about here is desalination. And Nelson mentioned it a little bit, but nobody, when they're talking about the hydrogen economy, is adequately talking about the enormous need for water, deionized water, right? DI level water. So not just clean water, potable water, not brackish water, but you need ultra pure water, because things like proton exchange membranes can't see anything like boron or any dissolved metallics. You'll destroy them in a minute. They're very, very expensive. So the cost of this water is not free, whether you're on the ocean or you're sucking water out of an aquifer. When you think about just the United States and Canada alone, you know, we need to be making billions of kilograms a day. All right. So that is the scale that we need to think about. And there's distributed systems that were spoken about before, which can distribute that load. But this particular exercise that I'm discussing here is for some of the bigger, more industrial scale. And that's not even talking about running ocean liners on ammonia or using ammonia for other things than with traditional fertilizers. So next slide, please. So the fourth part, and what we don't need this yet to get started with this energy transition. There's so much curtailed energy. Renewables, as you probably understand, are really not super great for running an industrial economy. You know, they're utterly unreliable. They're intermittent. The sun goes down, the wind stops blowing, and when it does, it comes on huge inrush energies that cannot be sustained. They blow out transformers, they wreck transmission lines. So what we need to do is get that thermal salt storage systems in between, as an in-between. So when you get 500 megawatts inrushing onto the grid, you have a place to put it, and then you can release it over time in a useful manner. But one day we'll be able to get rid of all that wind and solar and replace it with these molten salt reactor systems, which are low cost. They are quickly deployable, factory built, highly energy dense, and of course, everybody's favorite thing, safe, safe, safe. Everybody wants to be oh so safe. So, so we're going to, you know, do all the above with this. And the best thing of all is with 600-degree plus operating temperature, we can do things like high temperature steam electrolysis, or we could even run that copper chloride system that was spoken about earlier. Next slide, please. So this is just another view of showing how you would integrate all these different things. You could integrate carbon capture on the left there, thermocline storage on the left there. Down below near the bottom, you can use different sorts of hydrogen producing systems, proton exchange membranes, high temperature steam electrolysis, maybe even copper chloride. To the right there, you could have one of these cyclonic desalinators. And of course, on the far right there, you can have even yet more advanced thermal storage systems like thermophase system, the patented terrestrial energy system. And you could even use very basic alkaline electrolyzers or super advanced high temperature systems. It kind of doesn't matter. What matters in all this, if you're going to take one thing away from my talk here, is that since all these things are in place, the CapEx big ticket kit exists now. They're all catalog items. What is the controlling factor for all this? The controlling factor is energy input cost. If you can get to below 3 cents a kilowatt, you are golden. That's when you're making hydrogen for $1 a kilogram. $1 a kilogram is the cost of hydrogen at the Gulf of Mexico. And as was stated earlier, nobody wants to be green. Everybody wants to make money. You know, putting on your green clothes and your green kimono is great, but when the accountants get the bill, they're going to always go for the lowest cost stuff. So we got to be, we got to be green, as a knock-on effect. What we have to do is make this new hydrogen economy more cost-effective and more attractive, and not through subsidies and tax breaks and all that stuff, because those go away. Those are political. We need to make them cost-effective and the best cost choice right out of the gate, no matter what. And then tax and subsidies, that's all icing on the cake. So next slide, please. So I'm not a monster. I won't make your, I won't just read this to you. You guys can read it. You guys can have these slides later. But essentially, this just shows that this is a known thing, well-known, well-understood process. Now that we have these systems commercialized, we're starting to see the $1.50 a kilogram price being hit, and we think that you could get down to the theoretical lower limit would be somewhere around 29 cents a kilogram at scale for hydrogen. So when you're at 29 cents and natural gas costs $1, people are going to choose this, and then you'll get all the nice, beautiful knock-on effects for free. But the main thing is we need to make this the most economic choice. Next slide, please. So this goes to the economics again. Today, if we could make these molten salt reactors pop into existence right now, we would be, in fact, making the cheapest hydrogen in the world. And even with without the reactor, with the curtailed energy storage systems, we would still be making sub $2, $1.75 hydrogen. And that's even accounting for this year's up to 10% inflation. So next slide, please. Here's one of the things that people don't understand. Why is it so unbelievably cost effective? Because you eliminate beta. Beta is risk. Any of you economist fans out there will understand that risk. The super ultra fluctuations in natural gas that we're seeing now, crazy guys invading other countries, causing disruptions in supply chains, that's all called risk. But if you're able to take nuclear power and make power for the same cost day and night, 365 for the next 20, 40, 80 years, you've eliminated a huge amount of your risk. That is worth millions and millions of dollars. That enables long, long range planning. So that is a huge economic driver for doing this. Next. So this is just a little bit of a block diagram. We have a contract with the Department of Energy in the United States to execute on some of this. We're working with the MISO grid operators. We're taking excess nuclear capacity and curtailed solar and wind, and we just happen to have a very large battery in the form of a pumped hydro system. So we're using pumped hydro instead of molten salt in this case. But we would still like to integrate molten salt to get learning on that. Down at the bottom there, you can see that there's a huge part of our project is learning how to manage very large amounts of water and the byproducts, the brine, trying to find out if there's valuable byproducts we can get out of the brine. And then, of course, the standard electrolyzers, Haber-Bosch system. We're not trying to reinvent the wheel there. We have well over 100 years experience with that. Next slide, please. And so we're not alone in this. As I said, this has been studied for many years now by Idaho National Lab. And even I'm a member of the Ammonia Energy Association. And you can see that in that little chart all the way to the left, what is the best possible way? And these guys are not super pro nuclear, believe me, but even they had to admit electrochemical nuclear. And that is, if I had a little laser pointer, I would point. If you go from electrochemical light water reactor driven ammonia production and you switch to small modular molten salt reactor, that little diamond would be down near a 2. So next slide, please. So here's another, if that's not motivating enough, that this is more economic and all that other good stuff. It's greener, safer, better, local jobs. If you don't do it, well, China's doing it. And if they start making this stuff cheaper than anybody else, you know, and safer and all the other knock-on effects, but if they start making it, this is going to just be one other giant sector of the economy that they will dominate in, and they will send prill and anhydrous all around the world, as well as other things like synthetic fuels, synthetic diesel, JP8, and they will have the intellectual property for it, and they'll control this market. So, you know, there's a little motivating factor to keep your domestic, this is a, domestic security to do this, food security, national security. So next slide, please.
John, can you finish up?
Yeah, well, I'm finished now because this isn't my current presentation. So the last slide here is just like, if we do this, if we use these new technologies from thermal molten salt storage and molten salt reactor, we can live in Tomorrowland and not idiocracy. So the last slide is just, you could pop one more slide there. Next slide. So that's it. I just want to thank you guys for your time.
Thanks, John. Now, folks out there on Zoom, if you would like to submit your questions by raising your electronic hand, and we will pick up the questions and ask Nelson, Michael, John, and Olafina to give you an answer. So, can I ask, first of all, here in the audience, are there any questions that readily come to mind concerning what you've just heard about hydrogen and ammonia production?
I do. I have a couple of questions.
Okay. Claudio.
I just wanted to first note that before we get started with that, notice that we have not been introducing our speakers with all their bios. That's available on the workshop website. So just to gain some time, we're not repeating those. So if you are interested in finding out more about the presenters, which we are very grateful for, and thank you all very much for participating, you can find that on the workshop website. Now, and probably you have noticed there's a few student posters of the research related to hydrogen on the back. I guess some of you have already been interacting with the students. Thanks to the students for their contribution. So now, having said that, now I have a couple of questions. One is for Michael. It's regarding the issue of hydrogen to gas, or power to gas. In a particular issue what I'm curious about is most of these, what I've been reading, I'm no expert on that, that when you introduce hydrogen into the gas system, you can go as high as 20% before the gas, the equipment that uses gas stops working properly. My question is, how much can you go? Can you go 100%? Can you change your equipment that start using most of the hydrogen for heating purposes or any of all those applications?
In Ontario, they have regularly, the regulator has approved 2% of hydrogen. To go to 2% hydrogen, you will need in the probably thousands of electrolysis to make the natural gas that's out there right now, because we have so much natural gas going through our homes, going through now our turbines. We're never going to get there. But having saying that, yes, some people think that they will test it. I think that India has approved 10%. Other people are saying go up to 20% without any questions. one of the people from Ultra might be able to tell me Union Gas, I think, not Union Gas, who's building the General Electric. I think they've said that they will be up to 5% with no questions, right? Once we get up to 10% or 20%, then we have to start to think about some of the equipment, changing that out. But 2%, no question at all, it will go right out.
But do you envision using 100% to use some of these, transforming all this equipment to burning only hydrogen?
I think that we will envision some applications will be burning them the same. If you look at manufacturing, manufacturing builds a paint booth of our car, and it is about 70% of the energy in manufacturing is going to need heat for the paint. So they're going to need hydrogens have to go to a level to there. So eventually I envision hydrogen to be 100%, but that's probably beyond 2050, right? Let's get the vehicles first.
Fair enough, thank you. And I had a question for Ophelia. In terms of these reactor, the heat exchanger, etc., if I understood correctly, this will require that you sort of co-design the nuclear reactor with this system of hydrogen production? I mean, it's not just that you take the heat out of the nuclear station and then use it, right? It's something integrated with the,
That's right.
heating systems, correct?
That's correct. It has to be integrated with the nuclear plant and with the nuclear reactors, but there is interest from the nuclear power plants in the co-generation of hydrogen. So there's already some talks, and CNL was part of the original thermochemical copper chlorine cycle research that was conducted at Ontario Tech.
Okay, so in principle, you will need a new design or co-design of the nuclear reactor. It's not that you just add it to an existing nuclear facility.
You could add it to an existing nuclear facility if there's a series of heat exchangers. So we cannot, as long as we can extract the heat, because right now they waste it. They let it go into the water, essentially.
Can I also jump in here? I don't know if you can hear my voice, but
this was also for John. Yes, if you can.
So if you recall, one of the big innovations is the thermal salt buffer battery storage. So if you can put that in between your end process, whether it's synthetic jet fuel or ammonia, and your energy input, which in my case, I'd really like it to be an advanced molten salt reactor, but it could be anything. And the one thing that this big bucket of salt does for you is it simulates what your cell phone does, in that your battery on your cell phone can be simultaneously charged and discharged. You can plug your cell phone in and use it while it's charging. That's an impressive feat of engineering, right? But ours is just a big bucket of hot salt. So you can be pouring heat energy into one end and simultaneously be drinking out of the other end, energy use. So it gives you the ability to bring on huge inrushes of curtailed solar and wind, or a constant feed put from a molten salt reactor, or even a light water reactor at 3 a.m. when a light water reactor isn't being utilized efficiently, or even curtailed heat from a gas turbine, combined cycle turbine system. The point is that the thermal storage just acts as a giant capacitor, buffer, battery, whatever. And just like a swimming pool, you can pour energy in one end of the swimming pool at one rate and take it out of the other end of the swimming pool at a different rate. And that's how you integrate all these different systems. As Ophelia was saying, it's a little more involved with that. You need interstitial heat exchangers and such, but that is an eminently solvable technical problem.
Okay, yeah, and my question was regarding that, the heat exchanger process, right? To take the heat out of the nuclear reactor and use it in these other reactor, hydrogen reactor. What would be the challenges of that in terms of the kind of quality of heat and the kind of...
Well, the terrestrial system, to pick a Canadian reactor design, the terrestrial has the reactor salt within the reactor, never leaves the reactor. So there's a primary heat exchanger, and then there's a secondary heat exchanger that exchanges, heat between the fuel salt and another fluoride salt. And then there's a tertiary heat exchanger that exchanges heat from the working fluoride salt, and that transfers it to a solar salt. And so that solar salt could be any size. That last heat exchanger could feed a process directly, or you could put one of these big buffer systems in there. And the nice thing about a solar salt with nuclear is that the solar salt can actually absorb some stray nuclear fission components that might, very remote chance, but if some of the fission products make it out of the reactor, the solar salt itself can act as a buffer to the system and absorb it. So there's a lot of nice knock-on effects of using a high temperature reactor. If you're using a light water reactor and you're just generating electricity, the low quality steam that a light water reactor makes or can do, they don't make very hot steam. So you would just be using electricity at the middle of the night, let's say, because the reactor wants to run wide open throttle, right? And so you can't run these reactors up and down, up and down. They don't like that. So if you could run the reactor wide open throttle 24 hours a day and handle that load following inside the thermal energy storage, that's where, that thermal energy storage can take hits all day long. It's super simple. And you can just take your excess electricity from your CANDU reactor and feed it in there all night while no one's using power. And then during the day, the CANDU could be feeding schools and homes and industry.
Okay.
Ophelia, do you have anything further to add?
I'm sorry.
Yeah.
Sorry, Ophelia?
I'm sorry, I didn't hear the question.
I said, did you have anything further?
No, John explained it very well. And pretty much just to summarize it, we would use the solar salt, so the design for our heat exchanger to bring it to into the reactor would be the solar salt that would bring the heat to our reactor.
Okay, thank you. And I have a last question for Nelson. When you show that cycle of going from electricity, water, etc., to ammonia, what are the efficiencies in all of this? How much do you have to put in and then you get out?
So can you hear me? Yeah.
Thanks.
So the percentage of efficiency that we're experiencing right now with the current demo system is roughly 70%. And we're targeting... It's the full cycle. So what we're targeting is upwards around 90, which is going to be difficult to get to, but we have to develop some catalysts to help that, to increase the absorption rate. We're also looking at some different forms of electrolyzers. So there's some new technologies coming down the pipe. The fortunate thing with all the talk and all the hype about hydrogen is because there's lots of money being pumped in and now everybody's talking about it, so it's terrific. We should have been talking about it a long time ago, but it wasn't important enough. Now it's extremely important, so we're seeing a lot of money being pumped in all over the world, a lot of new ideas coming in from all over the world. So it's our job now as an industrial partner to take those ideas, commercialize them as quickly as possible, and find out what those results are. We found 3 different technologies that we're exploring right now for the hydrolyzers. So what we found is one thing, the problem with electrolysis is the CapEx. On the whole system that you saw, the CapEx hit from the hydrogen generation is over 70% of the system cost is associated with the electrolysis. So if we can come up with better formats of creating that hydrogen that costs less, like we said, everybody wants to be green if they can afford to be green. In general, we all want to be green, but the farmer has to be able to afford to be green. So we want to get that CapEx down. But we're also finding is it's not just the CapEx that's coming down with these new technologies, it's the efficiencies going up. So we're trying to target roughly a 90% efficiency. The cost is always what someone's willing to pay. Is that correct? So from a business perspective, we want to get the cost down so the ROI makes sense for the farmer. So our key was OpEx at first, right? Because if the OpEx cost isn't economical, don't build it.
You're talking about operations and maintenance.
Operations and maintenance.
As opposed to capital expenditures.
Correct. So if I were to give a farmer our machine, if he still can't afford to produce a kilogram of ammonia, it's high costs him more to produce it than what he can buy it. It doesn't matter what I get. I could give it to him. I could pay him to run my machine. He's not going to run it because it costs him more. If I can get that OpEx cost down, so we've got the OpEx cost down significantly in comparison to the existing cost of ammonia. So now they can start looking at how much they save. So if we take a 7 or an 8 year payback currently, the cost could be 1.2 million, 1.3 million for the system, and it's still economically viable. I can tell you we are significantly lower than that. So right now, it's really, I hate to use this term, a no-brainer, but the farmers are lining up for this system, but there's a problem, other challenges that everybody's experiencing here that you have to remember is you can't just make these systems. You need physical space to make them. It takes 2,600 square feet to assemble a system in a batch process. So if you need to make 100 systems, you're looking at a plant, approaching the size of Toyota to make a system, to make these systems, to make 100. If we have to make 1,000, how are we going to make them? So now you have to use serial manufacturing in a way just like Toyota does their cars, right? So you have to start thinking of that far into the future. So we're building a factory. It's roughly 90,000 square feet, but there's also supply. If there are containers, if each system takes 2 containers, 2 20-foot containers, and you make 10 systems, that's 20 containers. What if you make 1,000 systems? How many containers do you need? So we need to think now about all that supply chain. Where are we going to get all this from? The catalyst and all that sort of thing is the easy part. It's the big items. So when we make our converters, we're making them out of stainless steel. So we have to be able to get that stainless steel. We have to be able to get those containers. Does that answer your question?
Okay, Bilal, could you identify yourself first? Bilal Sheikh from Dofasco.
Thank you. Bilal Sheikh from ArcelorMittal Dofasco. My question, 2 questions, but maybe I'll ask one now. For Nelson, I think, given the energy crisis and shortages, and even food shortages, as you mentioned, also in fertilizer industry, very big shortage. That's causing, I think you said $2,000 per ton or something in the ammonia market. Do you think that, what I see is that ammonia will only be used for agriculture? Like, why would anybody from the energy sector use ammonia, given those fluctuations and uncertainties and also the need for ammonia for agriculture?
So the question I heard was, why would anybody use it in the energy sector? But let's start at the farm, because that's how there was a natural progression with how we're evolving our technology. So now we have our system at the farm, and it's running, and the farmer's using the anhydrous ammonia coming off his system as fertilizer for his farm. He's very, very happy. That thing's running 24 hours a day, and he's thinking to himself, he or she is thinking to himself, what if I put another system in? I could make more anhydrous ammonia. I wonder if I could use it for something else. So they've approached us and said, can we build some converters to run our tractors, and why can't we use this as a fuel for our tractors? So we start looking at converters for tractors, and we start finding ammonia was used for internal combustion engines decades ago. The problem was NOx emissions. So if we can solve those NOx emissions, and possibly put in a mixture of hydrogen, a little spritz of hydrogen there to heat things up a little bit more, you start eliminating the NOx emissions. We've solved the burner problem. And then if we can use that for grain drying, then we can start using it in grain drying. Now, a grain dryer burner is not much different than a cement, what cement companies use for their furnaces and their ovens. Big production bakeries use ovens. They're using natural gas. They've got burners in there. Steel companies use furnaces, heat treating furnaces, annealing systems, all that sort of thing. So maybe not the energy sector. The energy sector is already using ammonia. It's produced, they call it black ammonia and different other gray ammonia and black ammonia. But those are very large systems, and that's where John's type of solution really solves that. But our solution would solve for the farmer, for grain drying. You could start burning ammonia. We ask the question sometimes is, if you're going to use ammonia as a hydrogen carrier, you've put hydrogen into the ammonia, now you've got the ammonia, you've shipped it. Why would you crack it back to hydrogen to use it as a burner, right? You would use that in a fuel cell, but you've already got the ammonia. So you're sitting there with the ammonia. Wouldn't you figure out a usage for that ammonia that you just transported? So I believe that there isn't, and Peter's from Stelco, I believe, right? So yeah, he mentioned something, there's not going to be one silver bullet, and that's exactly right. We all have to work together to come up with different solutions that are all going to migrate together and work. So our system could be similar in an industry. So let's say at a Toyota plant, if they're using one of John's systems for their energy, and then the line goes down for whatever reason, are they going to kick in a diesel generator? We'd say don't kick in a diesel generator. Turn on the fuel positive ammonia system that's located right in situ, right on your plant floor, and use it that way to subsidize that. So now you've got a solution that's mitigated some risk. The other thing that we haven't touched on is refrigeration with ammonia. So these smaller distributed systems with refrigeration. So Connoisseur Cold Storage is a local company, everybody kind of knows them, using ammonia for refrigeration, and they're bleeding off 10% into the atmosphere. They have to replenish that. Let's stop bleeding it out in the atmosphere. Why are we doing that? Let's solve that. But in the meantime, we can use the ammonia for that. But as far as the energy companies, they are converting. ThyssenKrupp is building some large facilities for ammonia for the energy sector right now. They're being quite successful at it in Europe.
Okay, Bill.
Just one more question for, I think it was Dr. Ophelia. Just wanted to know, how does your the energy per kilogram of hydrogen compare to like a traditional electrolyzer?
So, well, traditional electrolyzer, it uses more electricity to operate, where because you break the bond of water, whereas in the copper chlorine cycle you break the bond of hydrochloric acid. So it uses 0.72 volts to break the bond, but it's a different cycle, so it's not really comparable. And to make it more, I guess, energy efficient, we do need the waste heat. Otherwise, the energy requirements would be very high.
Thank you, Ophelia. Any further questions? Oh, one more, yep.
Hi everyone, I am Anshul Goyal. I am a PhD candidate at University of Waterloo. I have a question for Mr. Nelson. In your flow diagram, I saw that it's a decentralized container where you are producing green ammonia based on renewables and hydro as primary source. But I had a question that in case out of 3 sources, 2 are unstable, solar and wind, where you don't know how much exact amount of solar and wind energy you can extract. The third one is based hydro, which is based on the availability of water. So what is the, how do you ensure the adequacy of the system in case if you want to if the farmer wants to have ammonia production large, so do you have any how do you ensure the adequacy? And the follow-up is like, in case if no, then why not integrating BESS, like battery energy storage system, into your system, into your container, so that you can store it, and when if more production of ammonia needs to be done and solar or wind is not sufficient, you can discharge it and produce it.
So those are good questions. So our current pilot projects are located in Manitoba. So Manitoba has a 100% clean grid. So the farmer can just plug into the grid and draw off the grid, and it's 100% green power. So the ammonia is only considered green based on the energy it's consuming. So if you fire it up with coal-fired power plant, then it's not going to be green ammonia. What we've built is an on-site system that can connect to any grid, but we certainly provide the customer with a solution if they have to go off-grid. So currently in Manitoba, they don't have to go off-grid, but if you're located in southern Texas and you want to have green ammonia, then we provide solar panels, we can provide wind power, but then you have to deal with storage, exactly. So you have to have either some sort of energy storage, batteries, but we are looking at the salt storage right now, so that's why it's so great when we can work with colleagues like John and there's others. There's some over in Denmark that have got some terrific solutions that have been used for years. So we are now working on some scaled down versions that work within that size model, so the 10,000 acre farm, et cetera. So you're absolutely right. So if you go from Manitoba, you go down to southern Texas, you're not into clean energy, but you are already solving a problem for that customer. You're solving the problem of the cost of ammonia and getting the ammonia, so we're trying to help solve the food shortage problem. Secondly, we want to make it green. So let's first get that food shortage problem solved for them, but give them a plan, a strategy to convert over so that they're almost 100% off the grid. And some other slides we show how large that solar array would have to be. So with one of our systems, it's roughly the size of a football field. So if you've got 100 tons a year, if you have a football field, you put a solar array on a football field based on today's solar arrays, and is it economically viable right now? I would say that wouldn't be economically viable right now. But with solar arrays, every 5 years, the cost comes down by 50%. But you need space, which farmers generally have the space to deal with that. And a lot of farmers already have some existing solar arrays. So our one farm in Manitoba already has a solar array that he's going to connect up to. But his grid is pretty cheap and it's pretty clean. So they're paying 4 cents per kilowatt hour Canadian. So John, I don't know if John, when he mentioned under 3 cents, was that US or was it Canadian? Because we're almost there in Manitoba, right? So.
Yep.
Thank you.
Okay, thank you. Any further questions? Yeah, there's one more up here. Yeah. Please identify yourself.
This is Aditya Legala. I'm a PhD student at U Waterloo. I'm asking this question from an automotive fuels perspective. If you look at gasoline or diesel, you have ULSD and other standards which say the purity level of the fuel, that being less than 15 ppm of impurities and stuff. When we are looking at green hydrogen, gray hydrogen production, what would the level of purity change with respect to production and whether we are transporting it through pipeline or trucks? Would the purity of the end product change when we are getting it at the pump grade? And when we are talking about $1 per kilogram or $2 per kilogram, are we talking about like the ultra pure version of the hydrogen that we use in our labs, because that directly affects the durability of PEM fuel cells?
Oh, I can try to start one. To start with, if you look at the refinery itself, the hydrogen goes into the refinery. So what's coming out of the refinery is exactly the same as the gasoline runs your cars today, and diesel. It's exactly the same. But refinery is there's a lot of mixed fuel. in a refinery. So they take light oil, they take heavy oil, they take a blend in order to theirs coming out. And they can change it out, but they can have the different blends that are in there. But right now, what I'm looking at is you'd be the equivalent of about 30,000 vehicles without changing the vehicles at all, just changing where the hydrogen is coming from in the refinery. Now the coming from the refinery comes from steam methane reforming, and that's no change. So that's where you can do that. Yes, other people are starting to blend hydrogen into diesel. I don't think they'll bleed into a light vehicle, but probably into diesel, that's possible. But I think that we would start first with the refineries, a better blend.
Gotcha.
Yeah. I could like to add to that. With our electrolyzers, we target a 99.999% purity on the hydrogen coming out. That's because it's going through an ammonia synthesis process, and you'll extend the life of the catalyst, you'll make absorption rates higher, et cetera. If you're going to use the hydrogen for fuel and the internal combustion engine that you're going to fire, or whatever you're going to use it for a fuel cell, if it can take a lower purity, the electrolyzer is going to put out more hydrogen. So if we want to increase our purity on our hydrogen, we slow down our electrolyzer and we put out a higher purity. So the electrolyzer can be dialed down in the purity and put out a greater amount of hydrogen. So as far as the purity goes, we work with a 99.999, but because it's going into ammonia. If the farmer's going to use it now for his tractor, we've got some work to do still, some analysis and see what's going to happen. Obviously, we want that number to be as low as possible so we can pump out as much hydrogen as we can. So we still have to work on that.
Gotcha. Yeah. Thank you.
Further on here.
Yes, so I have a question. So, Yu Wu, I am an assistant professor in the University of Waterloo. So I have a question to the two experts on nuclear reactors. So I was wondering for the system that you are designing, are you specifically looking at nuclear to hydrogen, or does these reactors actually can also produce electricity at the same time?
Yeah, this is John Kutch. The reactors would also almost always be cogen systems. So you would use the highest grade heat would go to electricity generation, and then you would pull the next grade heat down and use that for process heat. And that process heat is generally, the fancy one that everyone likes today is what we're talking about, hydrogen, but there's a lot of other process heat uses, cement production, desalination of water. I mean, basically something on the order of 75 to 80% of all chemical and industrial processes that need heat can be done under 650 degrees Celsius. So yeah, it would, to simply answer your question, yes, it would be generally broadly envisioned to be a cogeneration system that you would generate electricity and heat, but you might balance the load different. You might generate mostly electricity during the day and then mostly heat at night, that sort of thing.
Sounds good. How about the copper chloride cycle?
So for us, I have to mention that I'm not an expert in nuclear reactors. Our work in the thermochemical copper chlorine cycle, that's the focus. And our goal is to work with the nuclear power plants to co-generate. So they would, but their main generation would be electricity, and we would use the waste heat. We wouldn't have the nuclear power plant produce more heat for to have a desirable more hydrogen production. They already have waste heat at the temperature requirements that we need.
Sounds good. Thank you.
You're welcome.
I have another question.
Claudio, yes?
Thank you. I have another question for Nelson. Something based on what John mentioned about the need from, it's not just any water. It has to be somewhat ionized processed water. How do you do that in your system? Where is that water coming from? You have a system that is processing the water as well?
So our water source is direct from the garden hose. So it comes directly in. We have a cleaning filter. So with our system, it doesn't have to be super clean with just a standard water filtration system. And it's self-managed, so the cartridges get changed out once a year is what we're recommending. No different than your fridge. You open up your fridge, you take your cartridge out. So, and our lab system has been tested on that. Our prototypes, our hydrolyzer that we just built was tested on that. And so we're been pretty successful with that. But again, we're not dealing with you know, millions of kilograms of ammonia production per day. We're dealing with 300 kilograms on one system, which we're seeing might get up to 1,000, maybe 1,500 kilograms per day on some stacked systems, which the water consumption is very low, so it's pretty easy for us to deal with that.
Okay, so the same question for John. How will this work in a system that producing now the quantities of, the amounts of ammonia that the systems you described? Where is the water source and how is this being processed and the challenge?
Well, so one of the resources I could give you for further deeper dive into this is there's a company called Synergetic, and that was a spin-off out of a non-for-profit research group called Lucid Catalyst, and Lucid Catalyst just released a report last year in conjunction with EPRI, the Electric Power Research Institute. And so you can look into this. They do a very in-depth report on both synthetic jet fuel, synthetic diesel, and what is euphemistically called synthetic ammonia, even though all ammonia is pretty synthetic. And so the water requirement, desalination to deionized water level, that would require an intake of it's 3 to 1, right? So to get 1 liter of clean DI water, you're taking in about 3 liters of brackish water or unclean fresh water, and up to 5 liters of seawater and or you know, extremely brackish water. So it's you're creating a very, very large output of brine, very, you know, syrupy, thick, ultra salty brine. So it's a huge component of the cost of doing this, right? You know, if you're going to do it at scale, in the scale of billions of liters, billions of kilograms a day, you know, for an entire nation, you know, you got to start thinking very heavily about where you're going to locate these facilities. You know, you're not going to take water out of the Great Lakes. It's too precious. You know, so where next? You know, and what, you know, you're going to pull this out of the ocean. You're going to have these systems set up where? In Vancouver? Can you imagine trying to build something like this in Vancouver? You know, so it's you know, it is a huge issue that needs to be more carefully addressed, and that's why distributed systems like Nelson could be a very good starting step, because it's a not as heavy of a lift. But if we want to start doing things like replace 50% of our diesel fuel with synthetic fuels or ammonia additives, we're going to have a very serious discussion about where we get the water from and what we do with the byproducts from the water.
Okay, thank you. That's a follow-up question from Nelson then. is water demand a challenge in your system? Is it just take the water and use whatever you have available?
It's really not, because what we use per day on one system is less than what an average household uses. But where we see the challenge is we're climatizing our systems because they are on site. You can just imagine being in Manitoba in the summertime, you connect your water hose. I'm exaggerating when I say a water hose, but a water line connects up to the system. Then if you've been in Manitoba in the winter, you never want to go back again, right? So it's going to be frozen, so you have to deal with those situations. So placement of the system is very important, but now you're near a residence, you have a farmhouse, you've got neighbors, so you're making ammonia, you have to mitigate some risk if there's ever a catastrophic leak or a tractor runs into a valve and knocks a valve off and you start leaking off ammonia. What we're seeing is the farmers want to put them in the middle of a field, so then we have to really watch the water. They can't take from a well because it's very brackish water from the wells, so they have water systems coming from the municipalities that are filtered to a point that work well with our systems. But the challenge isn't so much the water supply, it's the climatizing of that, the mechanism getting the water to our container. So there's other industrial challenges.
Fair enough. And now, a question for Michael with the same idea. The water needs of, you have looked at the production of hydrogen for major applications, multiple applications. Is that a challenge? I mean, how the sources of water, how much water do you require to do all of this?
Yeah, you obviously production hydrogen, you're going to put in water, but I don't see that as being a demand on paper. Because remember, as soon as you get into a fuel cell, it's going to stay in the troposphere, because as soon as you go your fuel cell, it's going to run down in clouds eventually. So you're going to be in the water cycle.
Fair enough. Thank you.
If I have a little bit here, it may not be in the water. If you're using the hydrogen in that way, that's interesting. But the people who are going to pay for hydrogen first are going to be somebody like a Shell Oil who wants to add this sort of system to uprate their petroleum, or if Canada wanted to do its own refining of heavy oil sands, that requires a tremendous input of hydrogen plus lots of process heat. And so the hydrogen essentially could possibly be entrained into other industrial processes forever, essentially. And so there is something to be said for, like, the water won't come raining down again. But one thing I always tell audiences is that one thing we are producing is not just billions of kilograms of hydrogen in these scenarios, but billions of kilograms of oxygen. So if you've got ideas for what to do with oxygen, right now the only thought is, just release it to the atmosphere. And I mean, the irony there would be, do you actually release so much oxygen into the atmosphere that you dilute the CO2 effect? The solution to pollution is dilution. so it's an interesting thing to ponder, but there's a huge potential onslaught of atomically pure oxygen coming online. And so if people can think of what to do with that would help the environment and be cost effective, that's a business opportunity for all you've out there.
Okay, well, you heard that. This is the University of Waterloo. I'm sure people are thinking about it already. Yes.
With our systems, there's an opportunity for the farmer, if they have a water reservoir, which many of them do, we can recirculate that oxygen into the water reservoir. So that oxygenates their water. They can use that water into when they water the crops or for livestock. But we generally support the farms for crops for human consumption. but we're already finding alternates for that oxygen, and because it's a smaller amount, it's very easily dealt with in the in situ environment.
Yeah, I think finding uses for oxygen is going to be relatively simple in terms of oxygenating fresh water, oxygenating wastewater flows, etc. Okay, thank you all for that. We're going to take a 15-minute break. There are posters at the back. The students have put up posters at the back. There's some snacks at the back table there. And we'll be back here for panel 3, led by Eric Croiset at 3:15.
Thank you, everyone. Appreciate your time.
Thank you, everyone. It was a pleasure.
Thank you, Olafina. Thank you.
Okay, can you hear me? Yeah, so I think it's 3:15, so start panel 3. So my name is Eric Croiset, and I am a professor in chemical engineering at Waterloo, and I will be the moderator for the panel 3 on hydrogen storage. So our first presenter will be Maurice Dussault, who is a professor in Earth Environmental Science at Waterloo. So here we will have a pre-recorded video presentation from Professor Dussault, which is a good way to control the duration of the presentation. But in principle, Professor Dussault should be able to be present for the Q&A at the end. So whenever you're ready, you can start the presentation of Professor Dussault.
Good afternoon. My name is Maurice Dussault, and I'm going to speak a bit about storage of hydrogen in molecular form. I'm a subsurface expert in geomechanics, and we'll discuss subsurface hydrogen storage. So there is a consensus that fossil fuel externalities are leading to severe climate issues now and worse in the future. So this means that we want to reduce our dependence upon fossil fuels for primary energy sources. And this implies other sources like wind and solar, but also hydrogen, potentially for power for our grids, potentially for hydrogen for transport, potentially as a fuel for steel making, for cement making, and for other processes. So the premise that we are living under nowadays is that an energy transition is necessary, and that implies, of course, decarbonization of our primary energy sources, replacing fossil fuels, which currently account for just under 80% of our primary energy sources in the world, which further implies that we need different transportation fuels, and we must displace coal, particularly in China, India, Indonesia. We must displace coal, which is still widely used for electrical power. Hydrogen storage can aid this process. So let's look at more detail in hydrogen in the subsurface. Some of the hydrogen storage approaches are as gaseous molecular hydrogen. The trouble with that is that hydrogen is so light that we have a very low energy density per volume. We need large volumes or high pressures to store interesting quantities of hydrogen as a gaseous molecular phase. We can store it as a super cool liquefied hydrogen phase at 21 kelvins at 100 kPa. That costs money. That costs a lot for super insulated cryogenic storage facilities. Above ground, these facilities are not 100% secure against accidents, of course. As a metal hydride, much research has gone into this, fine, but currently the best we can do is perhaps 4 or 5% hydrogen as a fraction of the mass, so it's a very low mass ratio method of storage. Or we could convert hydrogen to another molecule, for example, methane, which is by mass 25% hydrogen, ammonia, which is 18% by mass hydrogen, or even methanol. All of these have different characteristics, advantages, and disadvantages. Here's essentially a summary of the problem of hydrogen storage. We need to store energy. So if we look at that yellow box, pumped hydro, compressed air energy storage, distributed batteries, heat storage in rocks, all of these have very low energy density, both in terms of volume and in mass. They all are found down at the lower lower left-hand corner of the energy density chart. Compared to diesel fuel and gasoline in the middle of the chart, and you see they store a lot of energy. But look at hydrogen way over on the lower right. It has a very low volumetric density for energy storage, but it has a very high mass density, 3 times as high as diesel or gasoline, approximately. So, will an H2 economy emerge? If it does, it has to be a network, just like our natural gas network, or, for that matter, our network for transportation by cars. We need places to store the cars, and we need a way to get a car from one place to another, and when we get to the other place, we have to store it again. Same thing for hydrogen. We need large-scale storage at the manufacturing location, medium-scale storage for local distribution at, if you wish, service stations or users, and then the small-scale storage that for which each individual user must be responsible, like a car or a truck. We need also a transportation system linking them, similar to our methane transportation system today. But there's users of different scale as well. A steel manufacturer will require many tons of hydrogen quickly to reduce the iron ore into liquid iron, and of course the hydrogen sucks up the oxygen and becomes water. A car needs about 7 to 8 kilograms of hydrogen to fill up, and it needs it quickly. And all of these storage systems must be integrated, secure, easily accessed, reliable, and safe. Here's about the smallest one that I could find that was interesting to me. It's a device being marketed by a company in Australia. It's about 1 meter high and 0.6 meters deep, I believe, something like that, to give you an idea of scale. And essentially, energy is converted into hydrogen by electrolysis, stored in the metal hydride, and then made available when needed. And this system can store 40 kilowatt hours of energy. Well, storing energy is difficult when the energy is coming at you in an intermittent manner, variable manner, and wind is that way. It's variable at all time scales, and it's not dispatchable. In other words, you can't take it off the grid when you need it because the wind might not be blowing. So even though the generation costs might be dropping to as low as 2.5 to 3.5 cents a kilowatt hour in the next couple of years, there's additional cost of storage. We can store it as compressed air, for example. Batteries, way expensive. Storage as hydrogen fuel, that is a possible pathway. So here are some density numbers. In a salt cavern, 1 kilometer deep, 20 megapascals pressure, about 15 kilograms per cubic meter. All these numbers are approximate, of course. At 40 megapascals in a well bore at 20 degrees Celsius, 33. 20 degrees Kelvin or 20 kelvins for liquefied hydrogen at minus 21, yes, that's right, 20 kelvins. That's very cold. About 71. 99 kilograms per cubic meter if it's stored at methanol, and 107 kilograms per cubic meter if it's stored at liquid ammonia. But there is a significant energy penalty associated with conversion of hydrogen to a different molecule and then reconverting it to molecular hydrogen to use in a fuel cell. Of course, you can burn ammonia and you can burn methanol, but they're not the best fuels. So for large-scale industrial storage, if we have salt, we're in good shape. It's unlikely that we'll be able to use depleted fields and depleted aquifers for storage locations for industrial scale amounts of hydrogen because of the very challenging issue of hydrogen leakage from underground storage facilities. But salt is a medium that is almost impermeable to hydrogen, and we do have good salt in Ontario. We need a large volume per cavern, and we can have vertical caverns if we have a salt dome, or we can have horizontal caverns if we have salt beds like in Ontario. These caverns are going to be on the order of 400 or 500 meters deep to 1,500 meters deep, far less expensive than surface tanks on a kilowatt-hour basis, low footprint, secure, safe, long life. You can't explode. There's no oxygen in that cavern, so there's no chance of explosion. Simultaneous charge and discharge of the cavern is capable from a single wellbore, properly designed. It's a mature technology. And just as an example, a 100,000 meters cavern at 10 megapascals, that would be maybe 700 meters deep. It would store 800 tons of molecular hydrogen. And there's a bunch of design criteria, of course, that you must honor. The depth to the production casing shoe is a critical one because you don't want hydrogen to be under such a high pressure that it breaks the integrity of the casing. There are disadvantages. You need suitable salt strata near hydrogen generation sites. These are rare. For example, Manitoba, BC, Quebec, Nunavut, none of these have significant amounts of salt, if any, and almost none in British Columbia, where the large industrial sites are down in the lower mainland. High capital expenditures, each well might be 3 to 4 million, up to 8 to 9 million, depending upon the diameter and the rock that you're drilling, plus surface facilities, etc. An environmental issue is that you have to dispose of 7 cubic meters of brine for every cavern cubic meter that you dissolve. The heat of compression of the hydrogen has to be dissipated somehow or used in some intelligent way. Slow brine accumulation in the base of the cavern means that the hydrogen may have to be desiccated upon withdrawal. And of course, there's geotechnical issues, steel embrittlement, although that's not a huge problem in the wellbore. It might be a problem at the surface. Saline aquifers, as I said earlier, are likely not suitable, but here's the problem: very limited salt distribution in Canada. In Ontario, 1 star, in Alberta, another star, and actually Saskatchewan as well. We have a lot of storage of various things in natural gas caverns, including compressed air, so we've got a good understanding of that aspect. And in Ontario, the blue shaded area is the location of the B salt beds. They are the best of the beds in Ontario. So they stretch from Windsor to Sarnia up to Goderich and almost to Bruce. Well, that's also where the best wind in all of Ontario is, right on the Huron shores. So if you want to generate wind power and store it as compressed air or as hydrogen, that's the place to do it, for sure. And of course, it's very close to Chemical Valley in Sarnia, close to Detroit and Windsor, which are industrial sites, close to London, near steel mills, relatively near to steel mills in Etobicoke and Hamilton. But what about the medium scale? Let's call it the service station scale. Well, we could use surface storage, we could use cryogenic storage, but these all have safety issues and size issues and footprint issues and cost issues. For example, metal hydrides are extremely costly because they have such a low mass ratio, although you would be filling them and refilling them regularly, so that might be a little bit better. Now, steel-cased cemented wellbores represent a viable solution for storage on the scale of several tons to 40 tons of molecular hydrogen. And of course, the wells can also store ammonia or compressed air or other things that we might want to use to generate power. So a well would look something like this. Low carbon steel casing, metal buttress joints, etc., etc. This is off-the-shelf technology. High density cement for enhanced confinement. We can easily, off the shelf, buy 30 centimeter diameter, internal diameter casing with a 60 megapascal burst pressure, 200 degrees Celsius rating, etc. So such a well at 50 degrees Celsius, 40 megapascals, would store 2 tons of hydrogen, and that's about 250 car fill-ups, or about 50 to 80 18-wheeler fill-ups. It's off the shelf, small footprint, modular. You can have 2, 3, 5, 25. Inherently safe. It's all contained in the earth by the steel casing and the cement. It's not constrained by geology. You can put this in a sedimentary rock, in a hard rock, whatever. And you can combine this with, for example, compressed air storage and use the two together in super high hydrogen turbines to generate a humongous amount of electrical power quickly. Here's a wellhead array. Of course, this isn't a hydrogen storage wellhead, but and these wellheads, as in many jurisdictions like Long Beach, California, they can be put into a concrete trench actually below the ground surface so that nobody sees them unsightly on the horizon, and they're not that big. In conclusion, salt caverns are the best alternative for large-scale molecular hydrogen storage, but they are not everywhere present, unfortunately. In Ontario, however, we have the location of the best winds and the best salt, about 400 to 700 meters deep on the Huron shores, stretching from essentially Kincardine, or north of Goderich by a little bit, down to Sarnia and even down to Windsor. Locally, we can store a lot of energy for small-scale power stations, peaking stations, service stations, etc. When we do that with steel-cased cemented wellbores for anywhere from 2 to 40 tons of hydrogen, maybe more. And this kind of storage scale, 40 tons of hydrogen, would be ideal for steel plants to convert fully to carbon-free steel. So, storage is an issue. That's the end of my talk. Thank you.
As in the previous panels, we are going to listen to all 4 presentations first, and then after we will answer questions. So the next presenter is Professor Xiaoyu Wu, who is an assistant professor in the Mechanical and Mechatronics Engineering Department at the University of Waterloo.
Thank you, Eric, for the introduction, and thank you, everyone, for coming and listening to my talk. So my name is Xiaoyu Wu, and I'm assistant professor in mechanical and mechatronic engineering. So today is my great honor to present about how we can use hydrogen as well as its carriers for energy storage. So first, let me introduce my group. It's a quite brand new group, so we call it Greener Production at Waterloo. In our group, we have different expertise. We're mainly looking at different membrane materials, as well as looking at the reaction kinetics, as well as system and techno-economic analysis. So here, just give you 3 examples of what we are working on these days. So first example is looking at hydrogen ammonia production, which I will briefly talk about, and how we can use the solid-state membrane to enhance hydrogen production and as well as to integrate it with ammonia production so that we can improve the efficiency. The second example is large-scale energy storage. We know that we have a lot of different options. We have battery, hydrogen, compressed air. So in this idea, we want to understand how the technology development actually can enhance and also how we can combine different combine energy storage technologies so that we can decrease the cost of the system. And then the third example is that we are developing this type of oxygen membranes and catalysts. So here shows you an example how we can combine hydrogen production as well as ethylene production into one membrane reactor. So there is some discussions of how we can use the oxygen that is produced from water splitting to produce hydrogen. So we have a source of oxygen here. So here we combine oxygen with methane so that we can partially oxidize this methane into ethylene. So in this case, we evaluate what is the effects of this membrane reactor compared with a premixed reactor. And you can see that because we're co-producing hydrogen, so the performance of the reactor is actually better than the conventional premixed reactor. So since this is a focus on hydrogen, so I'll briefly talk about hydrogen and its carriers. So Maurice already compared some of these hydrogen and its carriers. So here I only compare by weight as well as by volume, and I'm comparing all these liquid carriers, right? The reasons that we are interested in liquid hydrogen and its carriers because we want to understand how we can actually ship this, and we know that liquid is easier to ship, okay? So when we compare hydrogen and different hydrogen carrier, you can see that so hydrogen is always 1 and 1 because it's pure hydrogen, right? But then when we compare ammonia, this liquid organic hydrogen carrier, and you can see that they are around maybe 10 to 25% by weight. However, if you compare it by volume, it's much denser than hydrogen. So for example, using ammonia example is 1.5 times higher than liquid hydrogen, even higher than liquid hydrogen per volume. So that is why some analysis already show that if we can shift ammonia other than liquid hydrogen, we can actually decrease the cost of the shipping hydrogen from one location, in this case from Australia, that they produce a lot of hydrogen, to Japan, which is a hydrogen consumer. So this is a previous analysis, and recently we also have just started this project with MyTech. It's a MyTech project, and we are looking at with RWTH in Aachen as well as NRC. We want to evaluate how ammonia production and transmission can actually integrate the hydrogen economic of Canada as well as Europe. Right? So here shows you an example that if we have a lot of wind that is in the east coast of Canada, we can produce liquid hydrogen or ammonia and then ship it from our Montreal port to some of these ports. For example, Rotterdam is building a lot of hydrogen receiving portals, and as well as Hamburg in Germany. And once they receive this liquid hydrogen or ammonia, then they can redistribute it as hydrogen or as ammonia across Europe, right? And we want to evaluate what is the BAT, right? BAT stands for the best available technology. So we want to compare the performances, the economic, as well as the environmental of different available technologies and try to understand what is the best and what if one of the technology improved and how we can actually enhance the performance as well as the economics, okay? So this we just started, so Sukana is going to start in the fall, and so if we have some results, I'm very happy to share with you later this year. But in this talk, I'm focusing two of the topics that we have already some results. So first of all is using hydrogen for renewable microgrid. So let's look at this, right? So if we have a renewable microgrid, for example, using wind in this case, we know that the power generation and consumption usually they mismatch. So we want to understand how we can use, in this scenario, how we can use lithium-ion battery, which is good for short-term storage, and it's a very fast response, and as well as combined with power to hydrogen, which is a long-term storage and large scale. And we want to understand how this system will behave with the development of the technology, right? So here just shows you an example, the mismatch of the wind power as well as the load. So the load has some variations, but it's quite stable. But then the wind power usually changes from day to day, from hour to hour, right? So when we don't have enough wind power, then we might need to use hydrogen, use the fuel cell or the battery to power the load, right? But then when we have a lot of wind power, then we can use them to power the electrolyzer to generate hydrogen, or we can use battery to charge our battery. So how we can combine this in a microgrid, right? So we analyze this 100% wind power hypothetical microgrid in a Greater Toronto area. And so we assume that this microgrid has 10,000 residents, and then it uses a combined lithium-ion battery as well as hydrogen storage. And here shows you if the cost of the system changes, right? If, for example, if the turbine, lithium, and all these systems change, if they increase, how they will impact the overall cost, and if they decrease the cost because of technology development, how the cost of the system will change, right? So we identified that wind turbine, certainly because it's a big component, the system cost is very sensitive for wind turbine. However, if we compare, for example, the storage options, right? Lithium-ion battery is one storage option, and then we combine these three other components as a hydrogen storage option. You can see that hydrogen storage, the cost of hydrogen storage is one of the, so the system is very sensitive to the hydrogen storage. So that is why we were thinking that increasing the efficiency or lowering the cost of hydrogen storage is very important. And we also compare the systems, this current scenario as well as the 2050 scenario, right? So we know that current scenario, if we use only battery, then we need almost $100 million to power this 10,000 residents microgrid. But then if we use hydrogen, the cost is around $1/3 But if we have a hybrid system, then we can actually even lower the cost, right? But then if in 2050, when we have better technology, cheaper technology, then this number will be much smaller. So this is the first example of using hydrogen as an energy storage. Then the second example is using ammonia, because there are a lot of interest in using ammonia in the audience. So we can, considering how we can combine ammonia in the food, so now we can talk about how you can use the ammonia for agriculture. So we want to understand the role of ammonia in food, energy, as well as trade, because ammonia is a commodity that a lot of trading is actually happening. So that is what this the next topic is about. So we are analyzing electrified ammonia production. So the reason is because Ontario exports a lot of electricity at a very low cost, but the wholesale electricity price is almost 10 times of that cost. So this will actually lead to a lot of global adjustment and increase the cost of the electricity for our consumers in the province. So the proposed idea is how we can use this excess electricity to turn them into ammonia. And this is a very traditional, or not really traditional, it's one of the state-of-the-art systems. So we use a PEM electrolyzer, we use PSA air separation, and we use a Haber-Bosch synthesis load to produce ammonia. So once we produce this ammonia can be used in our local farms as a fertilizer. It can also use an energy storage for the local energy supply. And it can also be traded, for example, ship them to Europe so that we can get some profits out of it, right? So we did a base case analysis. So these are all from the literature data. So you can see that a lot of this energy consumption is going to the water electrolyzer. And very minimum amounts, they are going to air separation, Haber-Bosch process. But the overall is that we are almost using 11.1 kilowatt hours to produce 1 kilogram of ammonia. So we did some techno-economic analysis to understand what does this mean, right? How much does it cost actually? So this we compared different scenarios. So the base case levelized cost of ammonia is around $500 per ton. And then the sales of the ammonia, so we used 2019 data, which is quite low, right? As Nelson mentioned, that currently is almost $2,000 per ton. But we used the 2019 data because that's widely available in the literature. So you can see that currently, if we are making this ammonia from the electricity and then sell them, even locally or even export them, we can make some profits, right? But if we use them for energy storage, that means that if we convert this ammonia back into electricity and then sell this electricity at a wholesale price, we are actually losing money, right? So this is not a good thing. So we want to understand what improvement would be needed to make this power to ammonia more a profitable process, right? So we compare, so for example, we designed that what if ammonia production would become more efficient? That means that at the lower levelized cost will be lower. How about the ammonia to electricity conversion is higher efficiency, right? So that will increase our round-trip efficiency. Round-trip efficiency means that's electricity to storage and then to electricity efficiency. So we did a sensitivity analysis to understand how these two factors can impact the profits of using ammonia in Ontario. And so you can see that if we decrease the cost of ammonia, then for example, until $120 per ton, then using the current ammonia to electricity efficiency, which is 50%, then we can break it even. So that means that we are not losing money. However, if we want to make more money than just exporting the electricity, actually we have to make the levelized cost of ammonia very cheap, and we also have to further increase the ammonia to electricity efficiency to around 80 to 90%, right? So there are lots of development that we need. So that was why in our group we are developing this type of solid-state proton conducting electrolyte to enhance the efficiency. So we are looking at this proton conducting membrane that is at elevated temperature. It works very well at 150 to 250 degrees C, right? And then we combine hydrogen production. So on one side we have water coming in and produce hydrogen, and the hydrogen will permeate through this membrane because it's a proton conducting membrane. On the other side, we combine them with ammonia production. So the reason is because ammonia production is exothermic. That means that it's giving out heat. But then water electrolysis is consuming energy, consuming heat, right? So if we can combine them together, the goal is that we can enhance the efficiency. So in the lab, we make some of these membranes, and we'll be testing these membranes and also applying different catalysts so that we can enhance the efficiency of ammonia production. But we also, so as Nelson mentioned, that ammonia cost is actually is the December 2021 data. And you can see that in scenario one, we can make almost $1 billion US dollars profits by selling this ammonia, by converting this excess electricity to ammonia and then sell them, right? And the other scenario is that we are not using energy storage, right? We are not, because we know that currently energy storage is not, using ammonia for energy storage is not profitable. So what if we just use it for local consumption as well as for sales, right? So in this case, you can also see that we also make more profits than just using this electricity and export them. And the third scenario is that if we have technology improvement, right? So if the electrolyzer efficiency is higher, if ammonia production energy is lower, as well as ammonia to electricity efficiency is higher, so we can also see that even in this scenario, we can also make more profits than just exporting this electricity to the to our neighboring provinces as well as country. So, so that's all for my talk, and I also want to thank my sponsors and Circus MyTex as well as some. So the work are done by my students, which are mentioned here. And thank you so much. And if you have any questions, and I'm happy to answer them. Yeah, thank you.
I'm now calling Jay Duhan, who is a geomechanical engineer at RESPEC.
Good. Okay. Good afternoon, everyone. My name is Jay Duhan. I'm a geomechanical engineer. I work for RESPEC. We are based out of Rapid City, South Dakota. My main responsibilities include designing salt caverns and troubleshooting any issues faced during operations and planning of salt caverns. So of course, today I'll be talking about salt caverns, thanks to Dr. Dussault, who introduced everyone to salt caverns. Just to further that discussion, salt caverns have been used for decades for disposal purposes, for brine production. So like table salt you have at your home, it's probably coming from nearby salt mine or a salt cavern. And of course, salt caverns are used for hydrocarbon storage. There are hundreds of caverns in North America that's used for storage purposes. In fact, you may have heard about SPR, Strategic Petroleum Reserves. Biden administration recently mentioned that they'll be taking out oil from the SPR. So they have a total of 60 caverns in the Gulf Coast, and they can store a combined of 700 million barrels of crude oil. So that's a lot of oil which can be stored in salt caverns, and similarly a lot of hydrogen can be stored in salt caverns as well. So recently we received a lot of interest from the clients in the last 2-3 years for hydrogen storage in salt caverns. We have clients throughout North America. In Alberta there's a lot of interest, in Gulf there is a lot of interest, same thing in Kansas. I was actually lucky to be a part of a hydrogen hub that is being developed in Utah. Like, it's being developed by Mitsubishi and Magnum. They're developing a 1,000 megawatt facility which can power up to 150,000 homes, and I think they're planning to develop 2 hydrogen storage caverns. So recently we did a high-level study to figure out what is the storage capacity of salt caverns in various North American salt deposits to store and hold hydrogen. For example, what is the storage capacity in Louisiana, in Houston, versus caverns in Kansas, versus in Ontario, versus Alberta? So here's the agenda. I'll start with bigger picture, like how does hydrogen storage fit in within the bigger picture of hydrogen economy. Then I'll go over salt deposits in North America. I'll talk briefly about hydrogen hubs. Then I'll go over the approach we used in the study to figure out the storage capacity, and then I'll talk about the results. And I'll maybe give you one result that we found out that to match the storage capacity of 1 cavern in Gulf Coast, we'll need 37 caverns in Kansas and 20 caverns in Ontario. Yeah, I guess a lot of speakers before me have already gone over hydrogen economy and why we need it and the ways we can achieve hydrogen economy. Here is the bigger picture, the major components. So we have climate goal. We have to understand whether it is realistic or is it too ambitious, like how much time is it going to take? Is it 2035 or is it 2050? Then we have government policies like tax credits. Then of course we have to understand the industries that use fossil fuels and which can actually use hydrogen fuels, and we have to understand the infrastructure. Then hydrogen hub. We have talked quite a lot about hydrogen production and the issues. I will mainly concentrate on the hydrogen storage part and mostly just hydrogen storage in salt caverns. And then there is another component, carbon hubs, like CO2 removal, CO2 capture, and CO2 storage. Ideally, it's better to have hydrogen hubs and carbon hubs together, within the same place, such as Robert, this morning, the very first presentation, he was talking about Sarnia, where we have the industry, we have salt caverns to store hydrogen, and then we also have some formations where we can store carbon, potentially store carbon. Okay. So there are multiple options for subsurface storage options, salt caverns and porous reservoirs. About porous reservoirs, Dr. Dussault mentioned that it's a bit challenging because of containment issues. We may be losing about 20 to 25% of hydrogen every year, but I'm really focusing on salt caverns in this presentation. And salt, we can find it in it as domal salt or bedded salt. Like in the Gulf, we have domal salt. It's thick, thousands of feet thick. It's clean as compared to bedded salt. And bedded salt we have in Ontario, that's bedded salt. In Alberta, we have bedded salt, and Kansas, bedded salt. Ideally, so there are a few hydrogen storage caverns and domal caverns. The domal caverns are preferred because they're much cleaner. The salt there is much cleaner. They don't have that many known salt interbeds, because known salt interbeds can actually become a pathway for hydrogen to leak out of the caverns. So by known salt interbeds, I just mean that, say you have a 100-meter thick salt deposit, and within that you have couple of meter thick non-salt interbeds, which can be made up of shale, anhydrite, limestone, whatever. So here is a map of salt deposits in North America. That's Alberta and Saskatchewan right there. We have a lot of salt caverns in that area. The salt is pretty pure. And we have pretty big salt caverns there, and it's also an amazing place to become a hydrogen hub because of the presence of industry there. Then right here, we have Kansas, hundreds of salt caverns used for storing hydrocarbons. Then here is the West Texas. Here's the Gulf Coast, probably the best place to store hydrogen because the caverns there are huge. Like one cavern can store more than 10 million barrels of hydrogen. And then here we have the Michigan Basin, which covers Ontario as well as Detroit. And Dr. Dussault showed the zoomed in version of where in Ontario we have the salt deposits, so mainly in the southwestern part, covering Sarnia, Goderich, Windsor, and that's also where we have salt caverns and salt mines. Another place is the Maritimes. That's where we have salt deposits and can create salt caverns for hydrogen storage. The locations we analyzed in the study include Alberta, Kansas, Ontario, West Texas, and the Gulf Coast, so Houston and Louisiana. Also because all of these locations have the industries that can use hydrogen as a fuel, and we already have existing salt caverns which can be converted from natural gas storage to, say, hydrogen storage. So this is the approach we use. We use the thermodynamic principles. So I'll just read the slide. The thermodynamic processes involved in hydrogen storage cavern include energy changes caused by mass flow into and out of the cavern, heat transfer between the hydrogen and the surrounding rock, and heating and cooling caused by hydrogen compression and expansion. I won't go into too much detail here. The operating conditions. So we simulated the operations for 30 years of cavern life. We use 1 turn per year for hydrogen storage. I know there are, depending on the operation type, it can actually be 1 ton per day if you're using it to produce electricity. And the minimum pressure and maximum pressure, these two numbers are very important. The minimum pressure, we have to limit the minimum pressure as a rule of thumb to 25% of the lithostatic pressure, because if you go below it, we won't have enough supporting pressure in the cavern, which can lead to excessive closure of the cavern, which can also lead to roof stability issues. And also the maximum pressure, we should not ideally go over 80% of the lithostatic pressure, because then we can start fracturing the cavern walls, which can result in hydrogen leaking from the cavern. And these are just rule of thumbs. A geomechanical study should ideally be done based on the geology and the rock properties to figure out what these limits are. But these limits are very important to determine the storage capacity. Because I'll talk about it later, like the larger this pressure range, the better it is, the more working thermal energy we'll have in a cavern. Okay, so the cavern size was selected based on the thickness of the salt deposit. For example, in Kansas, because that's where we have the thinnest salt deposits, caverns in Kansas have the smallest volume, and because in Gulf Coast we have thickest salt deposits, they have the largest volume. We have to also account for regulations. In Kansas, even though salt can be 200 feet in thickness, regulators want the operators to leave at least 100 feet of salt above the cavern, just for stability purpose. And because they've had sinkholes in the past and natural gas actually leaking out to the surface, so they want to avoid that situation. Depth, of course, it's pretty important. Caverns in Alberta are the deepest, whereas caverns in Kansas are the shallowest. In Ontario, the cavern top we selected is at 1,600 feet, and the cavern height we selected as 100 feet, cavern diameter is 250 feet, and the cavern volume is 0.8 million barrels, which compared to the Gulf Coast caverns, which they can store about 9 million barrels, so much bigger caverns, which is expected because in Ontario, our salt is not as thick. So pressure range is very important for storage purpose. Pressure range has a direct impact on storage density. So the larger the pressure range, the better it is. So by pressure range, I just mean the difference between the maximum pressure in the cavern and the minimum pressure. Caverns in Alberta have the largest pressure range because they're deeper. So the deeper we go, we have more pressure range. But caverns in Kansas have the smallest pressure range because they're shallower. In Ontario, we have a pressure range for that particular location of around 900 psi. So let's talk about the results. So storage capacity, we're looking at two parameters, working thermal energy and storage density. So working thermal energy is actually calculated from working gas capacity, which is volume of hydrogen that can be used for storage. We also have base gas capacity, which forms we always need that volume in the cavern, which is about the 25% pressure mark. We need to have volume in the hydrogen in the cavern to meet that requirement. So the working thermal energy is dependent on size of the cavern and the pressure range. So larger the cavern, larger the working gas capacity we will have, and the deeper the cavern will have a higher pressure range and will have more working thermal energy. So the Gulf Coast caverns have the largest working thermal energy of about 505 gigawatt hours, whereas caverns in Kansas, because they are smaller and also because they're shallower, they have a smallest working thermal energy of about 13 gigawatt hours. And I think in Ontario, we have about 26 gigawatt hours. Here are just diagrams explaining the same concept. These two caverns are we picked in Alberta. They are at the same depth, so they have the same pressure range, but they have different sizes. So of course, the bigger cavern has working thermal energy of 125 gigawatt hours versus the smaller cavern, which has capacity of 77 gigawatt hours. Here is the example of the Gulf Coast caverns. They have the same size, but the one cavern is deeper, so that means larger pressure range. The pressure range in the deeper cavern is about 2100 psi versus the shallower one, which is around 700 psi. Therefore, the working thermal energy in the shallower cavern is about 200 gigawatt hours versus the deeper one, 500 gigawatt hours. So two parameters, size of the cavern and depth of the cavern. These two are very important. Another parameter we look for is storage density, which is just working thermal energy per unit volume of the cavern. And it is a better metric of hydrogen storage efficiency as compared to working thermal energy. Of course, we want, from a cost perspective, we want caverns with higher storage density. And storage density increases with depth, and it increases with increasing pressure range. So that's why I was saying earlier that we need caverns with higher pressure range so that they're cost effective. Alberta caverns have the largest storage density of about 510 kilowatt hours per meter cube, whereas caverns in Kansas have the smallest storage density of about 120 kilowatt hour per cubic meters. And I think in Ontario, it's about 200 kilowatt hours per cubic meters. And these are the diagrams explaining the concept of storage density. Maybe I'll just go over this example, the Gulf Coast example. This is the same scenario. The shallower cavern, storage density of 150 kilowatt hours per cubic meters versus the deeper cavern, storage density of 350 kilowatt hours per cubic meters, which makes sense because it's deeper. So in this scenario, it's much better. Another thing we should consider is that as we go deeper, because salt tends to close over time, so caverns can actually close at 1 to 2% per year. So that has to be handled as well. Here's my last slide, just showing the number of caverns required to match the storage capacity of the Gulf cavern. So that's one cavern in Gulf. To match the storage capacity of one cavern, we will need 20 caverns in Ontario, and then we will need 37 caverns in Kansas versus 4 to 6 caverns in Alberta. Yeah, thank you. So this was just a comparison based on storage capacity. Of course, there are other parameters that other people have talked about, like hydrogen hubs, like where do we actually need to develop the caverns. So having said that, like I did mention that we'll need 20 caverns in Ontario and 37 in Kansas, but those two places are amazing places to become a hydrogen hub. Yeah, thank you.
So our next presenter will be online. So our next presenter is Robert Stasko, Executive Director and CEO of Hydrogen Business Council.
Excellent, and thank you. So some of these slides are repetitive, and I used them this morning in the opening presentation. And the reason I'm going to use them again is basically to put things in context for storage. And the way I was originally thinking of putting this forward is we're talking about storage as an engineering or as a technical issue. I'm going to talk about it more from the business opportunity and commercialization standpoint. In other words, what is it in Ontario that's going to require storage. And the story is pretty compelling. Could I have the next slide, please? Pardon me. So I went through earlier about how we have an electricity grid that's getting greener all the time, but that at certain times of the day, because of the intermittency of wind in particular, we have a surplus of electricity at night, both from nuclear and from wind. Now, this may not continue, but I suspect that at least in the near term, there will always be a surplus. It may not be a large one from wind and nuclear in the evenings. And how do we store this? I mean, right now, you know, you can pump water uphill. That's about the best you can do. Or there is a compressed air storage facility in near Goderich that was developed by Hydrostore. There is ways that we can store it, but there's nothing at this stage that's dramatically cost effective in terms of storing electricity. Next slide, please. Next slide, please. I think I've gone through this, and we might as well go through this fairly quickly and get to the meat of it. Thank you. So we talked a little bit about this morning about the province of Ontario strategy on hydrogen, and basically both the federal and the provincial governments have come to the conclusion that they want to develop hydrogen hubs in Ontario. And fundamentally, they feel that this is the way to begin the process of transitioning to not just hydrogen necessarily, but to an electrified transportation and industrial base that does away with carbon. Atura Power was tasked by the Ontario government with laying out a provisional location of some of the hydrogen hubs that we envision. Not all of them, and I mentioned some of them earlier, and maybe I'll go back to them. If we could go to one more slide, please. And before I leave this slide, maybe it's worth mentioning, because one of your previous speakers mentioned how the salt caverns in Ontario are fortunately co-located with some of the highest wind resources. And many of the wind farms along the eastern shore of Lake Huron are nearing or will soon be without a contract to supply to the electricity grid. And the business model for them, since they're intermittent, may be to produce hydrogen, not necessarily to gamble on grid prices, because they would end up being a price taker. In the past, some of their contracts were take-and-pay contracts where they were paid whether they were dispatched on or not. That's not going to happen anymore. If you're a wind provider, if you can't follow the load, or if you can't come online when times of peak demand, then you're kind of stuck. You'll be a price taker, and that price might be very low. So Bruce Power sees itself, and that, by the way, the nuclear facility in Bruce, if you didn't know this, is probably the largest in North America, with the total capacity right now, I think, of around 6,000 megawatts. And that will probably increase over time to close to 7. And so they see themselves, again, somewhat constrained in that they don't necessarily want to bid all of that capacity into the electricity market. They'd like to offload some of it and produce hydrogen for commercial purposes. But they do know that they're going to need storage. Now, the salt cavern geology, as I understand it, does run along the eastern side of the lake, close to the nuclear plant. Maybe not close enough, but maybe close enough for commercial purposes. So I see this as being, first of all, a hydrogen hub, and also a hydrogen hub that will probably want storage for a host of reasons. And of course, we mentioned earlier about Sarnia-Lambton being a natural hub because of the Chemical Valley. They too are close to salt caverns, which are already being used for methane, for storing methane. Next slide, please. So maybe we should talk a little bit about Hydrogen Hub. In some cases, it should be self-exclamatory, but I'm finding myself constantly trying to explain what it is. And I think in its very simplest form, it's where you have 2 or more users that have a common supplier, hopefully more than one supplier, so that you have a genuine marketplace, even if it's a local marketplace, so that a user will have more than one source depending on what their availability is. But hopefully what we would look for is even a broader expansion of the value chain. So it wouldn't necessarily be just hydrogen producers and hydrogen off-takers. It might be hydrogen reformed into another product like ammonia or a biofuel. Or it could be producing products in that locale that can be exported, be they fuel cells or be they hydrogen storage technologies, that kind of thing. Could I have the next slide, please? Again, I'll repeat myself a bit that the first hub that's been announced in Ontario is the hydrogen hub, assuming that the federal grant comes forward to co-fund that facility for Atura Power at Niagara Falls. But Atura is also looking at Halton Hills, Brighton Beach, Nanticoke, and the Toronto Portlands. There will be other major hubs along the way, and we can talk a little bit about them. But this is my chance to give you a pitch about something that's close to my heart and to many here that I think have heard about it. We've been talking about decarbonizing the 401 corridor for many years now. And we have academics at the University of Windsor and University of Waterloo, for instance, who've been trying to develop this concept for some time. Apparently, it's captured the imagination of the Ontario government. So after the election, I fully expect that that's one of the projects that we're going to put forward. And it'll be rather ambitious because we have to, again, if it's not exactly even a hub, it's more of a corridor or a series of hubs along that chain along the 401. And the point would be that fueling stations would be there to supply transportation, whether it's trains, trucks, or buses. But more importantly, that we would also include suppliers of those trucks and buses, suppliers of the fuel cell technologies, suppliers of the hydrolyzers. All of them are here in Ontario. You can have a very high economic value chain right here in Ontario with many of the hubs that we envision. Next slide, please. Now, I apologize for the fuzzy nature of this slide. I had to do a screen grab from what was in fact the Ministry of Energy's website. It was passed to me through Atura. And Atura basically has laid out for us where they see their hubs. And so you can see on the left side that they see a hub for Lambton, they see a hub for Brighton Beach, Halton Hills, Niagara, and the Nanticoke. And so honestly, when I first saw this, I have to tell you, I thought, well, I'm not sure that those are optimal. But it turns out that all those locations have Atura assets. I believe most or if not all of them have combustion turbines on that site. And as I said earlier in the presentation, what Atura would like to do is produce hydrogen locally through electrolysis and then blend the fuel for their combustion turbine up to, depending on the maker of that combustion turbine, they can go up to 20 or 30% hydrogen, I'm told, without having to make major modifications to the unit. And more importantly, when they reach the end of their productive life, which may not be that far into the future because some of these assets have been around a while, they can buy gensets from Siemens and GE even today that can run on pure hydrogen. So you can see that the Atura philosophy would be, let's use this as blends. Let's look at a future where we would be generating peak electricity using a combustion turbine, but with pure hydrogen. But also that all of these hubs might then become nexus for other end users and other collaborators. Now, the one that I'm most interested to talk about today is the one at Brighton Beach, because, there may still be someone from Atura in the audience who can perhaps elaborate on this, but they recently signed an MOU to develop a salt cavern storage facility at Brighton Beach, which is co-located with one of their combustion turbine assets. So you could see, and if you look carefully at that, you'll also see that that's the end of one of the major 401 highways. So there is a possibility that that could become a natural hub as well. But I'm most interested in that pilot salt cavern storage because, to my knowledge, no one else is doing it. And so at this point in time, and it would be a very valuable learning experience, hopefully more than that, so that we can replicate that all along the eastern part of Lake Huron, all the way down to Goderich and even around Lake St. Clair to Brighton Beach. Could I have the next slide, please? So why do we need storage? Well, as we were mentioning earlier, in order to meet the demand here in Ontario, which will have a very large industrial demand and also hopefully a very large transportation demand, we're going to have to electrolyze and produce a lot of hydrogen. And so these are just gives you some of the companies that are involved, both here in Ontario and across Canada, but all of them will have a stake in this. Something that I didn't have a chance to mention yet, but Canadian Tire right now has built an electrolyzer project at their Caledon facility, one of their fulfillment centers, and they're using it to fuel their forklifts. Forklift trucks have been converted in Walmart. They've converted in some of the Amazon warehouses. They've been certainly been converted Canadian Tire. So, and the business case for converting from battery electric forklifts to hydrogen forklifts was compelling. It was about typically a 25% savings in operating costs for your forklift fleet. So this has been happening quite regularly in that kind of subset of the industry. What Canadian Tire wants to do is start retailing that hydrogen to cars and trucks at any of the locations where they've already produced and are already producing hydrogen, and they've increased the capacity of what they really need so that they have some excess capacity for such purposes. Could I have the next slide, please? And then we do have to talk about clean hydrogen from fossil fuels. This popped up earlier. It's whether it comes from Alberta through other means or whether we produce it by steam methane reforming and carbon capture here in Ontario. There will probably be a near-term role for producing so-called blue hydrogen from the cleanest SMR technologies. Now, my own favorite technology right now is methane pyrolysis, where you produce hydrogen from methane, but the only residue is carbon black, which is about as inert as things can get. You don't have to worry about burying a gas underground when you have carbon as an element. Everything from feedstock to industries to soil conditioning. So I'm hoping, I've been seeing results lately, and it's not my area of expertise, but I'm told that if you increase the scale of methane pyrolysis, you can compete with SMR technology. So, and it has substantial advantages if that becomes the commercial way that we produce hydrogen from natural gas here in Ontario. Next slide, please. Oh, and by the way, I just want to make a pitch. The Canadian Hydrogen Fuel Cell Association, whose slides I just borrowed there, we are an affiliate of theirs. To be frank, we're still doing some of the paperwork to make it all official, but to all intent and purpose, we are part of an affiliation of hydrogen industry associations from coast to coast, from BC to Alberta, soon to be in Manitoba, definitely here in Ontario, definitely in Quebec, and the Atlantic provinces are coming together to form an alliance there as well. So you can see that at some point we're going to all speak with one voice, but looking specifically at each province's special energy capabilities. One more slide, please. One more slide, please. I've shown that earlier today. Now, I can't resist, even though this is a bit off topic, and apologize for that. One of my pet projects has always been to electrify rail with hydrogen, because the most expensive, if you're electrifying a corridor by putting overhead wires to switch from diesel to electric, which Go Transit is considering doing. 70% of the cost of conversion is all that overhead infrastructure, the pylons that hold it up, the wires, the transformer substations, protective equipment, the fact that you have to raise some bridges, the fact in Union Station alone, they're looking at raising the roof of Union Station something like 3 or 4 meters to accommodate the extra wires. There's a lot of extra expense when you're electrifying using conventional methods that they've used for 100 years. Well, what if all you had to do was change out the rolling stock and use fuel cell electric, fuel cell battery electric hybrid traction drives, which, by the way, Cummins is manufacturing right now in Mississauga, has been for 3 years, and is shipping them all over the world. And this is why there's something like 10 or 20 trains, and I've just depicted some of them here, that run on hydrogen, commuter, light rail trains running on rails in Europe and in the UK. The one with the yellow front there, that's a converted electric train that was converted to hydrogen by the UK when they found out that that was the most cost-effective way of electrifying their corridor. So basically what you're saying is, instead of an infrastructure project where you put 70% of your cost into the overheads and it takes you 5 to 10 years if you're lucky, by changing out the rolling stock, you can do it in 2 years or less. And so it saves a lot of money. And so we're going to be trying to press, shall we say, Metrolinx into taking this seriously as an alternative. They did a study on it about 5 years ago, but at that point it was right on the edge of being economically viable, and they decided not to proceed because it was a new technology. Well, it's not a new technology anymore. One more slide, please. So it might be the easiest one to switch over is the rail link from Pearson Airport to Union Station. We all know the UPS Express. It's a diesel operated unit, which, although it's very efficient, most of the people who live along that corridor want it electrified. And Metrolinx has promised to electrify it over a decade ago. 5 years ago, when they did a cost study for electrifying it, they found it was going to be $400 million to do that. We expect that if you did it by just putting new rail stock on the rails, it would be more like 20 to 30 million. So huge, huge savings right there. On top of that, because of global climate change, that rail corridor gets flooded once or twice a year now, which means traditional electrification is no longer viable. One last slide, and I think I'll shut up. Oh, this is just the schematic for actually converting one of those trains. So you don't necessarily have to buy new rolling stock, but I have a report that shows that you could convert the existing rolling stock to fuel cell electric. And again, it would be a much cheaper way of doing it. Now, how does this fit into storage? Well, companies like Atura would be very pleased to have this kind of project as one of their customers. And one of the things that Metrolinx kept saying is someone has to give us a fixed price for hydrogen at least into several years into the future, so we have an assurance of supply. We're almost there, so I couldn't resist mentioning it because I can see that this is another potential hub in and around the airport. The airport around Toronto, by the way, is a huge employment zone, a huge zone of many, many warehouses that are switching over to hydrogen. And the Greater Toronto Airport Authority wants more hydrogen in its operation to green its operation, especially on the ground side. Thank you. I'll just wait and stop there if there's any questions.
Okay, the floor is now open for question and answer, but maybe I'm going to ask at least the local who are in person. So Jay and CRU to come forward. Is Maurice Dussault online now? Ah, Maurice, you're here. Okay, so Maurice can answer some questions. Okay, so without any further ado, if you have any question, please fire it up. So Claudio, I'm sure you have a question.
Yeah, that's my job. That was my assignment for this workshop. Anyway, as a question for Xiaoyu regarding his work on the microgrid that he was looking at. This issue has been, in remote communities, demonstrated that it works for long-term storage. Actually, there's a community, Velacula, in BC, that BC Hydro tried to wane out of, introduce renewables in it to wane it off of diesel. And they had this intermittent variable power coming from a local run-of-the-river station, and they needed basically, and they demonstrated that hydrogen works for long term. Now, for other type of applications where I couldn't understand why is in your analysis that you did for this community is the issue that you are competing with the grid in that case. With remote communities makes a lot more sense. I guess you saw the paper that we have in this area with a student here, Enrique, in which we looked at this problem from remote communities. That did make sense because of cost of diesel. But however, when you're talking about a community here in southern Ontario where you have access to the grid, it doesn't make a lot of sense because you are competing with the grid costs, right, which are very low or relatively low in spite of our cost. So that's my first would like to comment on that. The second thing that I was curious about is why did you look at wind instead of solar? Because in a community, urban community, solar is really the option. Wind is not as much. So if you can comment on all those two, I would appreciate it. Thanks.
Yeah, thank you, Claudio, for the questions. So I think the first question is, so why we select a Greater Toronto area instead of a remote community, right? So, so the goal of this study is not to design this type of hybrid energy storage, but trying to understand the role of, for example, the role of lithium-ion battery and hydrogen. So how actually we found that they're actually communicating with each other. It's not only that they are standalone. We are not adding just one battery and one hydrogen, right? They are actually communicating with each other. So sometimes maybe we have to use hydrogen to charge the lithium-ion battery. And sometimes we actually use lithium-ion battery to power electrolyzer. So we want to understand why these systems are communicating with each other. So the goal is not to design, I mean, you're right that this type of microgrid is more for the remote communities, but this is because we have the wind data of GTA, and we also have the cost estimate. So that is why the target is just to understand the system behavior. So we chose that easier to analyze example instead of a remote community. I hope that answers your question. Yeah.
Sure. My second question is regarding the second topic about the...
No, then I think you also ask about PV, right? So
sure.
we do try to include PV as well. So PV plus is wind, but as I mentioned, that this is just an example to study, so that's why we just chosen wind to start with. Yeah.
Sure, I got that. Just use it as an example. Fair enough. My second question was regarding the use of ammonia as a storage medium for hydrogen.
Yes.
And if I understood correctly, I'm not an expert on this, but from the discussions that we had today, I understood that that's not probably the best option because then you need to, there's a lot of energy in the process, then you have to recover it. However, you did look seriously at transporting this as ammonia to Germany, right?
Right.
That example you were looking at.
Yeah.
Can you elaborate a little bit more on the energy issues, the cost and all of that? Why ammonia? Why
yeah, so there are lots of different competing pathways to ship hydrogen, right? There's the liquid hydrogen, compressed hydrogen, as well as the liquid organic hydrogen carrier, as well as methanol. People are also discussing. So the reason that we focus on ammonia is because we are actually shipping ammonias millions of tons globally every year. So they're already standard, is set up, so that is why it's just the first thing that we want to look at because it's already happening. But you're right, that's when we scale this up, right? We actually have to have more ammonia storage tanks. We have more ships that is running
shipping this ammonia. Actually, we are interested in how this will impact. As far, for example, ammonia when it's emitted is a pollutant, right? It's not as good as if hydrogen is emitted, it just go to the air and then react with oxygen, become water. But if ammonia is liquid, right, or emitted to the environment and become a pollutant, so we do also analyze the environmental impact of how this, because we don't want to just say that cost is one thing, right? Because we are academic, we also want to understand whether CO2 emission-wise, whether that is competitive, or whether environmental-wise, whether that's actually feasible. So we want to analyze this as a big, more look at different perspective of this problem. Yeah. Thank you.
Yeah, Richard.
Yeah, I have a question for Jay, and perhaps Maurice might want to add a few comments. One of the facts you presented was the shallowest salt beds that you looked at in your survey, in your analysis, were in Kansas, and the deepest ones were in Alberta, presumably the Lotsburg. Now, to what extent do you encounter the problem of legacy oil and gas wells that are drilled into these salt deposits looking either for salt or more likely for oil and gas? And to what extent are they problems that you have in salt cavern development? It's interesting that Kansas has got the shallowest salt beds, because that was the first potential nuclear waste repository identified by the old U.S. Atomic Energy Commission back in the 1970s. And they realized after a huge outcry that it was riddled with abandoned oil and gas wells, and they could never assure the containment of the nuclear waste in that salt cavern. Now, so to what extent is the salt cavern option, which clearly is preferable for hydrogen storage, to what extent is it compromised in your view and in RESPEC's analysis by penetrating abandoned oil and gas wells?
Yeah, so let me clarify about Kansas. So of course, the salt deposits are bowl-shaped geometry. So it depends where in Kansas and where in Michigan basin we are looking at. So in Kansas, near the Hutchinson area, the salt starts at about 500 feet. Then you go near the Bushton area, which is the salt starts at around 900 feet. So there are a few gas storage caverns in the Hutchinson area, and there are quite a few brine production caverns as well. And that's where they have had sinkhole issues as well. And in terms of abandoned wells, I think the problem is much greater in Ontario. Like that's where we talk quite a bit, right? We never had to deal with abandoned wells while working for operators in Kansas. So clearly around their site, and there are multiple sites we analyzed. One cavern field, more than 100 caverns in Conway, more than 200 caverns in Bushton, more than 200 caverns in Hutchinson area. We never really had to deal with the abandoned wells problem. But I think it's much bigger problem for if you're for reservoir operations, because fluid can travel long distances horizontally, right? And then they can encounter abandoned wells and can potentially reach other formations through the wells. But in salt caverns, the whole point is that salt is impermeable. It should not leave the caverns. So personally, I never had to deal with any abandoned wells problems in salt cavern operations, but Dr. Dissau may have some more comments on that.
As you point out, that here in Ontario, we're the oldest oil-producing, gas-producing region almost in the world, going back to the 1860s. And so we've got 30,000 oil and gas wells, and probably about 3,000 that we really don't know where they are because they're so old. And it's conceivable we might have some problems with locating, and there'll certainly be the cost of plugging and abandoning. But unfortunately, we're relatively ignorant of where some of the older boreholes are in the Sarnia area and where the original oil and gas production was. Thanks, Jay. I much appreciate it.
Yeah, of course. And I guess I now have a follow-up question for Dr. Dissau, because I've only worked on a couple of projects in Ontario near the Sarnia region and never actually had to deal with any abandoned wells issue while working on a salt cavern operation. So Dr. Dissau, in your experience in the last few decades, have you ever experienced abandoned well issues while working on salt cavern operation?
I have not, Jay, and the issue remains one that has to be taken into account in the site location and design. But as Jay has pointed out, this is not a reservoir-wide storage issue. It's a fairly small area, actually. Jay was speaking of a cavern that might be 300 feet in diameter, for example, and I suspect much narrower if we're going to build a long sausage-shaped cavern in a salt bed in Ontario. So when you look at the superficial area, or the area of that cavern compared to the spacing of wells that have penetrated through the salina in Southwest Ontario, I think that we can reasonably site these storage caverns with a high degree of confidence away from all known boreholes that penetrated through the salt. In the old days, remember all those wells in the 1870s and 80s and 90s, they were very shallow wells that never penetrated the salt fully. Now, you raised the issue of the Lotsburg salt in Alberta. Indeed, the Lotsburg salt is a wonderful 150 to 200 meter thick deposit of recrystallized salt. Fabulous. It's just a fabulous resource. Now, the reason that the Shell Quest project chose that area to store CO2 is in the basal Cambrian beds and some Ordovician beds below the salt. Essentially, they have sufficient porosity, but no oil and gas anywhere in the sub-basin in which the Lotsburg salt is found. It's called the Elk Point subbasin. So that there's only a handful of wells that penetrated through that salt historically in Alberta. That's one of the reasons that Quest chose the site that they did, is because there are so few wells. In fact, when the Energy Conservation Board suggested that they might want to drill additional wells for monitoring at the reservoir level, Shell countered by saying, we have a remarkable degree of integrity because of the Cold Lake salt, that Lotsburg salt above us, and we don't want to impair that integrity by putting more wells through that salt than absolutely necessary. So given that there's only a handful of wells that penetrate through the Cold Lake Lotsburg salt, it would be very, very easy to make sure that locations are found that are, say, a kilometer distant from the nearest penetrating wellbore and still have huge numbers of potential caverns to build. And I think something similar, although not as promising, something similar could be generated for the salt beds in the Sarnia to Goderich corridor, where the winds blow. Yeah.
Thank you. Yeah, we have a question over there.
I have two questions for Dr. Wu. So first one is that in one of your slides, I saw that the cost for generation of electricity from hydrogen was cheaper than that from battery. So I was wondering, because in latest report from IEA, I saw that still cost of electricity production from any process of hydrogen would be much more than 3 to 4 times of any other production. And by 2050, they are expecting, if technology advances in fuel cell or hydrogen electrolysis, they might match. So I just wanted to know what kind of process you considered for obtaining that result.
Can you, because I think cost of hydrogen generation per kilowatt energy, right, kilowatt hour energy will be higher than using battery, but I don't know what you were referring to.
There was one slide in which there was a bar graph in your presentation where it was shown that the cost of electricity from battery was higher than the hydrogen.
Are you talking about the overall system? So if we use a only lithium-ion battery system, we need a very huge lithium-ion battery. So that is why the overall cost of the system will be higher than the overall cost of a hydrogen system, because in that case, we don't need that much amount of storage, and we don't need that amount of wind turbine. Are you referring to that?
I think that might be the case, because on the bar graph, it was only shown the bar with the prices. I don't know the system for the individual one.
Yeah, so the size of the system. So the target of that goal, the target of that project is we have to securely supplying electricity to that 10,000 residents. So that is why if we only use lithium-ion battery, we have to have a huge battery pack, and that is very expensive. And we also need, we found that we need more wind turbine so that we can securely supply the electricity demand. But then for hydrogen case, we found that the system is smaller. So that is the overall system. And per unit, I mean, lithium-ion battery is still very competitive. But when you combine all these effects into the overall system, and that will make it more expensive. Yeah, I think that might be what you're referring to.
Okay. And the second one was regarding the what Professor Claudio also asked, that storing hydrogen in liquid ammonia form would be the best in compared to volume wise, but if in the one of your objective, when you are transporting it between intercontinents or between two different countries, at the end you have to convert it back to hydrogen to use it as a fuel. So, but in one of the presenter earlier presented that in any form, if hydrogen is to be stored and then again extracted, the overall process efficiency would decrease a lot. So in that respect, though we are saving in volume, but the other end, when we have to again convert it, the overall system efficiency would really drop. So can you please comment on that or elaborate?
Yes, so based on the study from the Australia study, so if we want to ship hydrogen from Australia to Japan, they compare I show one of the graph that they compare ammonia, liquid hydrogen, as well as liquid hydrogen, liquid organic hydrogen carrier. So you're right that we need energy to convert hydrogen to, we need very minimum amount of energy to convert hydrogen to ammonia. But the reason is because that is exothermic reaction is giving out energy, right? But we do need energy to to crack ammonia back into hydrogen. So that efficiency is actually very comparable if you have to liquefy hydrogen, because liquefied hydrogen actually requires a huge amount of electricity. So that is why if you compare the amount of energy to liquefy hydrogen to cracking ammonia, they're actually very comparable. And also just add to one point that why people are interested in ammonia is because when we talk about hydrogen system, right, we always have this chicken and egg problem, right? Which should start first? Is it hydrogen consumers should start first, or hydrogen infrastructure should start first, right? The thing is ammonia, people are already shipping them around, right? People already have this infrastructure. So if we just tap in a little bit of this ammonia and start using them as a hydrogen carrier, as an energy carrier, so maybe that will actually encourage the field, the society to use this hydrogen. So that is also another reason that I think ammonia is attractive. Yeah, I hope that answers your question.
Yeah, thank you.
Yeah, Nelson.
I have a couple questions for Dr. Wu and a couple for Jai. Flow rate of your prototype solid-state ammonia reactor, what flow rate were you achieving there?
Yes, so the question is about the solid-state reactor, right? So we just started building them. We haven't tested yet. So we built the membrane, but we haven't tested yet. So it will, because so the membrane that we're building is very, very small, like a cone size. So it's a lab scale reactor that we're building.
Okay. Yeah. And then if you're successful with it, the material used in the membrane, do you foresee any issues with upscaling that?
Yeah, so that's a question about the material of the membrane, right? So the material of the membrane, we are combining two different membranes, so, combining two different materials so that we have the good proton conductivity. So one is ceria oxide. Ceria oxide is, although it's a rare earth, but it's quite cheap. It's one of the most available rare earth, abundant rare earth in the crust. So I don't think that will be a problem. The problem will be the other part that we use cesium. That might need a little bit consideration of where the supply chain would be. But then I think the good thing is that there are two components, right? So we need to optimize them to see what is the best performance. So if cesium is the limiting factor of global chain, supply chain, then maybe we want to look at another rare earth dopant so that we can make it more available.
Right. Yeah. Okay. Thank you. And Jai, who owns the salt caverns?
Who owns the salt caverns?
So if you have a salt cavern,
the operator.
Yeah,
sorry.
So if my neighbor has a salt cavern and I decide to drill and start storing hydrogen on my side, what's the process to get a deed for the salt cavern? Can anyone just start drilling wherever they want and start pumping hydrogen down?
No, I don't think so. I actually don't know about like land rights and subsurface land rights. And I think they're probably different in US and Canada.
Right.
But
okay.
Sorry.
Yeah, let me answer that, Jay.
Yeah.
Every jurisdiction is somewhat different. For example, in Alberta, all land that was not privately owned in 1905 is Crown land. So in Alberta, the vast majority of the salt deposits and pretty well 100% of the Cold Lake Lotsburg salt is government owned and is regulated through the Alberta Energy Regulator. However, here in Ontario, land rights included mineral rights, and those mineral rights have been, in some cases, sold on to third parties and fourth parties and fifth parties. So who actually owns the mineral rights is an interesting question. And we're trying to get that question answered a little bit in Ontario right now with respect to the potential for carbon dioxide sequestration. Who owns the pore space? Well, the same question arises, who owns the salt beds? And that question is not yet fully answered in Ontario by any means. And in the United States, it's a similar situation. There's private and public ownership of the subsurface.
Thanks. Thank you for that. My last question is lead time. So in manufacturing, somebody says, I want to build this. How quick can you build me a factory to build this? If I look at storing hydrogen in a salt cavern, how long does it take when you first start? Is this something that would take a year? Would it take 10 years? Because if we're considering this for hydrogen, we have to have a good understanding of how long it would take.
Yeah, the solution mining process can take more than 1 year. And of course, that depends on the size of the cavern, but definitely it can take more than 1 year.
Yeah, 1 to 3 years would be a good range, yeah.
Jay, you mentioned in one of your slides that the lifespan for a cavern is 30 years. So what happens at the end of the life cycle? how is it capped, and is the cost of that taken into consideration for the storage?
Sorry, let me clarify. There was just the operational lifespan in the model. The lifespan of Caravan can be way more than 40 years. That was just the model we used, the SALT Caravan thermal simulator. And there we modeled the Caravan for 30 years. That's a typical lifespan. But in Kansas, some of the Caravans I've seen, the wells were drilled in early 1980s. So clearly more than 40 years of lifespan. But once an operator has decided to abandon the cavern because of whether geomechanical issues, there have been excessive roof failures, or there are some containment issues now, then we go in the abandonment procedure, which is to just fill the cavern. There are multiple ways. One is just to fill the cavern with brine, and then, yeah, just plug the well. Yeah.
Claudio?
I have a question for Bob. You mentioned this transformation of this switch in Canadian Tire and other warehouses to these from battery forklifts to these hydrogen systems. Are you talking about fuel cell based vehicles, or just using hydrogen as to move an engine? That's my first question. The second question is, you said that it's 25% cheaper. Could you elaborate on that? I was surprised by that. Moving from battery electrical to hydrogen.
Sure. Can you hear me okay?
Yes.
Okay. So this has been going on for actually many years, but honestly, and maybe you can understand why this is the case, many of these large warehouses, when they start manufacturing hydrogen for their own use on site, and the local community finds out that there's hydrogen on site, it causes them some grief. Like in one case, for instance, in Caledon, the local community actually tried to stop it because they felt that hydrogen was an explosion hazard. So Canadian Tire had to go through a very elaborate process, and it took them a couple of years to finally get certified to produce hydrogen for their own internal use. But quite independently of that, the other big warehouses are switching. If they haven't switched over already, they will. And the reason is very simple. If you have forklift fleets that are constantly moving material around, and you have to recharge the batteries on those forklifts, that's half your forklift inventory is charging when the other half is being used. So you have to double your fleet. If you use a fuel cell electric, and it's a fuel cell, it's not internal combustion, it's a fuel cell electric, so totally non-combustion. If you use that, you cut the number of actual vehicles you need in half, and you can refuel it in 5 minutes. So the turnaround time is no longer an issue. So you can really run your operation 24/7, which many of them are. So it's this little microeconomy around fuel cell and material handling that's been going on now for 5 or 10 years. And most of us don't know about it because it's not a vehicle running around on the road. But clearly these warehouses are now becoming familiar with hydrogen and its application. And as I said, Canadian Tire is looking to actually start retailing it. And at their Caledon facility, they've actually started fueling some of their own demonstration fleets. And they're planning actually on buying a couple of, I guess, Class 6 trucks that are kind of like daytime delivery trucks back to the barn trucks as a demonstration fleet. So I don't know if that answers that question. As to how does that relate to, let me think, I'm just thinking out loud. I'm sorry, did that answer the question?
Yes, it did. My second question is a follow-up, which is, why are they producing hydrogen? What purpose for?
Strictly for their forklift fleet. That's why they're doing it. So rather than buying it and having 2 trailers shipped in, they put an electrolyzer on site and produce their own hydrogen.
Okay, thanks.
No problem.
Okay. Do we have another question? I have one, and maybe more for Robert. it's about the hydrogen transportation. We talk about storage. So I understand now that for large storage of hydrogen, it will be between Windsor and Godrich or something like that. And you mentioned, let's say, a hub in Nanticoke, for example. And if over there is a need of storing large quantity of hydrogen, can we transport hydrogen from the west toward Nanticoke, or that's not going to be very practical?
Well, no, it probably won't. And again, this gets outside of my area expertise, because once you start looking at distribution systems for hydrogen, I'm out of my wheelhouse. Because clearly what everybody tells me is that for as long as the lengths are not dramatically long, pipelines become a real option. And you need easements, you need to run under roads, you have to dig up dirt. So I often think of it as an infrastructure project that can run into all kinds of trouble when people hear that you're putting a pipeline in. But in terms of diameter of the pipeline, it will not be a very large diameter pipeline for hydrogen, especially if it's pumped at high pressures and volumes. So that's always one option. And the place where I think it's almost bound to happen is in the Sarnia-Lambton, all the way down to Brighton Beach area. That area around Lake St. Clair, I'm sure that if there doesn't already exist a pipeline, I wouldn't be surprised if there's one already there on hydrogen, but produced from more traditional mechanisms. But you can extend that pipeline. Now, if it's farther than a pipeline becomes practical, then you're onto tube trailers. And tube trailers are definitely going to be an interim possibility for producing enough hydrogen for, shall we say, transportation, because one tube trailer at one truck filling station, for instance, per day should suffice. But now you're adding the cost of filling that tube trailer and transporting it to the location where you're going to be dispensing it, and that's going to add to the cost, per kg. So it's honestly, we're in a bit of a unknown territory here as to which technologies are going to prevail and which solutions are going to prevail. So this comes back to this whole issue of hubs again. If we can keep the users and the producers close to each other, at least initially, then the possibility of either a pipeline or using tube trailers for short distances becomes practical and feasible. Once you're into long distances, I honestly don't know. Okay, perhaps Morris has a thought.
Just something general. The four-way shipping, a hydrogen network is very much like a grain network. We need, local sources come together, stored in large elevators. It's shipped out, and it is unloaded into large silos, where it's distributed locally again. So we need storage at both ends of this pipeline, whatever the pipeline might be, whether it's ships or whether it's cryogenic transportation in trucks on the highway, whether it's whatever. So at the production end, on the coasts of the eastern coast of Lake Huron, we have fortuitously wonderful salt caverns that can serve as the hydrogen storage medium. But when we start looking at distribution centers, let's say Nanticoke and let's say Waterloo, let's say Mississauga, let's say Cornwall, we do not have the salt geology.
Right.
So there are four ways to store the hydrogen locally so that you can dispense it to the local users, including the trucks, if we're going to do the hydrogen highway. Ammonia or some other chemical, like you could even convert it to methane if you want, or to alcohol, methanol, because methanol is pretty straightforward to transport and store. Cryogenically, and that means I think it's on the order of 21 or 25 degrees Kelvin. So you need a very dramatically significant surface facility that is cryogenically insulated. Certainly the technology is feasible. Number three, metal hydrides. Now the trouble with metal hydrides is the best we can do right now is about 4% by mass. So if you want to store 1 ton of hydrogen at a service station, which is enough for about 180 car fill-ups, I think, or something like that. It takes about 7 or 8 kilograms for one car fill up. So, you know, you're talking about one ton of storage of hydrogen would require, you know, about 30 tons or 40 tons of metal hydride. Wow, I mean, the cost of that is astounding. And then the last one is this idea of a high pressure compression in steel cased well bores, which can store on the order of 2 metric tons of molecular hydrogen under pressures as high as 40 megapascals, which is off-the-shelf technology in the oil and gas industry. That's not a high pressure in the oil and gas industry. So those are your 4 options: as a chemical, as a cryogenic fluid, as a metal hydride, or as a very high-pressured vessel of some sort. Which is best for a service station? I can't answer that question because I do not know how the hydrogen highway is going to unfold in Ontario. But those are our options, and I don't think metal hydrides have a role to play in this game. So that brings it down to 3 options.
I agree.
Thank you. Do we have question online or something?
Do we have time for one more question or not?
You can ask.
Yeah. I actually have a question for Dr. Dussault and Robert. So this is a very speculative question. So what if Ontario wins the race to develop hydrogen hub as compared to Michigan? Do we have the infrastructure to, I guess, provide hydrogen to the industry in Detroit and actually benefit from that? Say we develop a hydrogen hub in Sarnia and Michigan is lagging at that time, can we actually provide hydrogen or clean electricity to their industry? Do we have the infrastructure between Detroit and Sarnia?
You want to try that one first, Morris?
Yeah, I've looked at that a little bit. First of all, in the Detroit subsurface, we happen to have salt beds, and some areas they are very, very intact and have not been exploited, and there's no wells through them at all in some parts of the Detroit area. And these beds are about 400 meters deep in the Detroit area, and as you go towards the center of the Michigan Basin, they get down towards 800 meters deep. Some kilometers west of Detroit. So we have an ideal hydrogen caverns there for large-scale storage in the Detroit area. The second point is that there's relatively good pipeline systems, and you'd have to talk to Enbridge for the details. There's quite a network in Ontario for natural gas. And I understand that there's quite a network in Michigan for natural gas distribution to homes and businesses in the Detroit area. So I don't think it would be beyond a reasonable imagination just to simply drill a horizontal hole underneath the river, the St. Clair River there, and put in the appropriate pipeline structure in order to establish this kind of interconnection. I think that a very substantial amount of the infrastructure might actually be present right now. And the salt structures are looking very, very good in Michigan. And so things don't look bad. Now, as you start to go further away, for example, in Western New York State, we can also say the same thing, that there's salt beds, 400 meters deep in that area as well that are quite suitable. But when you get across the Appalachians to New York, well, there's no salt anymore. So you're going to have to use some other kind of a storage system. So the answer looks very positive, Jay, but we have work to do to nail together this framework. Yes.
Maybe I have a slightly different take on this, and it is that this is probably feasible from an engineering standpoint, but from an economic standpoint, I don't see it happening, except in one very specific way. The way things are right now, when Pickering shuts down in 2025, we're going to have a shortage of electricity capacity here in Ontario, and certainly at times of peak. At times of off-peak, there might still be a surplus now and then, but going forward, as we electrify everything, and we are electrifying everything, we are going to have to expand our grid at a rate almost unprecedented, but not quite, because, and Morris may remember this, if you go back into the 80s, we were commissioning a multi-unit nuclear station every 5 years here in Ontario. Pickering A, Bruce A, Pickering B, Bruce B, Darlington, every 5 years. So we expanded the grid capacity at great expense, I might add, but we did it, and we did it, the technology was there. Can we do it again? I'm not so sure, because now, of course, we're looking at wind and solar to make it green. They're intermittent. We may still need some nuclear base load, and that's problematic right now. So I guess what I'm trying to say is our electricity system is going to be challenged just to meet electricity demand, let alone produce hydrogen for storage. So my sense is that we're going to be consuming more hydrogen than we produce. And so if anything, we'll be looking for other sources. Now, there's one specific case though. As with electricity, we have agreements with our contiguous states that if there is suddenly a need, we provide that need on a need by need basis. So I can see a situation where we would have transactions of hydrogen between Ontario and Michigan, but they wouldn't be consistent. It might be a daily thing where one day it goes one way, the next day it goes the other day as the market evolves. But I don't see us in the short term becoming an exporter. Alberta will become an exporter for sure if they can get it to market. And now we see the eastern provinces, Newfoundland, very keen to export. Quebec wants to explore liquefied hydrogen to Europe. So the two coasts are probably going to end up exporting, but us here, not so sure.
Well, I have a counter question for you, Robert. It's an area that I don't know that much about. There's people in the audience may have much more knowledge. Here we have Saskatchewan, Alberta, New Brunswick, and the federal government all threw in a few tens of millions of dollars, each of them, into small modular reactors. And my question is, well, what's wrong with CANDU technology? It's one of the absolute safest of all of the nuclear cycles that are based on uranium. And the modular reactors are proposed to be based upon uranium as well. What are we doing pursuing another nuclear technology where we have one that we developed and have hundreds of years of reactor operation now, extremely safe?
Look,
what's going on?
You're preaching to the converted. I'm a big fan of CANDU. It's a mystery to me, although it may have everything to do with the economics. But just to give you an example, I know CANDU up, down, and sideways. I was in part of nuclear operations as a junior engineer. I designed safety systems for Bruce B. They're still running. And I wrote commissioning manuals for Darlington. I spent a lot of time at all three sites. Now we have CANDUs that are operating quite successfully and commercially in South Korea, China, and Romania, and Argentina.
Yeah.
And of course, New Brunswick is looking to repower. However, I like that site in Darlington. I would have liked to have seen two CANDU 6s there, 1,000 megawatts each. That would have meant a significant increase in our grid capacity. No, they've put an SMR there for 300 megawatts. Guess what? Stelco is going to take that whole. They actually need double that for their steel arc furnace.
Yeah.
So it's not helping. So I'm not going to be very popular with some of my nuclear friends when I'm saying nothing wrong with small modular reactors, but don't expect them to be the magic bullet, because by the time we replicate them to a point where they actually are providing significant electricity on our grid, it will be too late. We have to bend the curve this decade with what we have now.
Yes, there is no small modular reactor in the world that is operating commercially yet.
Nope.
This is unproven technology, and yet we put CANDU on the shelf. I find this incomprehensible, Robert.
I'm speechless myself. I'm just afraid that I'm going to get into deep trouble if but I suspect, maybe I can phrase it this way. As an export opportunity, the SMR, the 300 megawatt SMR is already signing contracts overseas, even though they haven't even built it yet, because we're going to do this, quote, demonstration at Darlington. So it's more of an economic development opportunity for the nuclear industry. But every time the government goes out and asks for a bid on a much larger nuclear facility, the price tag ends up being ridiculously high and they walk away. I think 10 years ago they did it, it was 27 billion. And the reason was, and here's the mistake the government made in my view, they said, we want a contract where there's no risk to the government at all. We have no downside risk. You take all the risk. What'll it cost? So of course, when they looked at all the risk profiles going forward over the 10 or 20 year early lifetime of that reactor, it just compounded to 27 billion. If the government had come in and said, we'll backstop you to the tune of 5 billion, it might have come down to something affordable. Now, you know, the government the government of Ontario is making billion-dollar bets right now on supporting Stelco, supporting Dofasco, supporting the car industry and making lithium-ion batteries. So they're just making a different bet.
Yeah, yeah.
Okay, it's now right 5:15. So I want to thank all the speakers for panel 3. So we have to put a closure now on this. Thank you very much. And I'm going to pass on the podium to...
Well, thank you very much. Thanks for a very interesting discussion. Thank you to the folks online who have been staying with us. It's been a long day. I realize that. Oh, sorry. It's been a long day. I really appreciate all of you sticking here until the end, and I really appreciate the contributions by many of the speakers here still present to make this a successful event. Unfortunately, we could not secure the participation of NRCan in this event. They were committed to, but the last minute they said no. We're not sure why, but anyway, we were also we're hoping to have some participation from either the federal government or the provincial government, which unfortunately we were not able to at the last minute. So just wanted to make you aware of that. We were hoping that we will have actually their involvement. In fact, I wanted to thank Bob Stacko for stepping at the last minute in our keynote speech at the beginning, which was supposed to be delivered by Deputy Minister from the government and NRCan, in charge of NRCan, which was the idea, but I guess it didn't happen. So with that said, thank you very much to all of you participating on it. I just wanted to conclude this long day. Hopefully the food was good enough and keep you fed through the proceedings. I just wanted to go through a little discussion about what comes next, okay? And I just wanted to make you aware of a good part of intention, as you would guess. Our interest here is to promote research. That's our main goal as an institute. The Waterloo Institute of Sustainable Energy establishing networks of collaboration. Some of you already know. We have worked with you or are working with you in some of these ideas. So what we're trying to, obviously, an interest is to establish these discussions, collaborate, and be a startup for collaborations. And in that case, our interest is to basically, our self-interest is to secure funding. And in that sense, we are always looking for collaborations in terms of MOUs or other forms of collaboration in terms of funding. Now, we're always interested in establishing these partnerships, okay, which are particularly appropriate in the context of the University of Waterloo because of the kind of structure we have here in terms of support for partnerships with the industry. We are unique, certainly, in terms compared to other universities, in the sense that the fact that the researchers on their own research, not the university, allows a lot of flexibility in those interactions. So we are always looking in terms of intellectual property. Some of you might already know. And so we are always looking for these collaborations. And an interesting advantage of doing business with us, or with university in general, particularly Waterloo, is the availability of matching funds, which allows us to basically duplicate, triplicate whatever funding is provided to us, as some of you already know, through NSERC or through OCI, Ontario Centres for Innovation. It used to be OCE, Ontario Centres for Excellence. Now it's OCI, and then through that mechanism, we basically can increase the levels of funding and allow these type of collaborations to happen. Now, as part of the intention of this event was to showcase some of the work that is being done here, some of the expertise, particularly in the area of hydrogen. And I wanted to highlight, basically, some of you already met these colleagues in the process of making their presentations, our expertise in this area. We have Mike Fowler. Thank you very much, Mike, for your contribution. He certainly has many years of working hydrogen. I know that for a fact because I collaborated with him not in the last 10 years, but 10 years ago we were doing quite a bit of work in this area when hydrogen was fashionable. Then he went off, became sort of an old fad, and now it's fashionable again, which we are I'm personally very happy for that, given all the work we have done in this area. We have Professor Shang Li here, who also has been doing this work for decades. So he's certainly an expert in this area, very well known, like Mike, in all these aspects of hydrogen systems, particularly fuel cells. We have Professor John Josquit, which is relatively new to our institute. I guess he's not here anymore. He had to leave. But you see that he's doing quite a bit of work in the area of hydrogen systems, particularly, I believe, as fuel cells. We have Xiangyu Wu, one of our professors, mechanical and mechatronics engineering, looking at different aspects of hydrogen. We have Maurice, which hopefully is still online, which is doing done quite a bit of work in geophysicals, geothermal systems. In fact, we are collaborating with him in these areas. And we have Professor Shang Galdi, which I guess is left already, which is a former, I guess, Waterloo student, and now is now in Quebec. Richard as well, he has done quite a bit of work. We're familiar with his work. Thank you very much, Richard, for your contributions to this event. He certainly is very active in all these aspects of storage and geothermal, geophysical systems for storage. We have Eric Crozet, which also is working in different aspects of compressed storage. Interestingly enough, now that I guess Maurice was asking how this is going to happen in terms of distribution systems, I know that, for example, in Germany, although this is a still smaller scale, all of these are using compressed systems, compressed hydrogen systems to distribute the hydrogen into these facilities. I actually visited one at the Fraunhofer Institute where we visited then. And finally, well, my area in hydrogen is mostly related to the grid. So I look forward to the work that Atura Power is doing in all of these aspects of hydrogen in interfacing with the grid. We certainly are quite interested now in all this process of electrification, particularly from what is needed from the grid side to make this happen, because it's not only hydrogen, now it's also electric vehicles. So if you think that an electric vehicle basically doubles the power of the demand of a house, you can think of the challenges that are being faced. On top of that, you throw in hydrogen, then you really have a major challenge here. And we have a major commitment to try to make that happen. A good part of that would be controls. That's what we're doing with utilities right now, how to allow basically utilities to control this charging, for example. And I think that would make all of this feasible. Now, our intention in all of these areas is to support your work. So these are I'm the executive director. Hopefully we'll soon have a deputy director as well, the Ontario Research Chair, which is being hired, and will be part of the team as well. We have Armugan. Thank you very much, Armugan, for organizing this. San as well, which has been basically our logistical expert that has made this possible. I wanted to thank them both for making this happen. We are planning to have more workshops of this kind in the future. For the fall, probably we're looking to net zero. We're trying to find hot topics and areas in which we have a lot of experts, okay? And we have a lot of expertise, as you could see here. Compress the issue of carbon capture sequestration, which happened was it November, October? Pardon me? October. That was a good also showcase of expertise. Now you have seen what we can do in the area of hydrogen and the outstanding experts we have around. And in the future, we'll talk about net zero, which to all of you are welcome to participate. These are hot topics, and hopefully we'll have the participation of government as well in these events. So with that, I wanted to thank you all, participants, presenters, attendees. Thank you for your attention, for your questions. I guess I gotta thank myself for that, because that was my job. Hopefully I wasn't too annoying. I'm well known in my area, in my field, for being a guy with a curious George. So I'm always full of questions. So thank you for your answers, your response, your contributions, and as they will say in Quebec, à la prochaine. Thank you very much. Thank you, guys. Thanks.